We're really, really excited to be here at Berlin. Thank you so much for all of the incredible support that this event happened. Thank you all so much for being here. We're really excited about all of the talks and everything that we have going. I'm just going to tell you guys a little bit about how the conference is going to unfold, and then we'll get right into it. So the first things first is, my name is Lee Wilkins, and I am the Open Hardware Summit Chair. This is Sid Germain. They are the community manager. We are different people. I have blue hair, Sid, different people. But to be a little bit more helpful around that, because we do collaborate a lot really intensely, especially on this event, you need something that's about Open Hardware Summit, or about this event, or about logistics about it, come find me, blue hair. But Sid is the year-round community manager for the Open Source Hardware Association. So something year-round, I'm gonna go. So first thing, I just want to talk to you folks a little bit about OSHWA, about the Open Source Hardware Association. I know every year we work really hard to go to a different city in the world and bring the conference to the amazing local thriving communities that are really excited about open source hardware. OSHWA is an organization that does exist year round, and we love your support to keep all the things that we do. So this isn't the only event that we do in October. October is Open Hardware Month. So Open Hardware Month, we celebrate all things open hardware, and one of the things that we do is we have a 12 or 24-hour live stream where you can be silly for 12 or 24 hours. And we have guests come in, members of the community like you, to share their amazing projects and just talk a little bit about all the open source things that are going on all around the world. And also Sid does a live stream.
For this year because there was logistical issues. For example, did you know it's really hard to run a live stream 2 days before doing a summit? Shocking, but monthly usually.
As a database of certified open source hardware projects. So you do not have to in any way get your open hardware certified, but it is one of the things that we do. So this is really amazing just to know that the projects that you're working with are for sure open hardware certified. All of the documentation is there, and you can search the database with companies that you're working with or using or have created hardware projects.
I really want to remind folks that as much as we love microcontrollers, which is so much, it is OSHWA's purview that anything made of atoms rather than bits is hardware. So, well, it can be electronics, and a lot of it is electronics, and that is very cool. It can also be all kinds of things like e-textiles, materials, biomaterials. We have open source perfume, we have open source flamethrowers, we have open source planters. We really love atoms. Any of them.
Kind of with that, OSHWA supports us all on their open source journey. So if you're a first-time open hardware creator, we're really happy to have you here. If you made a ton of open hardware projects, or if you're just open hardware curious, that's awesome. We're here to help talk about all of these things, and also to remember that open hardware is something that's political and something that we're excited about, and a form of activism that we are actively engaging. So I don't think you get to support things year round and be a part of our growing community. Thank you so much also to all of our sponsors who are helping us make this happen. So it's not possible without the support of our sponsors. So all of the awesome goodie bags that you guys have are full of sweet swag from our sponsors. Some of them are out inside the table room. Check out everything that they have. And yeah, we're just really excited to have such a thriving community, some of which are small projects that we've seen present maybe at the summit and grow to become larger companies. Some are foundational cornerstones community doing a lot of different important work. So we're just really, really excited. Thank you to Node Forum for Digital Arts, who's our collaborating partner on the summit this year. Without them, we would not have been able to hold the summit in Europe at all. So huge thank you, amazing support and logistic support, just getting through all of the bureaucracy and difficulty of going to a different country every single year. A special thanks to 3 specific people who really, really, really have like come through this year and would not be possible without Robert, Timon, and Alicia. You guys are just amazing. Just like every weird thing that we've been able to rely on these 3 people to. It's just a round of applause for these 3 amazing humans. These graphics were designed by Bleach Track. Amazing. These cool Rezo printed designs were designed to be tessellating repeating patterns. The snake patterns are generative, so they're always different, and Bleak Track makes really, really amazing artwork with these concepts and just generally amazing, cool sounds and graphics. You can see all kinds of awesome things. So if you need a weird looking or sounding thing, Track. Thank you so much to our volunteers. All of these bags were assembled by a cool assembly line of rad folks last night. So, and there are volunteers all around kind of making this whole machine kind of move. So again, a round of applause for our amazing volunteers making it happen. Just a quick note about the future. We are always looking for the next place to host the Open Hardware Summit. So if you have a community, especially if you have a local community that is really engaged in hardware, is really like curious, and you think that there is like a strong foundation in the place that you live to support an event like the summit, then please send me an email or come up and talk to me, and we'll look at what that could look like. We have a few candidates for 2027, but we're looking for every subsequent year forever. So there's lots forever. So the structure of the overall event is today there are talks and tables. So there's a single track. It's going to be held in here, and 1 track of talks that's live streamed. There will be no Q&A for every talk, but you can go to our Discord. There's a link on your schedule. There's a QR code. Join the Discord, and there will be a Q&A that's live for every presenter after they're done speaking. So that's a good way that you can kind of get some one-on-one time asking questions. And then tomorrow is going to be workshops and unconference. So many of you have signed up for workshops on day 2. There are 5 rooms of workshops and discussions. There's also space in those rooms if you get an official spot to kind of hang out and just like observe and like watch workshops. And for the unconference, by the registration table, there are 2 huge posters. So just write your idea of something that you would like to talk about or like to present about, and then also feel free to vote. So just use a marker and make a little X or a check mark or a cool smiley face next to the things that you would like to see. And we will plan an unconference track, and that will kind of emerge organically tomorrow. So please do that, take some time to share what you'd like to talk about. The badge this year. Thank you very much to Valia and Nata for your amazing help with this badge. So the concept of the badge is for everyone to bring things that you maybe have laying around, maybe that you want to recycle, maybe things that you bought too many parts and you don't know what to do with them, and then to exchange and trade. So there's a small envelope of a few components to kind of get you started in the badge, but the hope is that everyone is able to just like trade and all kinds of things. So looking forward to seeing the wild stuff that we, their badges. There is a solder station outside, thanks to iFixit. Matcha Cafe on the main floor for lunch. So they are also serving coffee. So if you just go out where you came down, right next to the entrance. And we also have refreshments provided by Arduino, but if you want some light, that's your best bet. This is the link to the Discord.
One of the programs that Oshawa runs is the Summit Fellowship. That is one of the programs that I spearhead. So every year we make sure to do our best to get 10 folks who wouldn't be able to get here otherwise to the summit, prioritizing folks that we don't often see in spaces. Thankfully, at the summit we have a pretty diverse community, which is really cool, but we love to make sure that we're helping support that community and getting those folks here and getting them one-on-one time with mentors and folks who are building really cool things and showing just like the vast array that open source hardware can be. So we have 10 wonderful fellows here this year that are going to participate in various ways. We're really stoked to have them, but one of the big things that exists within the community too is when you're signing up, there is the super supporter ticket that helps folks get here and helps fund that fellowship. So huge shout out to folks who claim the super supporter ticket and help make that happen. It is a huge help because it's a lot of work getting folks here from all over the world, but we're really thankful. So you'll see our fellows around hanging out. They might be hanging out in little packs because they already get to know each other from the work coming up to this point, and we're really stoked to have
them. By supporting Oshawa and becoming a member, I mean, Oshawa is a very small organization. There are and our amazing executive director, Alicia, and our colleague, so it's really just like, we're all part-time. Everyone is part-time. You know, we're just, so you do things like become a member, be a super supporter, then your money directly goes making these happen. Social events. So thanks to everyone who joined us for Hardware Happy Hour yesterday. Tonight we have open source open mic at CA. So yeah, it's going to be really rad. We have a handful of performances, and invite anyone to come and talk to us. Maybe tell us a poem or a joke or a song, whatever you want. And yeah, it's going to be a good time. And then on Sunday, we're going to close out the summit with the moth rave. The moth rave is just going to be outside these doors over there at around 7. A little bit of time when we're in these workshops, and we go grab a bite to come back to the moth rave. So yeah, with that, I will introduce our first MC, Kat Scott. Kat. So I'd like to welcome Robert Lee. All right, welcome, Robert.
Okay, yeah, so with our to you, Berlin, thanks for Sarah. I think, so we go right into the presentation. How do I say? Oh, very good. Okay. We're just here, Julian, Cologne, Serena, who already reviewed that so 3 people, 3 messages. And yeah, we want to make a business that does not mean you're evil, and we want you to document the process. So the first message is me. I'm starting here in front of you, telling you that I think open hardware is getting more mainstream. But how can we make an impact with open and sustainable manufacturing? That is the question today. I want to quickly focus in on a couple of different directions which should really be taken with a bit of because we need to change. And what you see here actually for us, research over time, did make us change the way we look at things. But this is when you see here the mechanical CNC machines. These are machines that are completely modular, they use standard parts, they have a great service, they work around the clock to make sure you have a repairable machine. They did start, and this is the story behind it here really, they did start as three people took things from the internet, designed from the internet, and along the world. Yes, and they're partner with us in our research project, our factory currently. And it's really important because they started to have a lot of shades of wood with their own stars and it really just says these simple things. Let's just do what you see here and make sure that we make it. This I would love to on many other machines. I must say this is very so let's also think now because machines are one thing. We are at TU Berlin, so representing our organization, I must say, obviously we do a lot of high tech also, and we know a lot of groups doing high tech. And this example here on the right, my able to tour it with Chris Winter yesterday here, and it's a very impressive project because making a low field MRI modular low cost, not even going to cost more than maybe 25,000 euros, somewhere in between that, would be amazing, and they are quite far in the. But there's a problem of production, that's manufacturing, because we want to change high tech, here. We have to think also a little bit out of the box. I think this is really something that the people at CERN did, because when they made this white rabbit solution, they made a nanosecond time solution. And what's important about it? They developed it, and then they went for contract manufacturing, so other people produced it. And I think so many people for listening in, should consider this because they have different producers, and like this, they make sure that they get exactly what they need. And I think this is a very important thing, that we produce things with specs and that we then get them produced also the way we need it. Okay, so let's think about fashion. And this is my last example. I'm actually starting here. I'm running on open footwear today. Somewhere in the room is also Yuval Sushkan, made this amazing open footwear. And white footwear. So this can change fashion, in my view, in the view of many others who already started making their shoes. And the great thing is they're customizable, they're made locally, they're repairable. We made it here with a team of people. And I'm running on them basically. I run as a team on them and a company run, and we run 25 kilometers. Not so long ago. Okay, so what I want to say here is this project was actually choose where we created locations in the world, and also 4 more locations where people made it a check and that knowledge. The production, manufacturing is so important. This project is very good. So just some closing words from me here. I think for product process one-on-one. Very recent publication from Mani et al. And it talks about a openness, readiness assessment. And this group, which is led France, Nancy, by years. So they made very interesting work to connect from the product level to the process level. We don't start using open tools. We don't start to manufacture one machine that are made for us. Yeah, we cannot make sustainable impact a lot of things. So this is just framing the problem a little bit, or also talking about what we need to do.
Thank you. Hello everyone. Bringing the second message. Really not. So this is much more here. And the second message is about words, right? When we hear the word business, about capitalism, liberalism, and so we try to not to avoid to bring our project at the level where they're actually distributed, sold, sometimes it's for this, right? That we can. But in the end, businesses can be interpreted as say a strategy for having more impact and to become scalable. And scalable could be another word that doesn't is connected to the profit. So the message is that from business to scalable project with a great impact. And I want to for the in our project Labs Factory, team advocating using artists, designers, and technology to try to build upon open hardware products and try to create something that was more closer to open manufacturing, distribution, but also supporting them for increasing values of European manufacturing, meaning including people and stakeholders in the process. These guys, for example, just a picture, there are many people involved. What they did, they tried to go beyond the idea of developing an open source manufacturer for a robotic car. You know, the manufacturer and they used it, they developed this manufacturer. Actually, what they did is developing this open source and the factor, but what they tried it was include also the idea of making circular production. So they the craftsman and craft everyone in the communities from the Alpine regions in Italy cycle the wool that actually waste in certain cases. Trend is like recycling plastic for new filament. And so creating production could be sustainable, but also involving the traditional culture of producing, creating craft objects with textile. So these are, so the idea is that our project, not just because it's nice craft object, because they are involving people of the whole system, meaning the craftsmen and also the communities from the Alpine places, and also focus on how to make the whole production for one project. Also, for energy alternative practical. So, project of course was according all of the hardware. One our project decided to support it. They went beyond the idea of design. They did it was very nice from designers. worked on the and also another project we supported where the idea of environmental data in the city went beyond the pure development of connected on bicycle that can us for having of environment. But bringing data for discussing assemblies, for using it for advocacy, using it particularly for information and involvement of citizens in the policy level. So this is why we consider this project beautiful, because they're just trying to address the systemic the policy. So this is how we're going to are supporting this idea of open hardware scaling up, not as but as project with an impact because they are involving and addressing different layers of development, that exchange, impact, and also the community beyond the.
For my course, which is and why documentation is needed to scale production and scale economy. This is basically 10 minutes in the talk. I want to make a big detour that will end up at the same place. And the detour is that I'm a biologist. I'm a researcher and I came to open source hardware through open science. And the good thing about that is that open source hardware in academia generates value. I think core value for the community too, like inclusiveness, are at the base of the thinking of how we want to develop open source hardware in academia. And the gathering of open science hardware, the community of people involved with open science hardware, they met for the first time in 2007, and we this year again for 10 years. One problem was designed to scale. But it's scaling of one object, but this one object is right. And I don't have time to explain why we came to it, but really we want to support open source hardware and develop concept for center of competence, workshop tutoring, and going to product there's a lot of elements involved with hardware, but I want to focus on the center of the project, and the other element particular to hardware manufacturing from the start of the project, because in the end only hardware which are built will happen. Right, and inside the Laos Factory project and inside the Open Make project, we developed helpers for the documentation. Basically, from an online view, the guide the documentation project. And the second part is that our production is and how you build a business or a sustainable plan for your project, and how people should use the hardware. And those different aspects. I'm very happy to discuss it further. And you can find us on the internet. We also have different exhibits, a workshop for on manufacturing, and exhibit. And with that, conclude with saying that scaling is important to get impact, and how it has to scale is something inside in the project. Maybe one hardware is enough. If you need 20,000 to get impact, then you should plan for 20,000. And with that, I thank you for your attention. I hope
Yeah, go ahead.
What we about today is not a finished product. This is something that is very much work in progress, and the reason why we want to speak to you all today is because we want more people involved and we want to know what you're doing relevant as well. So please help come and join us in the exhibition afterwards. A quick introduction to the team. Eric Nitsch, I think, is possibly a name that is known to many of you already. Unfortunately, he can't be with us in person, but we want to highlight his involvement. It's really him that brought us together around this topic, particularly a year or so ago when at Republica and Fab gathering in Czech Republic, we started some conversations about this. Eric is someone with decades of experience in mesh networks and I don't know what else. Oh, open hardware. Yeah. That's the one. And my colleague Vicky will talk to you very shortly. Vicky, I first met nearly a decade ago here in Berlin, but at the time she was driving the Global Innovation Gathering bus around East Africa. And more recently has been leading the Holopar project in Ukraine. Again, working with makers and mobile makers in conflict response. Tim, probably more of you know already also. Again, I met him here in Berlin when he was demonstrating the ASCO Tech at Rogue Gallery, which is a kit together over years of work with displaced people, displaced camps there. So teaching people in camps to be able to repair and maintain software, electronics and stuff, open hardware. And then I come from a background of having worked with an NGO in post-crisis, post-disaster zones across the Middle East. And so, oops, nope, sorry. So why did we come together? So 75% of disaster preparedness work creates investments savings, and with up to 93% of time saved. Only 5% of disaster spending actually goes to preparedness. And in a time where we're facing so many cutbacks, especially for funders, I think working out how we spend that money well is critical, especially at a time where we're facing an increasing number of disasters and conflicts. And in COVID-19, we saw a brilliant example of how makers can come together to solve problems in crisis, how designs can be shared globally, then localized and produced. However, I think it's fair to say that was a responsive response, and what we want to look at is how we go into preparedness, and particularly for challenges where there may not be an internet connection, whether it's because of natural disaster or security situation. People won't have the connectivity we actually had throughout COVID. So, what do we want to see? So, next slide. What we want to have is we want to have those tools, the tools for production, software, designs, for people to be able to produce what they need where they are. To do this, we know that we'll need education resources, we'll need documentation standards, and what we also want to have that kind of resilient communications, distributed networks so people can communicate with the area they're in, no matter what. So, the very much one way that we see this working is we have a sort of tech stack called Mark. And we see that being something which is co-created with makers globally, but it's localized to the local area. And you'd have some central maker space, which is connected to everything that's going on globally, but also connected locally, that in the event of disaster where you're cut off, you would still have this local communication. And going into that, we have questions about the Mark 1, about how it's set up so that it's already available and in the hardware that spaces have. Ooh. We have questions about how we continue to document what is localized, what is made locally, and that's fed back to others. And also how we are going to what do we actually need for crises? What are these things that we should be preparing in advance? And with that, I'll pass over.
Products and I would say that many clients guys more about that here, but definitely one more one example radio. I'll start for right. So already in parts, there are others, but this example brought us. So it's actually mesh nodes. Okay. I'll talk about the next slide for a minute. For example, the operating side, where you document what just happened. Of course, probably know the long list. I think there are many things that you can already figure out. Document our potential figures, for example, which is maybe more running network as well. For collaborative work, just had a meeting today. Beyond the know-how So talking about standards, talking about search engines, we're talking about linked data. If you are in that, where to look for, definitely this is also a set of tools that we need to figure out what exists out there, how we can collaborate. One thing that I was is any foundation. So maybe an example in general for software that is
do like FreeCAD, PCAD, and so on. So what software can engineers use in order to collaborate on open formats and open technology, right? So that's kind of the question behind this. And I think this is also a very relevant component when we're talking about nuclear emergency response. Last but not least, maybe the hardest part about all this is like how to actually create physical products and tools and toolkits. Here, just two names, the Absolute and the Open Lab Starter Kit. There's also a little bit the dimension that we are talking about. Small kits that are more for learning, tinkering, solving small problems, fixing things, repair things. You can have a look on these kits also at the table at the exhibit. But the Open Lab Starter Kit goes bigger, like big machinery that you can use in a tablet and so on. Both are actually applied around the globe already, but I'm pretty sure there are more. So this is kind of the scope that we're talking about, right? So to dive a little bit in one of these examples, the NIM that I mentioned, basically you can look it up, is a node in a network, for a mesh network. You can either use it locally and then have a local network. You can also connect it to the internet and then see how you can actually share knowledge. You share all the resources, the documentation, everything outside what you needed when you need to respond to certain crises, right? And that's a very essential component. And this one also will need active development and involvement to basically gather all the collections we have to the software tools and knowledge that we can provide through this. Another example, again, I was involved in this one with my work in Uganda. It's basically the one kit, I would say, that was also named ASCOTech, which stands for Access to Skills and Knowledge Open Tech Emergency Case. The story is a bit longer. I can tell you how that emerged at the table, the exhibit, but in general, this was the general idea. Out of this, we developed a modular set of repair tools. This idea is surrounded around the repair toolkit, but it's not limited there, right? If you think about the modular toolkits, I think this is also a very essential resource. They're organized, it's very topic specific for certain things, and can definitely have a wider variety of topics than just repair. But when we're talking about the things we need to provide, it's the knowledge transfer we want in these crisis situations. We want to definitely have access to tools and machinery to provide solutions, repair things, or even produce things, and in a wider sense, that's how we can connect and collaborate on those solutions. I think that it's just a glimpse of what's out there, but definitely make sure you involve yourself if you have a project that would fit into this category, so we can work together on a much broader scale of how these could emerge. And I pass on the mic to Vicky for the final words.
So we're still in the what is there so far category, and we've heard about software and hardware and standards and everything. The most important thing, as we all know, is the community, because they are the ones that decide what they actually want to have on their box and their repositories, and they're the ones who actually are going to prepare and respond to any type of disaster. And so here are a few examples of what's going on in this field, or what has been going on in this field that we know of. Again, it all comes with the, this is what we know of that we're comfortable to speak about. Please tell us more. So CADOS is a Berlin-based medical and technical response organization. They are currently working in Ukraine, Gaza, and Sudan. And and they have last year done a congress in this building for one day about what they call solidarity prepping. So let's not all go into the forest and build a bunker and live on ravioli, but let's come together in solidarity and still prepare for disasters. No matter whether we live in a state that has a very highly equipped system of people whose job it is to prepare for disasters, or whether we live in a country that is completely different, let's prepare in solidarity. One example from Ukraine that I learned about during the Toloka project is that from Ostrov, a beautiful makerspace in Kiev, if you ever happen to be there, they really were a community center where people came together. When there was no electricity, they put 10 car batteries in a row to provide electricity. When there was no heating, they figured out ways to heat up at least the 3 rooms that the community was gathering in, etc., etc. The Austrian community that Tim and I worked with for years through the road agency is a beautiful community who are always, like throughout 8 years of projects, they've dealt with the disaster of a war in South Sudan. Some of them are now refugees in Uganda, and that's where the Asperger comes from, because they were not prepared well enough, and so they needed to respond quickly. And then Susan has worked for Field Ready, like she said, in Nepal after the earthquake in 2015, on Solomon Islands right now, in Iraq after the war there. Amazing examples of how makerspaces and communities can prepare and respond to disasters. So this is happening. Again, these are just a few examples that we know of. And one thing for the Berliners, I wanted to put it here because I don't know much about it, but I read about it recently. Apparently there's an innovation hub Brasilia being set up at Ostbahnhof, together with the Berlin firefighters and a few other of these very official organizations. I'm very curious if anybody knows more, please find me. Where are we at? So, like Susan said, Eric brought the 3 of us together last year, and we organized a workshop with 15 participants, sponsored by the Offline Internet Consortium on enhancing disaster preparedness through offline first distributed manufacturing. A mouthful. It was basically people from disaster preparedness, from making, and from communication. So where in this nexus are good spaces to do stuff? And the kits, we call them Make Emergency Kits. By now, like when I handed the talk for Oshwa, by now we call them Make Resilience Kits, or MARC, which is what we wrote a proposal about this year to the GIG Fund, the Global Innovation Gatherings funding for member projects, kindly supported by the Judith Newsom Foundation, and we won. So we now have a small budget to build 3 pilots in 3 locations around the world. 2 of them will be the Global South, and 1 will be Eric's house, to build the MARC. And yeah, now we're here, so you see we're quite at the beginning. And this is how we think we want to do what we do. Again, open the discussion. We're going to build these 3 pilots, at least. If you want to build more, let us know. We just don't have more funding, so let's find ways. We want to attract attention. So, get more communities interested, get more people to share their knowledge and skills. We want to figure out how does this idea make most sense for most people? Maybe it doesn't need to be boxes and kits, maybe it needs to be a smartphone app. We don't know yet. We want to curate the hardware, software, and content. And there the biggest question is, what should be different and what should be the same in different communities? If you live in the desert, you probably need different things to prepare for disaster than when you live on the coast, etc. Then a more technical thing, and I'm surprised that that's not solved yet, but we need to ensure that the content updates every month, right? Or we have them regularly, so that the oldest possible content you have is 30 days old. And also that dead links are deleted. But I see that very often that it's outdated, it's dead links, and then you can't use the repository so well. And also Susan and I figured that out, like when you go to the Nimble build, it says as the first step to please make sure you install the latest version of Ubuntu on your machine. I would not be able to do that. So yes, I know I would be like, there's plenty of help out there, but if the world depends on me being able to do this, I need to link back to how does Linux work, how does Ubuntu work? You know, that's what I mean. Like, we have to think that we have to go a few steps back from where you guys are, and maybe even from where I am. Maybe I have to think of my mom as a persona. I don't know, but we have to think about this. And most importantly, we want to iterate together. If you're slightly annoyed that we didn't mention you now, please come and find us. We're very happy to mention you every next time we talk about this. If you think, people, this is a ridiculous idea, I have a much better one, please find us. If you think this is awesome, let's talk more, please find us. If you, I don't know, if you just want to say, I have this little thing that I would like to ask, please find us. We actually have a table in the room as next to coffee, so you'll find it, just follow your nose, and we'll be there today. And also, aside from the Discord, Wacoma, the Nimble mothership, has a Discord. If you scan this QR code, you're kind of automatically invited to the Discord. You do need a profile because Eric doesn't want to make it completely open. Again, I don't know how Ubuntu works, so I don't know what the pros and cons of open and closed services. Please come and meet us. Come and meet us at our table. And one little thing, we'll definitely be back here at 12:40 because then Nathan is talking about one of the things that we definitely think should be part of Mark, and that's the open source hardware manager. Thanks. 1 minute left. We are done. Thank you very much.
So next, I'd like to welcome Larry White and Neil Johnson.
Hello. And do we nail if we have sound?
You probably will.
Yeah,
Probably. Okay.
if you see us sitting up here, it's just want to make the sound be slightly better on the live stream. That's what's going on here. All right, so Larry is here to talk about Opera as a site for open hardware research and an untethered wearable objective.
Hi, thank you very much. As we were just introduced, yes, I'm Mary and this is Daniel. We're going to talk about Opera as a site for open hardware research and its untethered wearable projector. So people are often surprised when they find out that we worked on wearables for an Opera, but actually it's quite special to this production as well because the two visionaries who led the work were Paola Cristini, who's primarily known as a composer, and Mauro Soretta, who is primarily known as a jazz singer. And they had this vision that there would be an adaptation of a poem from Iris Radio, performed in the Metropolitan Museum of Art. And that as part of this work, there would be work performed. So some of that was driven by the venue. So we were in the Met Cloisters, which is a special site in northern Manhattan, in which they had taken parts of buildings from Europe and moved them to New York City and reconstructed them into a new collective space to show medieval artwork. But you might see if we're going to hold an opera here. There's none of the tactics of theater. There's no really detecting lights. There's no built-in sound systems. There's no obvious place for projectors. And it was also a processional opera. So we moved from room to room around the museum as this was performed. So how are we going to have kind of the things we need to make this opera have those theatrical moments? Then I'm going to take us back a step. So the topic of the opera was this poem, Primer Sueño, that was written by Sorana Inés de la Cruz in the 17th century in what is now New Spain. This was a time when nuns became nuns sometimes because they were women who were at the forefront of education and technology and wanted a chance to do things like write and research. And so she was a darling, actually, of the time, the literature time. She was published in Sevilla. She was asked to have her poems performed by the clergy at various important events. But she also was doing science, and she was also living a lavish and scandalous life from inside the convent. And of course, as women in this time did, eventually gets in trouble in the church and gets herself taken away. So, at this time, in Spain, which is now Mexico, nuns were asked to stop wearing devotional jewelry. They decided that the gold and silver crucifixes they were wearing were too ostentatious. So instead they were replaced by these objects. The escudo de monja, which of course, even though they're made out of base material, become as lavish as the things that they came before. So a lot of them were painted by people who were renowned painters, and there were also these sites for the imagery of the allegorical life of the religious life of the nuns or her family's aspirations for her. So, this is where the wearable finds its home, living over the hearts of the nuns. And this tech inspiration breakdown was by the costumer Andrea Lauer, who's a wonderful creative technologist in her own right. She envisioned them having lights and sensors, projection, sounds. It could record or play music. With this idea from Solana's work herself, there are many keys and there are many ways to kind of reach enlightenment. So that would be something expressed through these technological versions of the escudos. So here is kind of a more ended version of that. So the outside would have this imagery, and these are the tech features that they might have. So I got brought in because Andrea had a vision that the tech team would not just be her own idea, but that she would bring creative technologists who have their own experience and ideas to collaborate with her, and that's how Daniel also got involved. I was hired in part to be a research fellow for Vision into Arts. They have an impact lab for people who are making impacts in the changes of what opera can be. So my creative research in opera focused on 3 questions: sustainable creating, materiality and narrative, and open source creative technology. So in sustainable prototyping and fabrication, the 2 questions I started with were, how can we make sustainable making a major part of the creative process instead of just an afterthought? And can elements of this work be built from e-waste salvage and other reclaimed materials? So first we did some sourcing. The top image is materials for the arts in New York City, which is a wonderful reuse center that nonprofit arts groups can use to get free materials. The bottom left corner is what's left over at the university where Daniel and I teach. At NUITB, there's always leftover abandoned materials, and at the end of every year we clean and sort them and we turn them to places that students can use them for free, along with professors. And then we also went through our own stashes. I'm sure you all have a closet or larger, depending where you live, space where you have discarded things from past projects. So while I was doing my research, I kept my ear open to hear many of my collaborators say anything related to my work. So my favorite quote on this topic is, to understand the broke is to find God in the garbage. So that was from one of our museum advisors. So here we have our graphic prototypes. One had butterflies fly out of it. There were many that had sound. You can see the first version of the wearable projector is number 8. And number 3 actually has recording capabilities, so we again wanted to use audio. So we went on eBay and purchased buttons for training your pets to speak. It turns out people buy a lot of those and then don't use them. So, you are all familiar with the advantages of rapid prototyping, but there's also an advantage to this kind of quick and dirty, sustainable prototyping in the creative process in a large collaboration like an opera, which is we can bring a vision of what the technology could be without it being weighed down by the aesthetics of the specific thing. So this was our first technical demo. We brought all 9 of our prototypes in with the artists, and so that they could see them and begin to imagine what they might become in the future. So the next research topic was materiality and narrative. So what parts of the materiality of the costuming can honor the origin of the story? So we're talking about New Spain, 17th century, a convent, and also a dream. So what's the possibility of making something between countries to ground the work in a respectful and collaborative sense of place? So we were performing this in New York and the United States, but also it's of Mexico, and we wanted to make sure that it included Mexico. And how can the design choices incorporate materials and techniques from the past, the present, and the future? Again, we're living within a dream in a poem that was written long ago. So, the quote for this segment of the research is, "My work is a dialogue between the material and the ethereal," which is a quote from a sculpture that we worked with. We were lucky enough to go on a 12-day residency in Mexico and experience the material world, both as it is in Mexico today, but also through visits to museums and historical sites to interact with things that were related to Solon's life. And how that got included in the final versions of these pseudos were things like imagery. All of the imagery on the front of each piece was taken from primary resources. So for example, this one is the ceiling of the first convent where Solon lived, where they were, it turns out, far too strict. They would not let her do research in London, so she feigned illness after just 2 months and was able to leave the fine convent more than another thing that was from the primary research is the copper rivets that ribbed each of these pseudos. It was a detail that we saw on many of the historical pieces. Well, the idea of having things collaboratively made between the US and Mexico was not actually achieved on these pseudos themselves. We found other places in the performances where that was a reality. So David Herrera is a sculptor and also was the master for these performances. And Paloma Dominguez is an embroidery artist that we met during our residency in Mexico, who made these beautiful embroidered hearts that get revealed when they move their pseudos. And as to the question of the past, the present, and the future as represented in materiality, it's actually quite funny because I thought that would be a clear delineation. But really what I found is things either come from the past and we carry them forward with us through our culture, or we invent things in the present and they carry them into the future. But things only become sacred if we stop carrying them with us. So the only things that didn't exist in the present were the things that were lost. So for example, this is lacquer that was made from chia seeds, which since have been replaced by lacquer made from linseeds, and then moving into the present by artificial lacquers. So that was my learning about the materiality of time. So the last topic was open source creative technology. So can we document our process to demystify technology for costume designers and costuming for creative technologists? And because the open hardware, the director of Primaris Wayne said, knowledge is a call to freedom, which is a thing that probably is a shared value of everyone here. So, ironically, my first step in this journey was through the contract. So if you've ever signed a work for hire contract, it is very restrictive. It says the contractor shall not make any independent reports or project activities. So I was like, you want me to make this open source? This is a little bit problematic. And he said, well, what do we need to do to make it right? And I said, let me work with your lawyer and we'll apply some new words. So this gets changed to contractors shall be permitted to make use of independent reports and project activities for the express purpose of furthering fellowship research objectives. And similarly, on the ownership of the contractor work, we call out, this is created with the intention of sharing to open source. And all things created will be available for use for the producer and the contractor upon creation. And then we will choose among those things what else we will further share out to the world. So here are the finished Escudos. There are 7 visions of what the inner lives of these nuns were. And everyone is different. Speaker in your pulse projection service, Roman speaker, stained glass lighting effect. The one we're telling you about is the untethered wearable projector. And that's because wearable projectors are highly desirable in performance. And the reason they're usually tethered and usually not on the body is because the throw of the projector goes away from the body, because you need a place to get power from, and because you've got to control those videos somehow. So Daniel's going to come and tell you about how we solve these problems as he was the lead on the projector components.
Thank you. So here we have the Escudo, which primarily consists of a cutout from a control projector that is placed in the center of the Escudo with the lens facing up towards the performer. A Raspberry Pi 02W, which is attached to a Pi Sugar 3, and is tucked in to the right of the projector. It's a very tight space. And then we have a first surface mirror suspended on the brass rod that allows the performer to redirect the images out from their chest. So a first surface mirror, this was the recommendation from Jorg Kusanu, the project's projection designer. A first surface mirror has a reflective coating on the top surface of the glass as an arcase acrylic. In comparison, the second surface mirrors have a reflective coating on the backside. The advantages of which are that it prevents scratches and from other abrasions. To test this, you might want to place an object on the surface of the mirror, and if the reflection is touching itself, then you have a first surface mirror, as in the picture on the right. On the left, if there's a space, then it's a second surface mirror. Why would we use a first surface mirror? Well, the target does not distort the image, as in with the second surface mirror, so the image doesn't have to go through the glass or the acrylic before hitting the reflective surface. It prevents a secondary reflection of ghosting, so that's the reflection that when the light first hits the glass or acrylic, there's a slight reflection before it hits the reflective coating in the back. And then also the first surface mirror reflects more, about 15% more than the second surface mirror, so you get about 94% to 99% light reflected back on the first surface mirror. One caution is they scratch really easily. Do not ever put tape on them. These were easy to cut, and I tested it putting tape over top of it to protect it, and it peels right off. So there could be some exploration into coatings and such to protect it. So here's just an image of the secondary ghosting illustration. So for programming, we utilized RP Bitloper, which is a Raspberry Pi video loader controlled by GPIO pins. The main thing to note is that it is using OMX player, which has been deprecated since 2020. So you need to use a Raspberry Pi OS Lite legacy 32-bit image. Newer images use the VLC media player, and that does not have a connection to the GPIO pins. You saw that? Awesome. Cool. And then batteries. We went with the Luma. We wanted to have separate batteries so that we could change them out for performance. So the projector has its own battery, and then we use the high sugar-free battery pack for the Pi. Cool. And then we also use routers to bypass using Wi-Fi, which was difficult in a vehicle building. Cool. So here's our GitHub, and then. Oh, sorry.
Yeah.
Okay, cool.
Yeah, so if you want to download the resources we have now, there's the bill of materials, the SUV computer cutting, the model of these pseudo to be 3D printed and more. But I would say right now, the Google Doc from here is more in depth than they have themselves as a new learning journey for us. This is our first day of production, so we'll figure it out next year. But really, this is an invitation for people, of course, to make their own projectors. That was the image of the research here, that we didn't want us to just on production, we want to see other productions that people make. So you can have beautiful moments like this, and it wouldn't be to talk about opera music, so hopefully we will not hear sound.
Oh, we're not done. Hold on, I got next. Nice, restart it. Yeah.
All right, so this is a very beautiful place to have that contract. All right, next up, I'd like to welcome Sam Hardy to the stage to talk about creating single molecule circles with open source workers. There you go, that's all it is.
So is it just the arrow keys?
Yeah, space button.
Awesome. Okay, yeah, so hi everyone, I'm Sam. Just to sort of introduce myself, I'm here from Lancaster University in the UK, where I'm a postdoc in the physics department. You can see an image of the experimental molecular electronics group up there, which I'm a part of. And my kind of research interests really are around molecular electronics. And if that phrase doesn't really mean much to you right now, hopefully it will by the end of this talk. And also in developing new instruments to kind of measure these devices. So what I'm going to be talking about particularly today is how you can build a scanning tunneling microscope for low cost and use it to measure the electrical properties of a single molecule. So before we get into that, I should explain why I'm interested in molecules, and in particular why I want to put them into circuits. So the way I think about a molecule is as a kind of a customizable nanostructure. The molecules that we work with are typically between sort of 0.5 and 2 nanometers long. So that's 9 zeros. And these, at these kind of really small length scales, you get access to really interesting quantum phenomena, like quantum interference. And these allow you to really precisely tune the electrical properties of these molecules, as long as you can control their shape. And this is where kind of chemistry comes in, because chemists have this incredible amount of precision in how they can customize these molecules. Almost anything you can imagine, a chemist can create with varying amounts of synthetic difficulty. And so you can imagine kind of an idea of an electronic device, and instead of it being kind of nano-fabricated from a bulk material, we instead create the molecules that have the properties we want from the ground up, and then they self-assemble or grow into larger device structures. So why have we not really seen this realized yet? Well, the strength of these molecules comes from their nanoscale structure, and that also is what makes them incredibly difficult to work with. So when we're kind of testing out different things and trying to understand how different changes in the molecule affect their properties, we want a quick way to measure those electrical properties. We need almost like a multimeter for these molecules. But when they're about a nanometer long, you need incredible precision in how you position your electrodes to actually make a contact to either end of that molecule. And this is where the scanning tunneling microscope comes in. So this was invented in the 80s. And it really was transformative in that this was the first time we could see structures in real space with atomic resolution. And it uses the phenomena of quantum tunneling, which maybe sounds scary, but really all you need to understand about quantum tunneling is that if you have two electrodes and a gap, then there is a probability that an electron will cross that gap, even if classically it wouldn't have enough energy to do that. And that probability, and therefore the tunneling current, which is the rate of flow of those electrons, is very strongly dependent on the size of that gap. So if we take a really sharp tip, we put it above a metallic surface that we want to image, and we scan that tip across the surface, any variations in the height of our surface are going to change the width of that gap, and we'll see a huge change in our tunneling current. So this is how STM has been used to map surfaces with like atomic resolution. But I'm not really going to talk about imaging at all today, because what I think is really cool for me about STM is that, okay, we can do these nice high precision images, but we also have this tip that we can actually poke and prod at the surface with and interact with it. And that's what we do in these break junction measurements. So we have a metallic surface, in my case it's almost always gold, and a gold tip. And we start by just deliberately crashing that tip into the surface and creating kind of a nanoscale junction. And then we can slowly pull that tip back, and that stretches this junction through to its breaking point until eventually it snaps. And if there are no molecules on the surface, then when that junction snaps, you'd expect to see just the current drop away, right? Because there's no contact anymore. But if we have a molecule that just so happens to be bound between the tip and the sample, then we'll see all the current going through that molecule after the metallic part of the junction breaks. And we'll see this plateau in our conductance distance trace corresponding to the electrical resistance of that molecule as it gets stretched to its breaking point. So this has been a really powerful tool in molecular electronics, and it's one of the key ways we can understand the properties of single molecules. But the problem is that you need an STM. STMs are really expensive. You're talking typically hundreds of thousands to millions of pounds. And they're also not really designed for this type of experiment. Most people want an STM for high resolution imaging, and the last thing you'd ever want to do is crash your tip into the surface. So they're kind of overkill for this kind of measurement. So I started thinking about what we would actually need to build our own STM specifically for these experiments. And if we just put aside for now the electronics, which really could be a whole talk on its own, the actual kind of mechanical hardware of an STM is surprisingly simple. So we need two types of positioners. We have a long-range positioner. In this context, long range means about a millimeter. And this just brings the tip and the sample within close enough distance for tunneling to start. And at that point, the fine positioner takes over the short-range positioners. And these are piezoelectric crystals. So when you apply a voltage to these, they expand or contract, and that allows us to move our tip around with atomic scale precision. So this is kind of a thing that I've been playing around with making for quite a long time now. You can see one of my really early prototypes all the way on the left there that I made in my shed during the COVID lockdowns in 2020. And as they moved into the labs at Lancaster Uni, they kind of started to look more like scientific instruments and a bit less mad scientist-y. And you can see right at the end there something that we've just finished this year in the ultra-low noise facilities, which is our kind of state-of-the-art STM for these kinds of experiments. But when it came to choosing which one to open source, I decided that actually the second iteration from the right gives you the best balance of low cost and still giving you research grade performance. So this is the instrument I'm going to talk about. You can build this for about £300, and it gives you real ability to measure these molecules with real research level capabilities. So we actually use this in ongoing research in our labs. I'm just going to talk you through kind of some of the main features of the design that allow us to make this so cheaply. So you can see a kind of a cutaway image of the instrument there on the right. I'm going to start by talking about that composite frame. So the frame of the STM just holds all the components together. So you would think that would be a simple thing, but when you're dealing with kind of the nanometer scale, everything needs to be ultra stable. Any sub-nanometer vibrations or movements of that frame are going to show up in your measurement. So the materials that have good properties for this kind of thing aren't the ones that you really want to be working with as an individual or a homemaker. That are very difficult to deal with in small scales. So I decided on kind of a composite approach. So this is steel reinforced epoxy granite. We have a steel inner skeleton that everything's attached to. And then on the outside, we cast this in epoxy granite, which is just an epoxy compound filled with granite aggregate, which is pretty much sand. And this gives you a really good damping capacity along with the rigidity of that steel. So the steel frame is very easy to make. It's 2 laser cut plates, the top and the bottom plate, and you can just get those ordered through the post. And then the rods that separate them are just some 4mm steel rods, hand cut. And then when it comes to putting this into the epoxy, there's these 3D printed molds. So you can customize these to add, for example, windows and things for optical access. And they wrap around that frame and they allow you to pour in the epoxy and cure it and then crack the mold up at the end. And what you can see all the way on the right is a finished STM frame. And in the middle of that metallic thing is the heart of the STM, that's the scan unit. So the scan unit gives you all of the motion capabilities that I was saying we needed earlier. And this one's based on actually an open source project by another group that I've linked here that I really recommend taking a look at. Because the clever thing that they've done is they've combined that short range and the long range motion into one actuator. So it's more compact and it's less susceptible to vibration. So the short range provisioning, we have a piezoelectric actuator and a linear slide, and they're coupled together by a magnet. So when you move that piezo slowly, that coupling is very rigid. So the linear slide accurately reproduces those nanometer scale movements. But if you move slowly in one direction and then quickly in the other, the magnet slips, and so you get a net translation. When you do this over and over again, you can step and slowly move that slide longer distances. So you can see how this looks when it's assembled. It costs about £150 to make this 3-axis version. And these are about 15mm travel range in XYZ. And at any point you can stop and perform movements with a precision on the order of about 0.02 nanometers. So well sub-molecular resolution. And then once you get into that kind of positioning precision, you're going to have to worry about vibrations. So here's an example of an unisolated STM. I don't know if you can make out the yellow oscilloscope trace there, but that is the tunneling current during molecular measurements. And when I just drop this bolt on the floor, a few meters away from the STM, you can see a huge spike. And that's enough to basically ruin your tip and end your experiment for the day. So clearly, you're going to need some good vibration isolation to do these kinds of measurements. And what I've just built into this STM is a very simple viscoelastic stack. So we have a stack of laser cut plates separated by Viton O-rings, and these just damp the vibrations as they pass up the stack. And then going over the top of that is an electromagnetic shield, essentially just round aluminium tubing that just provides a little bit of resilience when you're trying to measure these very small currents to electromagnetic pickup. So in order to demonstrate that this thing actually works, you need kind of a benchmark with a known conductance. And a great thing for this is a single gold atom, because it's quite a common result in quantum transport theory that a single ballistic conductance channel has this conductance 2e squared over h, where E is the charge of an electron and h is Planck's constant. So if we stretch out our gold-gold junction, so there's no molecules there, it's just a gold tip and a gold sample. When we stretch it right before the junction breaks, we should have a countable number of atoms. And so we should see a staircase of steps of 2e squared over h as atoms leave our junction one by one. When we do this for real, that's exactly what we see. So this is a breaking trace, just zoomed in right at the end, and you can see these 3 steps of 2e squared over h, which corresponds to 3, 2, and finally 1 gold atom in our junction. So if we do this about 10,000 times and form a 1D histogram, you can see peaks showing the increased probability of these integer multiples of that magic 2e squared over h number. So we are forming reliably few and even single atom junctions. So if we can form a single atom junction, we should be able to form a single molecule junction, because a molecule is a lot bigger than an atom, but it's also a lot more complicated. And now we have to start thinking about the actual chemical binding of that molecule between the electrodes. So that has a lot of extra randomness, which is an important thing to understand in molecular electronics. So here's just a few traces. So this octane diphenyl molecule, so this is 8 atoms long. And you can see they have this characteristic plateau I was talking about earlier that corresponds to trapping a molecule in our junction. But there's quite a lot of variation between them. So what we would do here is collapse these onto a 2D histogram. So the brightest dots in this figure on the right correspond to where there's more data. And you can see kind of a shoulder on there on the right-hand side that is our single molecule plateau. So a lot of these traces have a single molecule in them. And then we can take the conductance peak of that. And it agrees very well with the accepted value of this molecule in the literature. But if we want to go a little bit further, we can now apply some machine learning-based clustering to this data set. And we can do 2 things. The first thing we can do is take out all the traces where no molecule was formed, because all they're doing is just adding noise to our measurement. And then we can take those traces that did have a molecule, and we can see what different types of junction we formed. So we can see there are clearly 3 different junction types there, corresponding to different actual chemical bindings and junction configurations. And this is really powerful for molecular electronics because we want to make devices that have consistent properties. So now we can go back, we can choose which of these configurations is favorable for us, and we can tune our chemical design, our deposition process, even our measurement parameters, and we can go back and try and optimize to increase the proportion of our desirable coupling in the data set. And then we can do this iteratively and hopefully work our way towards more reliable, consistent devices. So I hope I've convinced you that it's possible to build an STM for low cost that can measure a single molecule. So the next steps, I'm working on an open access paper that will detail this and include a build guide. On the next slide will be a link to the GitHub with everything so far in there. But if you're looking to build one of these things, I would either wait for the build guide or email me, and I'll send you the build guide so far. And then the data processing, I'm hoping to make open source as well, so that people can, whether they build one of these or they have an existing one, can kind of use that capability. And then you'll notice I've kind of skipped over the electronics quite a bit here. And that's because this is deliberately built to be kind of flexible in what electronics you use. A lot of labs will have something that they're familiar with or that they already own, so they don't want to waste money buying new electronics. I've used this system with various setups ranging in cost from about £250 to about £50,000. And the performance obviously scales with how much you're willing to spend on the electronics. But I am working on kind of an all-in-one controller that will be certainly on the low end of that price scale to build, that people can build themselves to kind of have a complete solution for these types of measurements. And so just before I end, I'd like to thank a few people. I'd like to thank everyone in the research group back in Lancaster, and especially Ben Robinson, the PI, EPSRC for funding the project, and I'd like to give special thanks to my brother Will, who gave me a lot of assistance with kind of the practical aspects, especially around pouring epoxy granite and getting the right mix and curing epoxy and things, which was kind of a new area for me that he has a lot of experience with. So yeah, thanks Will, and yeah, thank you everyone for listening.
All right, we have a short break coming up. Before you go on break, I want you to put your hand into your bag and pull out the zine. If you look at the zine, internally there is the schedule for tomorrow. Some of these things you need to sign up for, so make sure you sign up for them now. A couple other things to note: if you are jet lagged or just enrolling in a program that needs a lot of caffeine, the cafe is open outside. Please make use of it. Other than that, tomorrow is also an unconference, which means you need to pick the ideas that people are going to talk about
Woo! Amazing. And I got a question for y'all, and it's going to involve more weird hand movements. Put up how many fingers you have, or how many batteries you own. So, if you have one battery in your house, put up one finger. If you have two batteries, 2 fingers. We have any more than 4? Oh my goodness. Wow, you all have lots of batteries. Well, would you like to learn more about batteries? And also, okay, here's the follow-up question. How many open source batteries do you own? Let me see some fingers. I'm seeing a lot of fists. Fingerless hands up there. We have 5 open source batteries. We have 1 open source battery. But Kurt, how many you have at least 5 open source batteries probably. We have our next speaker is Kurt Smith. It was a PhD, is a scientist and engineer in the field of electrochemical engineering, focusing on batteries and electrocatalysis. Based in France, he's left conventional academia to work with the Flow Battery Research Collective, where he helps to democratize open source energy storage. Yeah, let's give it up for Kurt. And here is a microphone for you.
Thank you. All right, I'll get into it. Thank you all for being here. It's my first OSHA. I'm really excited to be here. So this is us in the lab. This is Daniel Fernandez-Pinto. He's the other main chemist contributing to this project. I'm more of an engineer doing the design. He's doing most of the electrolyte formulation. And then, of course, there's a lot of people on the internet and in real life that help us on our forum. So, quick slide and point I wanted to make. I stole this from someone else's slide on quantum computing breakthroughs. When you see the latest announcement of a breakthrough, don't say, finally, renewable energy is solved. Do say, where did they cheat this time? Because the battery engineering industry is full of a lot of hype. I'm sure you've all seen the media puff pieces saying a new battery is going to be 10,000 times more dense, last longer. Usually there's a glaring omission. So just wait a week or 2 for somebody to point it out. But you can believe us, everything we say is 200% true. So. And yes, we're open source certified, France 28. So we would like to get to the 10 plus kilowatt hour level. This is a type of storage unit that could be useful for a residential application. This is a this is a zinc bromine domestic system that was manufactured by Redflow, an Australian company. Notice the link is archive.org link. They are now bankrupt, so this design basically died. There's lots of liters of zinc bromine just sitting around in random Australian basements. It's a bit of a shame because I think it's really great technology, but the intellectual property in the form of patents is just left to kind of sit. So we'd like to avoid that, and that's why we're taking an open source approach. This will take a while to get to, but we're going to be prioritizing abundant and affordable materials, even if they're slightly less performant. Taking a hardware-first approach, so making the system scale and then being able to change to maybe better chemistries later. We're the Flow Battery Research Collective, but we're also open to non-flow designs, and we're trying to make it easier for other people to get into battery research. So this is a benchtop test cell. I have one here. Find me later if you'd like to take a look at it. Can you see the, yes, so we have, it holds about 5 milliliters of electrolyte per side, positive and negative side. If you have a positive and a negative pump, these are peristaltic pumps. And then you can see the electrical connections on the cell where you have flowing electrolyte where you do redox reactions, and that's how you transfer energy in and out of the system. So it works. We're able to do tests that last multiple weeks, which is about the same type of length test that's pretty common in academic environments. Our best testing conditions are able to get over 70% round trip efficiency, which is in the zone of being interesting. And generally our tests stop either because the power cut off at my lab and everything turned off, or we're getting long-term problems like maybe oxygen coming in because we don't have fancy equipment like shrink lines and glove boxes. We're doing this kind of in a shed. Like I said, no longer in conventional academia. I'm now a welfare king. And also leaks and evaporations over long time scales. Really just a side note, relying on those social safety nets to chase your dreams is absolutely a great way to do open hardware development. So I'll get into the chemistry. So we have two flow chemistries that we're actively using, and one that we are looking for static flooded cell application. So zinc iodide is really our workhorse chemistry. It's relatively safe, easy to get in most places. If you can buy these chemicals in the EU, it's almost guaranteed, as an individual, it's almost guaranteed you can find them in any other country, because the EU is very restrictive on what types of chemicals are available to individuals. So when the battery is charged, on the negative side, we're discharging metallic zinc. So it's actually a hybrid flow battery. You can ask me about what that means if you'd like to explain, but and then on the positive side, we have triiodide, which is iodine with another iodine molecule that we take back to iodide. It has pretty decent energy density for a flow battery. It's reasonably stable and efficient. It's a bit of a pain to work with because the iodine actually has a bit of a vapor pressure and it can basically corrode anything around it. But it's not bromine, which is nice. So you can see on the right, on the top left, this is a charge-discharge curve. So the top curve is the voltage charge, the bottom one is the voltage on discharge. And yeah, it's reasonably stable. This energy efficiency was over 75%. And this is really what we're using to try to scale the system up in a larger cell. We also have an all-iron chemistry that we're working on, which we would like to make work better. It's based on water and salt electrolytes. So basically, you just put a ton of salt in the liquid, and it makes things better. And better, I mean, you avoid generating hydrogen at the negative electrode during charging, which is a big problem with conventional all-iron flow batteries. So when you discharge, you're dissolving metallic iron into iron 2 and turning iron 3 on the positive side back into iron 2. Pros, it's cheap, it's safe, it sounds cool. The cons are we don't have it working as well as the zinc iodide system yet. We have some ideas on how we could improve that. We're currently trying to find some research funding to investigate that further. But this does actually work much better than the current commercial all-iron hybrid flow battery companies. If we try one of their systems in this setup, we can't even do a single cycle because it makes so much hydrogen. So this is based on other people's work in academia, of course, but we're the first ones to publish results for this in a flow battery system. So this is a 100. So this cell right here has an active area inside of 2 square centimeters. This one right here is 175. And on the right, you can see this is a centrifugal pump that is chemically resistant and driven by a magnetic coupling. So we're going straight into trying to go into a practical system. So no more peristaltic pumps, actually doing centrifugal pumps, which are much more efficient. We haven't done a lot of chemical testing with this yet, but it's in progress. And the design of this is such that they can be, the cells can be stacked internally, which is how you do it in a real system. So that's how you accomplish increasing the voltage while still only having 1 pump and 1 reservoir per side. So now we'll go into our static or non-flow batteries. So we realized that we could simplify things even further. We adapted some of our development kit technology to be able to use most of the components and then just still have a very well-defined area inside the cell and be able to test these flooded chemistries. So think of like a lead acid battery that you use for off-grid, or a car battery, or a caravan or something like that. And this has the advantage of being a lot cheaper, simpler for people to get started. So while we're interested in this for its future applications, it also lowers the barriers to entry to battery research once again. So yeah, this is just another, so basically we just swapped out 2 of the inner components for a laser cut acrylic piece. And on the left-hand side here, we can just basically inject a couple milliliters of electrolyte into each side, keep everything else the same, and then test these batteries without having to get anything else. So this static chemistry is based on copper and manganese in methane sulfonic acid, which is a innovation that we've achieved. It's quite early stage. So the negative side, you're dissolving metallic copper, and the positive side, you're dissolving. The reaction is a little bit more complex than this, but this is the overall reaction. It looks like I'm missing a plus sign on the right, but manganese dioxide. The trick is that manganese does a lot of weird things in aqueous solution, and you have to be sure that you're forming electrochemically active manganese dioxide. So that's what we're still trying to figure out, the cycling conditions, to always be able to do that repeatedly. But again, it works well enough to do testing, and it's definitely promising enough to keep going. So the energy density is on the same level as lead acid batteries. So you're not going to have this on your e-bike or on your phone, but it's quite cheap. The cost of the chemicals, the cost of the copper and the manganese salts and the acid. The problem is actually not the cost of the copper and the manganese, but if we take the system that we currently have and extrapolate it out to commodity pricing for these materials, I won't go into the cost of every single component. This is just kind of a relative, but the most expensive component actually ends up being battery felt, this conductive carbon material, which is the cheapest you'll ever be able to find is $25 per square meter. This actually ends up costing for 1 kilowatt hour an order of magnitude higher than the actual active chemicals. So we need to find a cheaper material than that. If this was actually going to work, of course we can use this to build larger prototypes, but we probably need to find something else. So we have an idea for a cheaper conductive graphite-based material, and that's so for comparison, lithium iron phosphate batteries is currently well under $100 per kilowatt hour. So just not in the same area of competition. But there's coke, so calcined carbon coke, so actually a byproduct of the coal industry. We don't know if this works. This is starting to approach a bit more the complexity of an academic battery laboratory in terms of the materials and the powders that we're working with, but you can see calcined petroleum coke, the unit cost, this is for 1 kilowatt hour, is on the same order of magnitude as, say, the acid and the copper and the manganese that we put into it. So there are routes to potentially getting to competitive price for this, but we haven't done this yet because it's a bit harder and we're still looking for the funding. But this would go, this techno-economic modeling shows that it could be comparable to lithium iron phosphate. That's not a guarantee, but it could be. At least the numbers work out on this sort of napkin sketch level. So we have a lot of things that we want to do. We're in the process of doing some of them. Continuing to test our large format cell that I showed you with zinc iodide initially. The goal is to just be able to reproduce what we have with 2 square centimeters with almost 200. That would probably be more difficult than we imagined. We'd like to do a proof of concept 1 kilowatt hour cell with the centrifugal pumps. That the ideal is that the battery obviously will make enough energy to power the pumps in a well-optimized system. The pumps are usually consuming 1 to 2% of the energy. In a non-optimized system, they can consume much more than that. We would like to validate the iron chemistry in our development kit so that we can scale it up. We would like to do that's a typo, petroleum coke copper manganese battery, because this seems much more viable for an actual eventual market application. In the meantime, we would like to test a bigger system with the graphite felt. So again, the kind of expensive approach, but it works, at least for now. And continue to look at other chemistries. So we have a system that you can basically fill with whatever liquid you want. So even academic organic chemistry laboratories, they can synthesize their own reactive molecules and use this kit to benchmark it in a repeatable way. So a quick note on being an open source project that deals with hazardous chemicals. It's really a big barrier to entry. I'm not going to pretend that it's not. The cost of the chemicals, the safety, but all of that said, there are still random people on the internet that post in our forum and are like, hey, we did it, it works. Not that many, but it has happened. And it was really exciting to see this because we don't know who these people are. We barely gave them any instructions except for what was already on our website. But it was enough for them to source all the weird little things you need and build a battery in your garage or their shed. So it feels a bit weird sometimes to set up all this infrastructure for hosting a project, and then you put your documentation out there, and then it's just crickets, But eventually, people can come and give you some really, really useful feedback. And to go further on that, it can be pretty helpful when you're trying to democratize technology to get these initial replications done. And I think for projects that involve chemistry, educational institutions are really instrumental to this because there are people there that have the skills to do that safely and the infrastructure to do so. So we have actually run 20 flow battery experiments at the same time at TU Eindhoven with an undergraduate engineering course. And this was a true trial by fire, but we did it, and we learned a lot. And to my knowledge, flow battery engineering had never been done. It's generally a graduate level research exercise, not an undergraduate teaching exercise. So this really forced us to simplify and standardize even more. So I would recommend that to other projects working in the chemical design space. So just want to do some quick shout outs. Daniel, the other main collaborator, Josh and Professor Sami Fayez from Utrecht, Alexander Quinn from the Burchett Group at MIT, everyone on our forum, all of our financial contributors, and Enelnet, who gave us our first grant that really helped us to get going. We have a website that has links to everything useful, and the QR code on the left is a YouTube video that I just made trying to explain the project and showing actually myself preparing some of the electrolytes, building the cells, talking about it in a bit more of a casual way. So thank you all for your attention, and I'm ready for your questions in the Discord.
Thank you very much for that. Talking about application and internet strangers making things, I want to give a quick shout out to when sometimes people get grants to work on projects, develop an open source idea, and oftentimes people are very smartly building in things like documentation into the budget so you can document it and get your open source out there. And an extra thing to think about maybe adding to your budget is actually money for replicators. Even the open source hardware associations help where branch. It's even doing things like having some kind of stipends to get other people kind of audit the technology. So it's a kind of fun idea to actually try to use and replicate it, and you'll learn a lot about that. So, upcoming next, we have a fun talk about knitting machines. And I know lots of people at Open Hardware Summit traditionally like strings. Who likes strings here? Yeah! Okay, what kind of things you doing with strings? Who's crocheting out there? Put one hand up if you're crocheting with the one hook. Put two hands up if you're knitter. You're a knitter. Nice. Put your hands parallel to each other if you're weaving. Weaving stuff. Now, okay, a couple of weavers out there. Well, we are going to hear an awesome talk called The Domestic Machine. And it is by Victoria Manganiello. And they work with Nicole Messier, who unfortunately said he cannot be here right now. But they are a group called Craftwork, which is a multidisciplinary art and design studio exploring the nature of textiles and technology through installation, storytelling, and material-based research. Victoria and Nicole are co-organizers of the Electronic Textile Camp. Who's been to Electronic Textile Camp? Yeah! And they teach at Parsons School of Design at New York University. So let's give it up. Here's your microphone.
Thank you for having us. As was just mentioned, Craftwork is an art and design studio working at the intersection of textiles and technology. We are based in Clinton Hill, Brooklyn, so if you're ever in New York, please come say hello. And today I am going to tell you about a project that we have been working on for a number of years called The Domestic Machine. It will culminate in a documentary film, which we're currently editing, and at the end of the talk, I'm going to show you all our trailer for that. But today we wanted to draw some attention to the history of knitting machines and the overlap with open source ethos. So knitting machines, among other craft materialities, have been sharing information freely in this open source ethos long before the name came along. When we think about the history of technology, craftspeople are often left out of that history, especially those that come from marginalized groups like women and domestic workers. So the history of the knitting machine is a nice chance for us to bring them back into that conversation. Looking at the definition from OSHWA of open source, we wanted to draw out some of the criteria that are present in the knitting machine community. Criteria 1, documentation. So in the knitting machine community, design files, hardware and software are shared and released in a format that can be modified and built upon. Criteria 4, derived works, modifications, and derivatives are encouraged and may be distributed. All kinds of materials that need to be translated across languages, for example, from different places, different modifications for updated technologies are all available. Free distribution, criteria 5. There's no limit on distribution, and there have been a lot of incredible craft communities that have popped up. Maybe you're familiar with Ravelry or Knitlist, Knit Club, and of course YouTube, where so much information is shared freely. And criteria 7, no discrimination. So the license to use these materials does not discriminate against anyone. People of all types are working with knitting machines. So looking to the history of knitting machines, the first is credited to Reverend William Lee. It's called the stocking frame. And the lore says that he was frustrated with his wife for spending so much time knitting, so he made a machine that would knit faster so that she could spend more time with him. But that machine was never patented because Queen Elizabeth I was wary of it taking jobs away from the hand knitters. So it's interesting to look at this history and see that it has always been of the commons. The first guild that was formed for knitting machines was called the Worshipful Company of Framework Knitters in 1657, and it was specifically around maintaining and teaching people how to build and utilize these machines. It included an apprenticeship program. There were regulations on the hardware. Unfortunately, there was a limitation on who could access and build these things, so they kind of stepped outside of our ethos briefly, but they did maintain this passage of information from person to person and generation to generation. They also created a lot of really helpful materialities. So here we have some images of some examples of the documentation. Everything was clearly labeled, and this information was circulated by the Guild for about 200 years. Some more diagrams that they were creating around these machines. So there was this guy, Felkin, who created a book in 1865 that sort of gathered all of that information that had been created and shared for the usage and maintenance of these knitting machines. And it really helped preserve this knowledge. As time went on, the machines continued to develop as well. And we just have some more beautiful images of some of these old documentation. This is a part manual for the ripper of a knitting machine, and you can see everything is labeled with a number and a letter so that someone could get access to the parts that they needed. So going a little bit further ahead in history, we start thinking about the home knitting machine, the domestic knitting machine. So in the 1890s, this flatbed knitting machine, which maybe some of y'all have seen or used, became available. And it really started to stimulate this cottage industry where people, especially women and domestic workers, were able to create things in their home space alongside their other domestic jobs. They could, for example, knit a sweater for L.L. Bean and be paid by the sweater. They would be sent the yarn, create the sweater, send it back to L.L. Bean, and they were able to make some income that way. And unfortunately, in the 1980s, with the rise of fast fashion, these machines sort of abruptly go out of business, and the manufacturers, all but one, basically stop producing them. Brother, even though they were one of the companies that stopped producing them, has remained one of the most popular knitting machine brands. They created machines that were early mechanical models in the 1950s through to the until 1969. Then they introduced a punch card system for more complex stitch patterning. And then the electronic machines that were around from 1976 through 99 expanded the possibilities. They were designed with about 600 pre-programmed patterns, and they supported hundreds of stitch modifications as well. And eventually they were designed to work with floppy disks. Nintendo, just at the end of this time period, came out with a board that could be added onto your knitting machine. Sorry, they didn't come out with it. They prototyped it. It never came out, sadly for us. They did show it at some of the trade shows, and a few people got their eyes on it, but for the most part, there's not much that remains of that prototype in the public space. This is an image of the advertisement or the poster that they had at the trade shows. And I just wanted to call out that the poster says, Nintendo Knitting Machine is just one more example of the innovative thinking that keeps Nintendo on the cutting edge of video technology. So we just love this call out of knitting as a technical skill. So when the internet comes around, there are these opportunities for the people who have held on to the knitting machine knowledge despite the machines not being produced. And have started uploading information to the internet to help people figure out how to use it. And along with their content that they're sharing comes so many more people who are interested in learning it. And things like Ravelry, KnitList, knit clubs start forming places for people to share knowledge on how to use these knitting machines. And on these forums, you can really find almost anything that you might need: how to repair your needle selector, for example, how to adapt your yarn weights for different types of machines, how to replace a broken motherboard on one of the electronic knitting machines, how to modify your carriages, anything that you might need to make your old machine work again. In addition to those community spaces online, the YouTube space has been really incredible for people to share their knowledge. On the left is a screen grab from Diana Sullivan, who's one of the subjects in the film. You'll see her in the trailer in a few moments, showing how to replace the floppy disk in one of these old electronic knitting machines. And on the right, you'll see a video on AYAB, which is an open source hardware and software platform for these knitting machines. Here again, AYAB, which stands for All Yarns Are Beautiful, which started as a German project but has become a international project, which has been getting a resurgence. They continue to update the software and the hardware, and it allows you to override the motherboard that comes with these electronic machines and connect it directly to your own computer. A few other similar projects, just wanted to call out GlitchKnit from Socano did something very similar, and the OpenKnit project, which wasn't exactly focused on patterning as much as 3D shaping with knitting machines. So The Domestic Machine is the name of our film. Like I mentioned, we are currently in the editing phase, so we're hopeful that the feature-length film will come out early next year. And I'm going to play our trailer. Let's hope the sound works. So we are thrilled about this project and can't wait for it to come to a theater near you soon. Like I mentioned, we have been in the editing process, and we're really excited for the project to be finished so we can share it. The next steps for us include finishing that editing. We're looking for partnerships. We're excited to share it at film festivals and other types of institutional spaces. If you're interested in getting involved in this project, please come chat with me afterwards. And thank you so much.
Oh, that really warms your heart and potentially your arms and the rest of your torso. Sweater jokes. Quick announcement about unconferences. So today is like the big talk day. We're all in this big room, it's an auditorium, and you're gonna see talks. And tomorrow is a big workshop day, where there's lots of different workshops where people are building stuff. But what's gonna happen in this room? There are gonna be more talks, but none of this fancy rope, only elite talks. It's time for the community talks tomorrow, the unconference. You decide what happens here tomorrow. But how do you decide? You decide it by going near the registration desk, and there is a piece of paper with ideas on it. You can add new ideas to propose things to talk about tomorrow. You can also vote. Maybe you don't want ideas, but maybe you want to cast your vote on which ideas you really want to see that are already there. So go to that thing when you get a chance and vote on ideas for the unconference tomorrow. Cool. And then one of our next speakers, pop on up here. Okay. We are going to study negative pressure. We're going to talk about vacuums here. We're going to be slurping stuff up. Thanks to Thomas, Bolger, and Janos. Thomas, which one? There we go. Thomas crafts innovations at the intersection of product design, hardware, software, prototyping, and AI, with a focus on modularity, circularity, and usability. Over. OSEG and Alta Geisel there, guys, sorry, wants to build open hardware for everyday life, shopping trolleys, vacuum cleaners, household appliances. Whoever here has used a household appliance? There we go. You need them to be open. Bringing open source hardware into the hands of boring civilians. Who is boring? And finally, Ganos, who crafts innovations at the intersection of product design, hardware, software prototyping, and AI, with a focus on modularity, circularity, and usability. I'm going to let them take it away.
Thank you. Lovely.
Thanks. Hi there. Bringing open source hardware to the masses with a vacuum cleaner. What do we mean by that? Well, our starting point is our desire to bring open source hardware more into the mainstream of society, to have more people in the mainstream getting exposed to open source hardware, its benefits, its empowerment, and just think about the previous talk to get an idea what I'm talking about. And one of the ways to accomplish that is to make open source hardware more visible in public spaces. So all these things here are great conversation starters. The flip side of public spaces are private spaces, households. Here, similar idea. We would like to expose more people to open source hardware appliances, having them used on a daily basis. And such an appliance is a companion for life, actually, because you can mod it, you can upgrade it, you can repair it, of course. And well, but how to get from this fuzzy idea, this fuzzy sketch of a vacuum cleaner to version 1? We approached it, first of all, by pretending to be a startup. So we're not the real one, but we want to leverage the advantages that, let's say, entrepreneurial thinking brings, that entrepreneurial tools and techniques are bringing to the table. And we, for the project, we gave each other roles, or we have different hats on. And for example, I am the product owner, and that person suits me very well because it gives me dictatorial powers to enforce the project vision. And I'm also very gifted, it turns out, as DAB, being the dumbest assumable builder for testing purposes. So every startup needs a manifesto. This is actually also good for the product owner. It frames him. And this manifesto is entirely AI generated, but based on an involved set of questions that we answered for an entrepreneurial course. Günter Faltin, actually, he's also here in Berlin. We structured the project with weekly sprints, with soft goals. Soft goals because, well, hard facts in life get often in the way of open source hardware projects. Yeah, after a bunch of these iterations, I've been heard there was some cut work involved, there was some KiCad work involved. We had this here on the screen. And now we just had to instantiate it and have some fun with product photography and branding. But it's not only a fun exercise, we kind of also want to convince ourselves and you guys and the world that this can be a real product, that there are actually users out there in the world who would be willing to buy it, willing to build it. So let's take one step back and, well, fill in some more details.
Thanks so much. I'll walk you through the development process a bit further. So we basically went on to the topic with two sides, basically. One, we wanted to understand how commercial vacuums are being built, and then, of course, have a look at different form factors, maybe. But we also had a lot of ideas on what an open source alternative should and could be. So I'll walk you through some design principles we came up with. Modularity, of course, was on top of our heads right from the beginning, so we wanted to have different components that work individually without compromising the other if you change it, but also have the ability to extend the product. So if someone maybe wants to come up with a robot vacuum based on our product, he can do it. So we have screw terminals all over the product, electronics, which are really extensible. Thomas will talk about more on that. But yeah. Nuts and bolts, obviously, because we wanted to make it really accessible, let you guys open it up, and of course close it down as long as you want. And also have an industrial design that really reflects that and shows that you can open it right from the beginning. So we have screws really visible, and you can interchange all the modules on top pretty easily by just using M5 screws. One of the main things we wanted to accomplish is reusing all these broken vacuums you can find on eBay for really cheap. And you can easily salvage all the motors and motor brushes, for example, and reuse them in our vacuum. And the battery is actually one of the most environmentally harming pieces of most electronics, actually. So we use power tool batteries from different brands. We just happen to start with Parkside batteries because they're really cheap and accessible. But if you have some of your own at home, you can basically just replace the adapter and you're ready to go. And I actually did the ICA hotspot testing and did the calculation in our certificate, which I did last semester at La Fama. And you can see 85 kilograms equivalent is the most important thing, environmentally speaking. Regarding the design process, I actually started by just mocking it up with foam, and then also in parallel started sketching out some ideas. And that's basically how we went through our weeklies, Holger throwing in some ideas, we trying to think about how we implement them and structure it so we can have a well thought through product if you want. But one of the main questions we started scrambling right from the beginning is what exactly is the role of the core, which we wanted to be as universal as possible, and therefore we went on a lot of different iterations. Thought about maybe if we can implement the buttons right on the core, or if we wanted to have it in the handle, if we wanted to have the battery sort of in the core, or just plug onto it on the sides. And we came up with a pretty cool solution, I think, where you can have different parts right on the top with different HMI elements. For example, we have the PCB Thomas will show with LEDs right inside, but you can also attach a display or something like that. And we solved the button problem by exactly this solution. The cyclone, which we use for dust separation, which is, by the way, not the only solution we tried out. We also used the back variant, but eventually decided on the cyclone. Is pretty funny because we had an intern who sketched out the first iteration, and therefore we really get to understand how it works, but then later decided that we wanted to use a different approach where basically the dust gets axially through the vacuum and then turned tangentially for dust separation instead of the one you see here, because we wanted to have modules that can stack easily on top of each other, and therefore this approach wouldn't really work. That's sort of the evolution of our cyclone, which is not at all finished, by the way. And we use adapters all over the place. So you can, as I said, reuse components you find on eBay or maybe your old broken vacuum. We also support motor brushes right from the start, but also you can attach hoses, etc. So that's basically the design process on one slide, from sketch to product, if you will, with some iteration, obviously. But yeah, now Thomas, take it away.
Thank you so much. Hi, I'm Thomas. I'll tell you a little bit about the electronics that make that whole thing work.
So the first step, obviously, we tried to get to a very quick proof of concept. So the first question we had, what kind of vacuum motor do we use? And actually on the European market, there is not that much, but luckily there is AliExpress for all that niche stuff that you can't find anywhere else. And so the main choice at the beginning was, should we go brushed or brushless? And if you look at brushed motors, they're a bit more heavy, they're bigger, they wear out over time, kind of lame, a bit old. And so we went for brushless. They're super high RPM, they're fun, they're small, way more efficient, and also very common and cheap. And they have an integrated speed controller. So what we did first was just order a few of those, try to get them to work with like 0 documentation, which did work. And now we had a really loud motor without a housing. But we had the question, like, is it any good and how do you even measure that? So if you dive into that topic, you'll find air watts, where even Dyson says that that's the unit that we should use. And it's basically a formula where you put in negative pressure and airflow, and what you get out of it is a value that somehow correlates more with everyday use. So we needed something to obtain these measurements. So it looks a bit like a gun from Halo, but it's actually our test bench, which means we can use it, plug in the motor, get negative pressure values and also airflow. And if we use that now with the formula, we get some results, which I won't go into detail with, but in short, some of the €4 AliExpress motors actually outperformed most of the vacuums we bought for testing and for comparison. So at this point, we're good and went to build a system. So a vacuum is not just turning off and on a motor. We also wanted to control the RPM, which you can see on this picture. That was the first try. The motors luckily use PWM. So with their integrated speed controller, that worked pretty well. And so we started to plan our PCB and got some requirements. So we wanted to use these PWM motors, control the speed. We wanted to read back the RPM signals, like the actual RPM, include the power tool batteries, some connectivity, safety features, and also some just cool things like buttons, RGB LEDs, maybe a display. And at this point, we just got to work, built a PCB, which got a bit smaller than initially planned, which didn't really make it less complex. But soon enough, we had it ordered and did all the picking, placing, soldering by hand, and had our first version, which you can see right here. So I'll give you a really quick rundown on what it is and what it does. So we are almost the size of a credit card, with the goal that it just can fit anywhere, whatever vacuum you're building. And even if it does not fit, you can just break it apart and rearrange it in some way so that your trigger button can actually be in the handle or somewhere else. And then you can just reattach it using the pads on the back. So it's also expandable, because like the philosophy we had is we use up all the GPIO pins that you really need for the function and then expose all the rest and all the protocols with UART, I2C, SPI, you name it. So you can just be super flexible and build your own version of this whole thing. So the firmware is really, really work in progress, but it also follows the same vision as the whole thing about modularity that Janos just proposed. So in the core, it does some basic things. It does some safety stuff. It has a kill switch. It does some battery management, like cutting off at under voltage. And on top of that, there sit firmware modules that you can just like replace and change out. So if you want to use an LED bar or a display or another one of the few popular OLED displays that we already wrote modules for, you can use different motors or just develop your own modules, which could be a sensor, some actor, or something else that you just like. So here, for example, if you want to see from far away what's going on, this LED bar is quite handy. Or if you want to use an OLED display for some insights or deeper insights, or even deeper insights, you can go for this. Or you can basically do full configuration. If you have a pre-flash board, you can select your motor, your whatever HMI you have attached, and you don't even need to touch your computer to set this whole thing up. So you can also use the web interface, of course, so Vacuum meets that to define everything. And you can also use that interface to self-calibrate motors and batteries. Yeah, so that's Casney, but I get one little bonus more.
Because to be even more flexible, we also wanted to look at proprietary hardware because that's quite interesting. If you look at one of those, which is like one of the standard vacuums, you usually have a motor, you have a trigger, you have a lot of plastic, and you have a battery that sits at the bottom, which actually is not really a battery, it's actually the whole vacuum cleaner. Because if you look at it in detail, it has like 25 pins because the trigger is directly wired into the battery, just like display, and the motor, which basically means it's the main board, which makes the battery expensive as the whole vacuum cleaner usually. And it's usually also the first thing to break, which is interesting for us because that means that you can get a broken Dyson with a broken battery on eBay for 15 or 20 euros, and you'll get a lot of adapters, a lot of parts, a really powerful, optimized, safe motor, but it uses UART and not PWM because it has a lot of more sensors. It uses a proprietary protocol, which we reverse engineered and put it into a module, so we can basically revive all of these broken vacuum cleaners on eBay. And yep.
Let's get a bit more to the boring parts, documentation, or write the bleeping manual. Nadia in the previous summit talk made the point that if you have a detailed BOM, that goes a long way towards replicating a project. So here are just a few highlights what we did with the BOM. We decided on having telling names for each part of the project. These names are, let's say, semi-hierarchical and use some tagging. So the idea is hopefully if you have a rough idea of the project and if you read a part name, it should give you a rough idea what this part is about and how it relates to the project. A bit of color coding for the different part types. We have a gallery view of the printed parts. That is nice to judge the complexity of the part and how it's oriented on the build plate. If you hover over a part, you see the part name we just discussed about. So on the right, you see a lid insert, and to the left, that part is called lid. So that gives you already some hints how these fit together. Also, the build plate can double as a visual BOM, gives you a feeling how many parts are involved and how they relate in sizes. And well, remember we have this guy in the team, the DAB, the dumbest assumable builder, and with that guy we determined that the BOM is not quite sufficient. So what Janos did, he came up with a build video, how to assemble the vacuum in first-person perspective, so FPV if you want. And this video turns out is actually quite, say, immersive and quite fun to watch. How did he do it? Easy. So we also started to make timestamps with the build video, and again here the names show up, so you could search, for example, for a part and then see where it's assembled in the build video. So far still documentation is more on the unstructured ad hoc side, and we are hoping for AI for the rescue. There is also the bill of tools, which we believe is also important for you to judge, obviously, what tools you need, what skills you need with these tools, how expensive the tools are. And for the printed parts, for example, or for the printer, we made sure that it also is workable on smaller printers. So these are the build plates of a Prusa Mini. Yeah, thanks for everybody who got us to version 1. And we already have plenty of ideas for version 2, and hopefully so have you. So please contribute, and maybe you find something that interests you. Since it's relatively modular, so you can, for example, work in isolation, let's say, on the PCB, or on including a new battery or an improved cyclone. With sensors and diagnostics, we haven't even really started, I would say. There's a lot of potential there. And yeah, please just visit us, look us up on our table, and get some hands-on experience of the vacuum. And yeah, thanks a lot for watching.
Awesome. Recurring theme, I think we'll see continuing. But I really like the quote from Carrie and Daniel's talk earlier. There was people were like, the Baroque is finding God in the garbage. And I love going through broken stuff and finding stuff, which is also the theme of our next talk with Allison. It's going to be about circuit necromancy. Allison Clark is a Toronto-based media artist exploring human-machine relationships through interactive installations and custom-built electronic instruments. She works at the studio at InterAccess, an artist-run gallery and makerspace, supporting experimental practices in art, sound, and technology. Take it away.
Wow. Yeah, thank you so much. This is my first Open Harbor Summit I've been to, let alone talked at. It's been so great. Getting familiar with all of you and getting familiar with the summit. So I'm here to present my talk entitled Circuit Necromancy, an Introduction to Electrical Salvage. Electrical salvage is a big part of my process. I learned electronics through taking apart old pieces of equipment. It's been a big part of my journey with electronics. And I also think electrical salvage is really valuable for combating this perception of electronics as black boxes, that especially maybe not, this room may not feel this way, but definitely the public feels this way, that a device is either working or not working, and there's no gray area there. If it's not working, then it often ends up in the garbage. When in actuality, a component might be not working, but there could be so many other treasures existing within these devices. So a little bit about me. I'm a media artist and arts technician based in Toronto. My electronics background is from that arts background. I work a lot in like audio circuits. I make instruments that I perform with on stage. And I also make interactive installations. So a lot of my electrical knowledge is self-taught. I don't have an electrical engineering degree, but I think through this practice of electrical salvage, I've been able to gain a lot of that knowledge. So I wanted to start by walking through some of the projects that I've taken on that use electrical salvage. This first piece, I finished in 2023, and it's entitled Echo Machines. And I'll speed through these projects. There's a link at the end of this talk where you can view video documentation of all of them. But I'll just highlight how I use electrical salvage in each of these. So the salvage in this piece is two codec carousel slide conductors, where I disassembled, dissected the remote controls, and then connected those controls to relays, and those relays to an Arduino brain, so that I was able to write code to speed up and slow down these slide projectors. I was interested in using these machines to replicate a human conversation, so they kind of take turns exchanging ideas through the pictures that they present. This next piece is called Temporal Landline. The first iteration of it was also completed in 2023. It is an ongoing piece. I'm still kind of thinking through it, seeing where it will eventually end up, but it's a second-hand rotary telephone that I replaced. I basically gutted it and replaced all the internals with an Arduino Nano and one of those like MP3 player with hobbyist boards. And it works in that if you dial a number, like say your home phone number, then put the headset to your ear, you'll hear an auditory memory. I collected a whole bunch of people's responses to what was like the most vivid sound from their childhood, and then either sampled those sounds or created them through like synthesis, and then put them all in this headset. So when you dial a number, you get your own unique memory that you're hearing. I really loved, this is like the first project where I fell in love with the idea of opening up these old machines. Like the way that a rotary telephone works is you dial back to the number 7 and then let go, and it makes and breaks the connection on the inside 7 times. So it's a really simple device, but you can do so much with it. And there's so much beauty in that simplicity. And then this is a current work in progress. I actually brought it with me to Berlin, so if you're interested in hearing it, it's here. It is a portable custom synthesizer where all of the controls are components that I salvaged from a broken down mixing console. These controls are connected to a Electrosmith Phase EC, which is like a audio microprocessor, I guess. I would really wanted a way, I write a lot of like audio code, create my own synthesizers, and I wanted a way to put that code on a portable platform. So this was my way of doing that. And I love the faders on like audio mixers. If you're interested, you can definitely come up and see how they feel. They feel great. And I really wanted a synthesizer that had those faders, so it was really liberating finding those components in the wild and then blending them using them in my own design. So some stuff to know before starting if you're completely unfamiliar with electrical salvage. It can be, excuse me, it can definitely be a difficult process. It isn't the best introduction to electronics, although I do think it's a great accompaniment to a practice in electronics. Part of that difficulty comes from if you end up using these components in a later project, it can be really annoying not knowing if there's a bug in your code or something wrong with your circuit, or if someone just ruined the components decades ago by spilling beer on it or smoking heavily in that room. And then there's also some potential dangers, so like chemical hazards, similar to all electronics, you can potentially expose yourself to lead. Some of these really old machines use asbestos as like a heat dissipation or to limit fires, I guess. There's sharp parts potentially, and there's some thin shreds. And then there's obviously one major issue with opening up old pieces of hardware. There's electrical dangers. No one is allowed to shock themselves after listening to this talk, please. This talk is just an introduction to get you interested in the practice. It's not a comprehensive how-to. There's definitely devices that even I feel uncomfortable opening up, stuff like microwaves, of course, CRT televisions. Sometimes you're working with voltages way above what exists within your wall, which we all already know to be scared of. So yeah, there are some dangers, but there's also ways to know when you're working within those dangers, within, I guess outside of those dangers, within safety. You can always check what voltages you're going to be working with. It's always easier to work with devices that aren't running off of AC voltage, where the power supply is outside of the device. I'm sure we've all seen these like oblique black boxes that connect to our electronics. Those usually have voltage information, so you can tell what kind of voltage is coming out of those devices. But sometimes even if that voltage is quite low, that doesn't necessarily mean safety, because you might open it up and you might discover something like this. These are some high voltage capacitors that I have found opening up electronics. Large capacitors like this, if you're unaware, can act like a balloon, and you can use a small spout of like maybe 12 volts DC to fill up a 450 volt capacitor. There are ways to discharge these capacitors. I won't really get into how to do that in this talk, but just know, even if you look at the ratings and you'll say, if you open the device up and see one of these, it's a sign that you need to be careful of that. So, if that didn't scare you away, which I really hope it didn't, there's a lot of different places where you can source these old or decommissioned electronics. There's like creative reuse depots or electronics reuse depots. There's maker and hacker spaces often have e-waste bins or e-waste shelves where members of these spaces would bring their old electronics for you to use. You can of course buy these devices at thrift, charity, and antique shops. One of the benefits, or I guess downsides of a practice of electrical salvage is just because a device that you find is said that it's not working, that doesn't mean you don't have a use for it. So you can usually get stuff for very cheap. The downside of that is, of course, if you go into one of these shops, you now have one less excuse for walking away without buying anything. And then the last and most valuable, I think, source for these decommissioned electronics is your friends and family, collecting from your immediate circles. This is also a little bit of a double-edged sword, because as soon as you start telling people that you will take their old electronics, you will end up with a lot of old electronics. So once you found something, the next step, I guess this is what electrical salvage actually looks like. You need to open up these devices. The manufacturers don't often want you opening up these devices, so they use stuff like a whole lot of screws, sometimes 30, 40 screws. And they also love to use multiple different sizes and types of screws to put these things together. So make sure that you come with a whole bunch of different screwdrivers, make sure that you take photos of each step of this assembly. And you might want to think about having a tray for all of these different screws or different reservoirs. This is often the most time-consuming step of electrical salvage, especially if you're going to be putting it back together again, so it's good to be prepared for that. Once you're inside, you're shown this really beautiful landscape. I love looking at these commercial PCBs and being able to figure out what is going on the inside and work backwards. Especially some of these older devices have really interesting mechanisms. This picture on the left here is a rotary switch from I believe, early 1980s telephone line tester. And the rotary switch literally just means a wiper to switch between a bunch of full-size resistors. So once you're inside of these devices, what are you actually looking for? You can, of course, find all the basic components, anything that you would use in an electrical project, you can probably find in some commercial device somewhere. There's some special things that you might want to look for, like diodes that use older technology that's maybe desirable for audio circuits, stuff like germanium diodes, same thing for transistors, and then of course there's beautiful vacuum tubes in these devices sometimes. But what I would actually recommend that you look for, though, especially if you're new to a practice of electrical salvage, is these interface components. That's stuff like faders, knobs, switches, buttons. These are all, I think, these are the most rewarding thing that you can pull from these old devices. They're essentially all either variable resistors or electrical switches. They're quite interchangeable, and they're really easy to connect to modern microcontrollers, microprocessors, that kind of thing. So like Arduino, ESP32, or the electrosmith easy that I showed you at the beginning. So once you've found that component that you would like to use in a project, now you need to desolder that component. Desoldering is one of those things that you learn through doing. It's basically soldering, but in reverse. Some of the tips that I would give you are to add new flux or possibly leaded solder to loosen the old solder. Solder that's been sitting for a long time kind of starts to calcify, I guess, or harden, and it can be hard to work with. So I find adding leaded solder reduces that melting temperature, especially if you're working with devices using unleaded solder. And then after you've turned that solder molten, you're using something like a solder sucker, which you can see in the bottom right here, to suck up all that molten solder. And once you've removed most of the solder around the device, you can usually just pry it out. Once you have a component out of your device, Next step would be cleaning and testing. There's usually a ton of dust and dirt and grime in these machines. Like I said, sometimes someone spilled something inside of them. Sometimes there's like nicotine residue. Clean up most stuff with isopropyl alcohol and Q-tips. For really finicky parts like faders or potentiometers with grime on the inside, you can use a product called deoxyc F5, which is really great for cleaning these moving parts. You just spray a very small amount inside of a component and then twist the knob or the fader. There's an equivalent product called deoxyc D5, which is similar for like buttons and switches. And then once you're done once you're done cleaning, you can move on to testing the components. Yeah, with a multimeter. Yeah, I guess why are we doing this? Why are we doing electrical salvage rather than electrical repair? I think one of the most clear answers is electrical salvage is electrical repair. Every single step that we just went through with electrical salvage, you would just then at the very end, say you were removing a bad capacitor, you would be desoldering that bad capacitor and then replacing it with a good capacitor at the end. There's also a case where a lot of devices are either archaic, like that rotary telephone, which you just couldn't use in its original purpose anymore, or they're just beyond repair, they're so damaged, like someone has spilled something in them. And so salvage is often the best end of life, I guess, for that device, or secondary life. Yeah, and part of that is also a big part of repair is sourcing these rare or archaic components, so stuff like vacuum tubes, rare transistors, and you often need a new donor device to be able to source these rare components to let into something that's closer to working. And why salvage in particular? I mean, it's fun. It's really amazing opening up these devices that maybe haven't been opened in decades and decades and seeing what was on the inside. I think you can learn so much from how electrical devices have been constructed through the decades. There's so many methods that we used early on in electrical history that we don't really use anymore that maybe have some kind of new use case in our modern age. It's also a tried and tested way for people to learn electronics. I mean, how many people's stories, especially before the year 2000, how many people's stories of learning electronics involves taking apart old radios or, just the devices that they come upon in their life, and disassembling these machines to figure out how they work. I think it's such a natural part of the human brain to figure out how the world around us functions. And I think also, maybe the most important thing for me is that the practice of electrical salvage changes these devices that are maybe at the end of their life or their originally intended life. It changes them from being a waste product and it turns them into something new. It becomes a resource, it becomes a site for inspiration, for learning. They're no longer something to be disposed of, they're something to be appreciated. And I think that that's a really valuable change in thinking. Yeah. That's my talk. Thank you. I have a video documentation on my website. So those first three pieces that I ran through, they all have some kind of moving or sound components. You can view that documentation on there. I'll also post this link in the Discord. Yeah, thank you.
Cool. Thank you very much. So, let's give it up for Alison. Sounds so cool. Okay, there are 2 more talks until lunch. I want you to do a little stretch break. I want everybody to stand up. Everybody stand up, yeah. And the reason I want you to stand up is I'm doing another poll, okay? If you can, you're going to show me the answers to my response by jogging. We're all going to jog, okay? So, everybody start jogging, and you can stop when this no longer applies to you, okay? So everybody, let's get going. Get the heart rate up. Come on, people. This is Open Hunger Summit 2026. Okay, who here, if you have made an open source hardware thing, keep jogging. Keep jogging. If you made a thing, you make one thing. Who here's made at least two things in the audience? If you haven't, sit down. You're out of the race. You're out of the race. Keep jogging. You make more than three things. Keep jogging. Keep jogging. Okay. Okay. What have you made? 5 things? Have you ever made 5 open source hardware things? Remember, this is anything that's made out of atoms. That is replicable for other people. So keep jogging, keep jogging. This is 5 more, people. We're dropping out. Okay, what about 10 or more? If you make more than 10, keep jogging. Okay, we got people. Oh, William dropped out? I think you make more than 10 things. You keep jogging, William. You have 30 things in your workshop. You keep jogging. Okay, if you make more than 30 things, keep jogging. If you made more than 100 things, keep jogging. If you made more than 200 things, keep jogging. Okay, this is the high knees round. If you made more than 300 things, keep jogging. High knees. Okay, if you made more than 1,000 things, keep jogging. So I'm sitting down. Keep jogging. If you made more than 10,000 things, keep jogging. So we still have people. If you make more than 30,000 things, keep jogging. We still have a runner. We still have a runner. If you have made more than 50,000 things, about 50,000, and that's the same as our next speaker. Please come out for a round of applause to the winner of the open race. Our next speaker is Akar. He is the founder and CEO of Air Gradient, an impact-focused company building open-source air quality monitors and data tools based in Thailand. He champions the intros are a little harder than I read. Based in Thailand, he champions open hardware, open data, and community-led innovation to expand access to reliable air monitoring. His work supports schools, cities, and NGOs worldwide. And I've noticed he's not still jogging. I think, yeah, okay, you need to keep jogging, because this talk is about making 50,000 things.
Take it away.
So let's see if I can still hold my speech after being a bit out of breath here. Great to see. I have to talk to the guy with the 50,000 and we do exact counting after the presentation to see where we are. I think 8-9 years ago, I went on a sabbatical. I was working in Bangkok in Thailand, and I didn't want my kids to call me uncle, so we moved to northern Thailand, and there's a great school. So I got active at the school, did some Arduino classes, all kinds of stuff. And then this happened. So this was a picture I took in 2019 from the terrace of my house. And at that time I learned that actually in northern Thailand we have 5 seasons, not 4. And the 5th season is called burning season. So it's a recurring thing that happens every March, April. And you see it's 320 micrograms per cubic meter, PM2.5. Just to give you an idea, the World Health Organization recommends 5 micrograms limit. Okay, so you can do the calculation. So it means people, hospitals full of people, just a massive health hazard. So the school at that time didn't know, do the air purifiers work well enough in the classrooms? Is it safe at school or at home? And I was parents president, so I was kind of sandwiched between a head of school that said, I have very strong lungs, but I don't know about my kids. So we sprang into action, and we said, okay, let's do something. You know, we cannot change the environment, we cannot change the outside air, at least not that quickly. So let's build something. So we started building air monitors for students here on the left side. We used some old plastic bottles as enclosures. I started building actually air purifiers with the school, so also need to talk to the vacuum cleaners because it's just the opposite way to use that. And then we also looked at what are the underlying causes. So we invited a couple of high school students from the most affected areas to the school, did workshops on advocacy, on how you protect your health. We had firefighters coming in and teaching them actually talking about their work, how they extinguish fires and so on. So we then just continued developing these sensors. We put them out on the internet as build instructions. We didn't even call it open source at that time. We called it DIY air quality monitor. We built a simple dashboard based on the Arduino ecosystem. So we made a nice Arduino library, just super easy to use. And then something interesting happened that a lot of schools contacted me and said, hey, we want to build this. Can you help us? I said, sure. So we did a couple of workshops with students, with teachers, with parents, and then I got calls from Bangkok. I thought, okay, interesting, let's help them. And I got calls from China, and I thought, okay, that's really interesting, because China has this long history of combating air pollution, that they still felt, okay, there's something interesting around doing something together as an educational approach. At the same time, I think a lot of you guys probably know Hacker News, so I also wanted to promote this kind of toolkit. So I said, everybody hey, send me a few dollars hostage fees. I sent a PCB from Thailand. So I started doing this, and I think I sent a couple of hundred PCBs out, and one of them got to Jeff Gerling, which some of you might know. So he's a really big YouTuber, and he got one. I didn't even know, but I saw that our website broke down at some point when he published the video. So he got this out, and then he started thinking, because I didn't really want to go back to my old job. I felt, hey, I can have a lot more impact. And actually, I have a co-founder, Nick. He was doing this stuff with me at the same time, and I thought, okay, can we actually build something around this that supports that mission? Okay, and so fast forward today, I think we were quite successful finding that missing piece, and that's something I want to talk today about it. And I think we had it in the first talk today, how can you actually scale up or make an open source hardware project sustainable. So today I'm here actually with 3 of our team members from Gradient, Anastasio and Emilia and Mariana, and we have around 30 people in the company now. We have a huge communication outreach team, a big science team, engineering operations. I'm always joking, I'm the only one who's doing sales. There's no sales rep, all this kind of stuff for the other, we just don't have it. Okay. And I will dig a little bit deeper into how this works, but that's the team I want to introduce. So all our monitors are open source hardware, all. There's nothing proprietary that we do. We have 2 of them already certified. We have 2 newer ones which will be certified soon. We have everything on our website. So there are the KeyCat files with the BOM, the enclosure step files, everything you need. You can just download. You don't need to register. And we do it under CC BY SA license, because we think it's important that the attribution is there, and that like any improvements remain open. But we allow commercial use, so like anybody can take the whole thing, like massively produce it, sell it, totally fine. It's actually welcomed, because we think air pollution is such a big problem, like not a single company can actually solve this. So what's the next question that I'm getting asked now with most people?
How do you make money?
Yeah. Thank you. Okay, so that's exactly the question. I think it's a very interesting question, and I think that's where like a lot of the people that do open source hardware needs to get a little bit creative. Okay, obviously the design is open. Okay, but there are a lot of things you can actually do to build a business around it, and the way it works for you, for us, is basically, well, it's actually quite easy. We sell the same stuff. Okay? And because we sold like 50,000 monitors so far, we get those purchase prices. You know, we talk directly to the factories. You won't believe how much cheaper things get if you move away from DigiKey or mouse. Okay, we talk about factors here. Okay, so we can actually create the monitors at very, very affordable prices. And we also said we actually want to sell them as kits. Okay, so if you sell something as kits, you don't have to do warranty. Okay, because it's not a finished product, so you can take these warranty costs out and basically cover it with the price. But there are a couple of other things we actually do, and I think this is a really important one. Like, you need to trust the air monitor, obviously. And so we have our own test channel. We have a very expensive reference instruments now. They cost like $30,000. And every single unit that we produce gets a test report and gets additional calibration factors. So it's open source, but we can basically fine-tune them. The test report is open, all our algorithms is open. But obviously, that's something we can give in addition to the monitor. And that's what a lot of customers actually value. I think what's also, what we often see, which I didn't put on here, is that obviously a lot of people want to just support us. You know, they see what we do, they have a choice between a proprietary and open source solution, and they just say, okay, let's go for the open source because we want to see more of that happening. So that's a bit the history. I think it's really important that people understand like where we come from, because I think that's really kind of determining your path forward. So now I want to go through a couple of things that I call it the open source advantage. But word of caution, I'm talking about this from a manufacturing perspective. So I'm not going to talk about repairability, okay? I'm not going to talk about like extensibility or hackability or reverse engineering, what you can do with your own stuff, okay? I really want to approach this from a manufacturing perspective. What can you do if you design your open source hardware product to make it successful in the end? So number one, I think a key thing that's kind of obvious, but I think still often overlooked, is open source hardware accelerates innovation. Okay, and I will give a couple of examples here. So these are just a list of open source volunteer contributions we got from the community. We just got it for free. You know, like just people did something, and because the firm is open, the product is open, it's very, very easy to do this. And I have actually a funny example here. Some of you might know OMI, it's a smart home system. And some of the people that have OMI, they ask us, hey, like, can you make an integration? We want to use it. And then my co-founder, Nick, looked into it and said, hey, look, this is Python. I don't know much about Python. And anyway, I'm going on holidays tomorrow. Like, let's talk about after my holiday. Okay? So I thought, well, yeah, but let's try it a little bit different. So on July 13th, I posted in the HOMI community forum and said, hey, like, anybody wants to help us doing this? And then 4 developers came back and said, yeah, why not? So I talked to them, and I thought, okay, 2 of them are pretty good. I sent DHL Express a couple of devices to them. They started doing their stuff. Like a week later, no, actually 2 weeks, but before my co-founder came back, this thing was published on the Omni App Store. Okay, and I think that's a great example how the community can really help you innovate and implement these kind of innovations basically in the end. Now, a new thing that's really interesting now is this agentic coding. So I played around a little bit, and you can see this device on our booth, is that agentic coding and an open firmware can actually create super interesting community innovations. And I gave an example. So I said, hey, Claude, add an e-reader to the air gradient Go, which is our portable air quality monitor. And 30 minutes later, I was reading Alice in Wonderland. Okay? It was just worked great. Another example was Tetris. Okay? Also working great. It crashes after a couple of minutes, but never mind. I think it's a great proof of concept. And what I want to say here is that if we allow these open source firmwares, the community can try out so many things. And then we can see what actually picks up steam. And we can, talk to the community and maybe integrate some of these features into our own products. Okay? And I think that's really interesting now going forward, because firmware in the past was a very, very difficult thing to do. You need the tool chain, the documentation was often very bad, and so on. I think that's what agentic coding can. I'm probably planning an additional talk on that. I think it's a super interesting thing. Now, number 2, open source hardware advantage. Open's powerful advantages. That wasn't something that we didn't have on the radar at all. Okay, but last year we got 2 projects from the United Nations. One with UNDP in Singapore that wanted to develop an open source air quality monitoring toolkit, which is capacity building, and they were just looking for a company that's just open, that just shares their knowledge. So we got, even as a relative newcomer into the industry, we had an advantage by being open with a UN organization. And that was like something new. Also a lot of partnerships with universities, because they know everything they tell us remains open. I'm not signing any NDAs. I don't demand any NDAs. I think NDAs are bullshit, if you ask me. So yeah. Now, another really cool project we did with UNICEF. They have a really super strong data science team based in Stockholm at the Office of Innovation. And they wanted to do better air quality monitoring in Laos. It's a neighboring country from Thailand. And they were just looking explicitly for open source solutions to feed their data model, basically. And that's why we just automatically had a huge advantage by being open source. Now, number 3, open source hardware, I think, just builds a much better community. I think, maybe even the only way to build a real strong community is with open source. And one of the key things is, we can talk about everything. Like a lot of proprietary hardware providers, they don't want to tell you exactly what sensors they use or what's going on in their devices, what shortcuts they took, whatever, and we are super open, and that's actually makes our blog super interesting. So we have 4 or 5 people from our team writing about our blog. We write about everything. Also here, like the one on the right, where we flew down the air gradient Go from the 3rd floor, and obviously it broke. Nobody else probably wants to show you a broken device and so on. But in the end, it builds trust, because people know, okay, we take this serious. We might not be able to fix everything immediately, but at least, okay, we can talk about it. And then we do a lot of science thing. We have also strong opinions about open data and so on. So we can just address all these things. And that's interesting content, and interesting content gives you traffic, free traffic, okay? Our forum is the same thing. We have a Discord forum, and we have just a lot of visitors there that discuss all kinds of things. So I think what's also fun with open source hardware it really increases accessibility and maximizes impact. And I want to talk a bit about price. Okay, so I mentioned before we don't have a sales team. We get pretty much free traffic. We don't do any paid advertisements, nothing. You will not see anything with us on like Google AdWords or anything like this, but we are very, very good ranked if you just search for open source hardware, aircoin monitor, and so on. So that obviously, often actually, if I look at our competitors, 30% of their staff is their sales team. Now they have to factor that cost into the product, which we don't have to do. So this way we can, together with the, let's say, the supplier price advantages, we can have a lower cost than the competitors. So, and that obviously then gives you an advantage in your sales. No? What's also important here is you need to design your products to be efficient, and I come to that at the end, obviously. And often we have over-engineered products that might make that a little bit more difficult. Capacity building is super important. We are based in Thailand. It's an area very affected by air pollution, with a lot less financial means than in the more developed world. So we run a lot of workshops all around the world, where we actually take our kids and just teach people to build their own aircoin monitors. And we want people to actually do this. There are so many countries we cannot really reach, and we want them to be able to do that. This is really interesting, I think, because anytime somebody could fork out GitHub repo, produce the whole thing, we always need to be competitive. We need to be innovative. We cannot just stop and count the money or something like this. So I put it this way: like we always need to be better than the cloners in regards to our cost position and innovation. And I think that's a very, very positive thing. It's something that just makes you going further and further and further. So wrapping this up a little bit, why did it work for us? I guess you can already make your own opinion a little bit, but I think what's super important, any model you run, try to be 100% authentic. Don't compromise. There was a 4 weeks time where we had a license not to allow commercial use. And after 4 weeks, I thought, okay, let's just go full in. And I said to my business partner, Nick, this is either the dumbest or the smartest decision in the life of Agrarian. And I think so far it turned out to be a good one. We are totally bootstrapped. We don't have any venture capital. We are self-funded. You can start now with hardware actually, even if you don't have too much money. I think there are a lot of possibilities. I think with venture capital it would have been a lot more difficult to go that path. Also, like when I make a decision on what we should do, I always have two things in mind. One is, does that decision maximize the impact? Can we get more transparency in aircoin monitoring? And the second one, do we not go bankrupt by doing this? Okay. So interestingly, most of these decisions turned out to be also profitable ones. Okay, just by maximizing impact. We never had a business plan, but just maximizing where can we have the biggest impact led, in my opinion, to some of the best decisions. And last one, I mentioned it earlier too, you have to make sure you have efficient processes. Like we went from our last generation of the aircoin monitor that you can see on our booth had actually 30% less components and achieved the same thing. And we looked at like how can we optimize production, how can we have everything on one side of the PCB and so on. And because in the end, every dollar counts. Because if you have done 10, 20 things, then okay, you come to a level where you can really like play around with the whole thing. Great. One more thing, there's in the goodie bag, there's a PCB, and this was us and our team sitting here yesterday at the kitchen table, taping this stuff together. So build your own monitors, contact us if you have any problems. You still have to buy the expensive stuff, so we couldn't afford that. But it will be a great project to do this. With that, thanks a lot. We have a table over there, and yeah, if you have any questions, just stop by.
one more talk coming up before the lunch break. We have Nathan. Perfect. Nathan has spent the past decade working on problems at the intersection of open source hardware, disaster response, and supply chain logistics. A former welder, electrician, and installation artist, he is a contributor to Make Magazine, co-founded the Internet of Production Alliance, and spent most of 2020 coordinating open source medical supply projects across several major communities with helpful engineering. I'm going to give it to Nathan to take it away. Thank you.
So, who here remembers 2020? I know most of us are trying to block out. Specifically, in 2020, the supply chain shattered, and across much of the world, you couldn't get medical supplies for love or money, because our supply chain is optimized for efficiency, not resilience. And what happened, especially amongst the maker and open hardware community, was inspiring. It was really amazing. It was something I spent a lot of time in. I imagine a lot of folks in this room were involved in some way or another. This is a very brief list, but a lot of folks came together trying to solve this problem, creating open source medical supplies, PPE, etc. One such organization, opensourcemedicalsupplies.org, claimed responsibility for around 16 million as of, say, mid-2022. Globally, I think the number is closer to 48 million. There's some really inspiring things that happened. But also, it was kind of a mess. All right, really quick. Everyone put up your hands if you feel like you personally learned valuable lessons from the COVID response that are going to change how you deal with the next disaster that comes. Put your hand up and leave it up. Okay, now keep it up if you feel like your community also learned these lessons. Okay, keep them up if you feel like your government learned these lessons. That's what I thought. So the thing is that there's no version of the next 50 years that gets any easier. There's no reason to believe that we are any better prepared for the next crisis. The future is going to be a series of disasters filmed through phone cameras, and the point of view gets closer and closer until we're the ones filming it. And, given what's happening with hantavirus, the next disaster could be any day now. So how do we take what we have learned and actually be better prepared for the future? The thing is, the response was not something that makes the maker community or engineers or hardware nerds special. This is a human thing. This is a mammal thing. Rebecca Solnit wrote a wonderful book, which I recommend, documenting how in crisis people come together. It is what people do. When the official channels fail and the government falls apart and people are left to their own devices, they come together and they help each other. It is what we do. This is what Kropotkin wrote about, and properly read, this is also Darwin's thesis, that mutual aid is not a form of idealism, it is a survival mechanism. It is what species that survive do. So, how can we learn from this? When I was there trying to run around and coordinate these open hardware responses, trying to get the open hardware PPE and ventilator designs to places that could build them, distributed to places that needed them, I watched the wheel reinvented over and over and over again. I watched people burning out, spending 70% of their time and energy and volunteer man hours manually solving simple coordination problems. I saw people doing things because it was easier to start a new prototype that got halfway to being useful than it was to find an existing design and improve on it. And especially when it came to the context of medical devices, anything more complicated than PPE has to be safe. It has to be tested, otherwise you could hurt someone. There was a lot of people, especially in labs and universities, who got very excited about making open source ventilators. So there's a huge shortage of. And very, very few of these made it into production or use, and frankly, that's for the best. Most of these would have killed people, frankly. They'd overinflate someone's lungs, and then great, you've not died of COVID, you've died of your hardware. There were some good designs out there, but how do you find them? How do you know that the version that you have is useful? These are the problems that kept me up, and these are the problems that I spent most of 2021 yelling about to anyone who would listen. So there are underlying problems that I can't fix. I don't know how to fix the supply chain. I don't know how to fix the social and political realities that created that crisis in the first place. But there is a specific set of problems that we can solve. So, with universal open hardware data standards, we can solve discoverability, we can solve portability. It allows us to start doing things like automating design to facility manufacturing, automates discovery and sync. It allows you to lock versions and say, this specific version of this specific design is actually safe to use. More than safe, you get the idea. A lot of these are problems that are very well solved in open source software and are very, very difficult to solve in open hardware. If you are already operating inside a closed, vertically integrated ecosystem running on SAP, running on any of these big supply chain management systems, this is trivial. It's already solved for you. But these are the systems that broke. These are the systems that failed us. The open hardware ecosystem is the opposite of this, and as you are all very well aware, the extreme heterogeneity and openness and flexibility is also what makes it nearly impossible to coordinate anything at scale. So what can we do about this coordination infrastructure? Obviously, I'm not working on this alone. I felt it's important to acknowledge that there's a lot of people working on this at various points. Many of them are here. There's a lot of moving parts to this. I'm specifically trying to solve a narrow but critical slice of it. But obviously, this is an open problem, and a lot of people are coming together on it. So the thing that I am here specifically to talk about is an open source tool that I have been building in collaboration with Helpful Engineering, a group I helped start during COVID, called Open Hardware Memory. It is primarily solving this core problem of, given an open hardware design, how do I find places that are capable of producing it? This is, again, the thing that I saw about 70% of volunteer man hours in COVID burned trying to solve in ways that were, lost entirely to time. Everyone who built systems to solve this during COVID created spreadsheets that no longer exist. There's no infrastructure, and so this is what I'm trying to solve here. This is on a technical level, this is a fast API server, runs in a Docker container that you can interact with very easily. You can run it on very simple hardware. It is built primarily on these two open data standards. So open know-how is a way of representing all of the information required to produce any given hardware object. And open nowhere is a way of representing what is a given facility capable of doing. And so this, again, these are things that are trivial in closed ecosystems, but the ambiguity of how people build these systems and how they run their facilities and the fuzziness at those edges is where this gets complicated. I don't have time. I was hoping to do an actual tech demo, but since I can't plug in my laptop, I'm just gonna have to describe it. But at the heart of it, the thing that this does is it says, okay, we have information about what a product needs. We can infer, if the design files contain STLs, we know that the process requirements include 3D printing. If it has a DXF, we can assume that it requires laser cutting, et cetera, et cetera. So you have to do a lot of inference. The whole system is built on a sort of a 4-layer pipeline that says, okay, first we do direct matching, string comparison, one-to-one, looking for matches. That's only going to get part of it. So then the next layer down does heuristics. It says, all right, we have these banks of rules and synonyms. All of these things are other ways of referring to this one process, so we roll those up. If that doesn't produce a match of sufficient confidence, it rolls down to the next layer that uses NLP, uses vector embedding to look for things in the same semantic space to try to find a better match. And then the final layer, which is optional, is there's an LLM layer that kind of provides a sanity check to the whole thing and can find matches where they're very ambiguous. The system is meant to run very light hardware, meant to run offline, so the LLM layer is optional. If that's not available, it will still work. It will return you a ranked set of matching facilities. It will also find, so what it returns is a supply tree, which is a structured JSON object that says, given this design, here is a solution. And this can be spread across multiple sites. So if you have a complex design that requires sheet metal bending and laser cutting and 3D printing, and no one site can do that, as long as it knows of some set of sites or facilities that can do it, it will roll those up into a solution and return it. This is where the tech demo is going to happen. Since this is what I had to work with, I've included a couple of screenshots of the front end. This is the very simple reference front end that I threw together. The system itself is really meant to run as an API server, but no one wants to look at raw JSON. So very, very broadly, I picked this as an open source ventilator design that came out of that. You go through the matching workflow, and tell you, it will offer explanations of how it arrived at the match, what its confidence was, what was missing, provide recommendations if something is not quite right, or you're close to a match but don't have one. And then for all of the valid matches that you find, you select the ones you want, and it will generate an RFQ, a request for quote, that you can send out to those facilities. In and of itself, seems fairly simple, but if anyone spent any time during COVID trying to solve this problem, that 2-minute process took you probably about a week. So what does that do for us now? In 2020, this community came together and did some really amazing things. Produced 48 million units of PPE worldwide and struggled. Everyone came together because of what people do, but the process sucked. And I just want to ask you guys, when the next crisis happens, when the next time the supply chain breaks and you all come together and go, I want to help, I want to do something, what if it didn't suck to do that? I will also point out, so I imagine a lot of you are thinking this, oh good, another standard. No one has time to manually learn and translate their existing projects into another standard. How do I even interact with this? What am I going to do with all of the legacy systems that I don't have time to go update? I have all of this. The same pipeline that I can use to find matches also is repurposed within the system to translate existing projects into this standard. So what I was going to demo, I have about 25 existing open hardware designs from the internet, all on GitHub or GitLab links. And I can point my system at OHM, OKH, generate from URL, pass it the link, and it will pull the entire thing down, consume it, parse it, and spit out a valid OKH. You can also do package management, where you can say, all right, the OKH is the OpenML is a thin JSON manifest that's just all of the metadata of the object. But a hardware has a lot of heavy files. It has your CAD files, your SQL files, and so on. So it is the manifest, very lightweight structure that says here's where all of those files can be found and links to them. The package is actually the full directory structure of all those files. So you can treat it like npm. You can say, all right, build the local directory structure, pull all of those files, instantiate them locally, push that package remotely, version it, pull it down somewhere else, move it around. You can also, if you want to start a new file or a new project that is compliant with the system, you can scaffold those out with this tool. So I'm trying to make this as easy as possible for people to adopt and to meet people where they're at, so that you're not just going, great, another system I have to learn. So if this is interesting, if this sounds at all like something that you care about, what can you do about it? If you're going to makerspace or a fab lab, publish your capabilities. If you are designing hardware, publish your designs. If you're building tools, integrate against the API. This is all meant to be pretty accessible. It is very thoroughly documented. Use it. Let us know what you want it to do. There's a lot of ideas about the future roadmap. This is going to integrate with the Maker Resilience Kit that we were talking about earlier. The things that I'm working on now are how to make this a federated data source. So rather than having yet another Thingiverse where everyone puts their designs and then it loses funding and goes away and all the designs are gone, it is meant to run as a mesh network where you care about your designs on your node, nodes discover each other, and you use like gossip protocol to synchronize their designs independently. The other big piece that we're working on is the business logic. So how can you automate the process of calculating the cost it will, how much will it cost you to build this thing that someone has just sent you a request for? So these are the things that we're still building. But the point of this is not to be an economic engine. The point of this is not to say, how do we get rich as makers? This system is never going to compete with Amazon on price point per unit. This is because a crisis is going to come again. And I know when it happens, I will run towards the fire, and I imagine a lot of folks here will as well. And it would be great if we had better tools than spreadsheets and calling people to be like, hey, can you make this thing? Here's the link to the project, because I can get a hold of me. Here's some of the groups that work on this. If you're interested, come find me after, or we have a Q&A on Discord, and hopefully we'll hear from some of you soon.
And that's another good reminder there's a link to the Discord in the schedule, and that's also a great place to follow up with any of the talks, ask questions, see maybe you can do fun collaborations or something like that. Another reminder,
to come back after lunch to see our talk. So yeah, we're Fancy Fibre Mill, and we're building open source infrastructure for the textile commons. So we're going to introduce ourselves. We're going to tell you what we're building and why. Then Nick's going to do a deep dive into the actual machinery of it all, and Laura's going to talk a bit about the online collaboration aspect. So yeah, my name's Rosie. I'm based in Edinburgh. One of the co-founders of Fancy Fibre Mill, and I'm mainly working on growing the flax at a couple of different farms up in Scotland. And then I'm also part-time doing my textiles engineering PhD and some flax machine building.
So I'm Nick, I'm co-founder of Fancy Fibre Mill. I do engineering and philosophy, and I'm not affiliated with any universities, and that's important. I'll come back to that later in the talk.
And I'm Laura. Thanks. So I'm currently here in Berlin. I am a volunteer mechanical reviewer for Fancy Fibre Mill, lurk on their Discord, and I'm a fiber engineer and a software engineer in my daytime job.
We also have a few collaborators who aren't here today. So we also work with Percy in Edinburgh, who is helping with the flax processing and machine construction. Jordan, who's in Kansas, is a big part of the team and has actually developed wool and cotton versions of the spinning machines. And then Iris in Rotterdam, who is working on flax and hemp and cattails, which is a kind of bulrush, and helping with the flax spinning machine design and build. So it's quite an international team at the moment. So why are we doing this? So we've been really inspired by the fibre shed movement, which is the idea that instead of having a huge global and linear supply chain for textiles where you're extracting oil or growing cotton, making it into textiles, and then it all goes to landfill, that you could have a natural fibre process where you're using organically or regeneratively grown textiles. It's being locally made into clothing, and then at the end of its life, it can all be composted and give its nutrients back to the soil. And this really has a lot of advantages over the kind of fast fashion model, because it means that it's actually good for the environment. The fashion industry is one of the most carbon intensive kind of industries. About 10% of, I think, greenhouse gas emissions are attributed to textiles. And also it means that you can have a supply chain where you know everybody in your supply chain and there's no kind of like exploitation of workers. And so when we were starting this project, we found that there was a bunch of farmers who were keen to grow flax, which is what linen is made of. And there was a bunch of fashion designers or interior designers who were like, yeah, we'd love to use locally grown organic textiles, so that sounds great. And then there was nothing in the middle. There's nobody connecting the farmers to the fashion designers, especially in the UK, but I think also in America and a lot of parts of Europe as well. A lot of the manufacturing centers and machinery just doesn't exist. So we decided to start a project to build our own manufacturing technology to be able to reconnect the farmers to the textiles people. And so what are we building? So we've been working on flax processing machines, but we also, as you saw, have some collaborators working in wool, cotton, hemp, and cattails. We're working on stuff that's farm scale. So we're aiming for like a small to medium-sized farm around 1 hectare a year, and machinery that fits in a shed, or we were thinking maybe even on the back of a truck. We really want it to be affordable. So at the moment, for the parts of the machinery, we've priced it around £10,000, although that's for one copy of each machine, so it would be more than that for like production scale. But compared to what's out there in industry, we got a quote for an industrial processing mill, and they quoted us 6 to 8 million euros. So even if it was like 10 times that amount, it would still be like way cheaper than what's available out there. We really wanted to use like appropriate technology, so things that are easy for people to access within their communities, like carpentry or CNC routing or 3D printing at like a makerspace. We use a lot of Arduino for the software components of it. We've tried to use easy to find off-the-shelf parts, so like the extrusion beams, although we do have a couple of specialist parts which we have ended up sourcing from various like specifically textile machinery factories. And then also we're really interested in trying to build a community of textile hubs. So I think our dream for the distant future is that there would be lots of textile hubs in different communities where people can have access to like locally made textiles from their locally available fibers. And we've been working on 3 machineries. So there's the breaking machine. So flax is like long grass and the fibers within the straw. So this snaps up all the straw. The next one is called the scutching machine. So this essentially scrapes away the outer skin of the plant, revealing the fibers inside. And it also has some rotating combs that comb out the fiber in a process called heckling. And then the last step is spinning, which involves first combining all of the loose fibers into one continuous ribbon called a sliver, so that's drafting, and then spinning. And the last machine we've made actually does both those processes and has a few modular parts. And I'm going to pass over to Nick, who can give you a lot more in-depth info. And I'm also going to pass around some samples if people want to try and touch the flax fibers. Yeah, the space key.
So this is a video of the breaker in action. This is actually last year's breaker, and this is one of the issues we face really in the sort of open source aspect of it, is every year we build a new version and we make some improvements, and then I don't really feel like telling people how to build the old one anymore. And like quite significant changes. But yeah, this gives you an idea of how it works. Obviously there's lots of exposed parts, which we should probably hide for health and safety reasons, but it looks nicer when you do it this way. And you'll see that there's actually an e-bike motor there that's powering everything. So we'll try and do everything using DC motors where possible, which is extremely unusual for the textile industry. So if you look back historically, well, it would have been water power, steam power, and now we're talking big power, right? And so if we run things of e-bike motors or other things, we're all DC, we could technically be off-grid, which is kind of amazing for a textile factory, I think. So this is some impressions of the scutching machine. The scutching machine is a bit harder to get a feel for because it's more boxed in. And again, this is these are old models really. This year we're working on a new model which we're calling which has 2 turbines that interlock rather than this mono-turbine variety, which was initially easier to build, but actually we think that the 2 turbine version will give better results. And then these are some of the results that we're getting. So really we're interested in going all the way from the raw product into really end product garments or other textile end products. But really the really interesting thing is to get to yarn, because this is the step that adds a lot of value and which is currently really not done in Europe or you could almost say in the global north really anymore. And what we're really excited by is we've made some improvements to our machinery, especially the spinning machinery over the last year, which has allowed us to make much more regular, much finer yarn. So this picture on the left here, you can see the old version and the new version. And for anyone familiar with textile units, there's a unit called the NM, numerometric, I think, which is essentially, I always forget which way around it is, I've got it written on the blackboard. I think it's the number of 1,000 meters per kilo, I think, which reduces the number of grams per meter, basically, of the yarn. Or otherwise, if you're a weaver, you like to speak in wraps per inch. So if you wrap the yarn around a ruler or something, the number of wraps that you'll get in an inch, and we're up at now 35 wraps per inch, or about 5 nm, which is really a super versatile yarn that you can start to use for lots of different applications. So we're really excited about this. It really opens the door to actually making end product, which, although some people liked its kind of artisan look, you can't really say about the other. And then sort of thinking about, that word that's come up a few times today, scale. So the machine on the right there, you can see has 2 spindles, so already that's better than 1 spindle. So we're starting to think about this scalability issue. How do we actually make volumes that are interesting from a sort of business or economic point of view? And then just to give you a bit more, this is like some of our yarn on the loom. So this is the latest yarn. And we've been working with different weavers to kind of validate that the yarn is actually usable. So these are both hand looms, obviously, and then we're going to be looking to potentially use the yarn on some power looms and automated looms. But we're really excited about these samples that are coming out at the moment. So now for some before we go into technical details, so this is a sort of video of how the spinning machine is working. So you can see there's some, it's quite an unusual machine, I think. There's these big screws that move these things called faller bars, which then like drop and move around. You'll see in a minute you'll see the other end, so you see the faller bars are brought up. So this mechanism is how flax has been spun sort of by machine since flax spinning was mechanized. Was in the mid-19th century, and like engineering this kind of motion of the faller bars has been really quite difficult, something we kind of avoided trying to do, but we just couldn't get the quality without doing it, and we spent the last year doing it, and it's really exciting that it's actually working. It's been great. So normally I talk to textile people, and they would not understand anything about this, and now I'm going to tell you about this, and you'll be like, well, duh, of course you did it this way. But I'm quite excited about what I call the DAR, which is the distributed Arduino architecture that we use for the spinning machine, because we have to run 1, 2, 3, 4, 5, 6, 7, 8, 9 motors at the same time, all with different settings. And you can't run all of that on one Arduino. So basically we have a controller Arduino, which has a ramped 1.4 shield. Probably I should upgrade that to something newer, but once it works, it works. And then we run actually 2 stepper motors from one line. I can talk more about that if you want. And then, so 3 other stepper motors, and then that Arduino is connected through serial 3 to a secondary Arduino. So if you hit the start button on the first one, it signals to the second one, you better get started as well. That controls 4 motors. And then we have a monitor Arduino. So this is a new addition, which basically this machine is running, and every now and then something will fail. A faller bar will like get out of place, or something will happen. And really, you want the machine to stop in that case, especially if you're scaling out. So supervising 5 or 6 or 10 of these machines, you don't want to have to be like on alert all the time. So you want the machine to stop if something happens. And so what we've done here is added this extra Arduino, which then through the end stop interrupt of the controller Arduino can signal, like, so I've detected something, you need to stop now. And we can then basically scale out any monitoring apparatus we want by plugging it into this monitor Arduino. So now we've just got a photoelectric switch, but you could even imagine like having different monitor Arduinos all like bouncing down to this one to like trigger off which is quite fun. So yeah, this is the sort of architecture. This is really for the spinning machine. Obviously, for the e-bike motors, we have a different architecture. Right, on to you, Laura.
So I'm going to focus on what it's like to be not as deeply embedded. Like Rosie and Nick are the geniuses here, and I contacted them at some point, and I was like, I want to help. So I did a little bit of review, but my day-to-day, I work on very, very large mass production devices, including from 2016 to 2023, the Google hardware. And so it's been really interesting to look at what Fantasy Fiber Mill kind of can bring to mainstream industry. They have a beautiful vision and I support that, but what are we getting right now? So that's the next thing, is like, how does Fantasy Fiber Mill intersect with fast production, fashion, and consumer electronics, which just operate on totally different scales with totally different values. So first, a little bit of history. Like I said, I worked on the Google hardware. In 2020, I specifically worked on the fabric for the smallest speaker. And we made that fabric on knitting machines that are made and designed here in Germany, a company that has like 100 years plus of experience. And just this year, they were financially distressed and they sold to a Chinese company, which I'm personally very glad that someone's keeping that tradition alive. But they're not the only ones. So Meyer and C sold this year. There's another very big German company, Stoll, which makes programmed knitting machines that I think is still looking for a buyer. And you might ask yourself, like, what's going on here? Stoll and Meyer and C, the best factories in all over the world use these machines, and yet they're suffering. They have moats around their precision machine design and their manufacturing, but that's still not enough to keep them alive. So they're having to sell to places that have mills, that have the entire supply chain still. And all of the expertise, I'm sure they'll keep, this is a photo of the factory in Alstadt for the machines, I'm sure they'll keep lots of those German machinists on, but the expertise that those people have is not being passed down. So this is a huge problem. Whereas for Fantasy Fiber Mill, they're using components that you can source and buy everywhere. Obviously, this kind of hardware is kind of a little bit open source, no matter what. If you have access to one of these amazing knitting machines, you can see like all the parts that go into it. What you can't see is how those parts were machined, the exact order of the process steps. How did they manage to make steel do these crazy things? And with Fantasy Fiber Mill, we don't even have that mode. And I think that's actually a good thing. So it makes sense from my perspective that this hardware be completely open source. Because at the end of the day, we're not just producing hardware that people can replicate and make fiber from. The biggest gap in the European and North American textile industry is process expertise. So process expertise on how to make the components for the specialized like machinery, and also process expertise on like how to spin. So the things that Nick has been doing with the spinning machine, I've been learning so much over the last like 3 months that I just couldn't get anywhere else. And this used to be a deep part of every culture, like everywhere has fabric, right? But we have lost the understanding what you used to see your grandma do or you used to do in your own home, like just nobody knows anymore. And so that's my next point is it's really hard for people to learn textile processing and to understand how it currently works at scale. I'm lucky enough to have gone to Belgium to see some of the mills there. There's a couple mills left in Belgium that do the weaving, but they don't really do the spinning anymore, as was sort of previewed. But flax fiber and animal fiber processing are great places for engineers like myself or even designers to upskill and to continue to learn these things because they're the only types of fibers that people are still processing by hand and processing into like very, very high, high value fabrics. And so when so many mills are geographically inaccessible to young designers and engineers who are starting out, I think Fantasy Fiber Mill is going to start like closing that gap again. And so that's what I'm seeing personally on Discord right now. Just by being part of the community and sort of working on the Discord, I can ask questions that I would never be able to ask before. So traditionally, like flax fiber on one side, flax plants on one side, all the way to fiber on the left, these are all their own boxes. A different entity, a different company processes each of them and pays the next one or the previous one, right? And big brands have done their best in the Northern Hemisphere to offload knowledge that belongs in each one of these boxes. So when a company buys fabric, they may not know anything about the details of the yarn that went into the fabric. But when there's a failure, the moment you're like, hey, this is blocking too much of the sound transmission on the speaker, what do we do? The company might turn to me and say, should we change our yarn? Should we change our fabric? And I don't know, because the person who knows everything about the yarn and what we can do with the yarn, the subtleties of it, is in one of these boxes, and they don't speak English. So while the program manager or the sales team member that I might talk to at the mill does, I can't get to any of the nuances of the person who's on the shop floor because that person doesn't speak English and the sales team person doesn't understand the question I'm asking. So coming back to like how does Fantasy Fiber Mill maybe make money? Obviously these products have value, right? Like we sell the products down the supply chain. But I think actually one of the most interesting things that happens around this kind of thing in open source ecosystem is the expertise has value. And that brings me to my very last So doing this on the fantasy fiber mill scale breaks down those silos, opens those boxes, and makes it really porous, and you can see this on the Discord. I had a question, like a couple months ago, I was taking apart some old fabrics that had been through a bunch of wear, and I was trying to understand how the fibers behave after they've been worn and washed for a long time. This was linen fabric, and linen is like famous for having super long fibers. That's why it's super strong and durable, one of the reasons. And I was getting out of my sample like really short fibers. And so I thought, gosh, is that all wear? Like after you wash these sheets for 10 years, like all the fibers that were almost a meter, like they're now just 4 inches, like that's crazy. And someone said to me on Discord, like I could have spent months researching this question, and someone said to me on Discord, oh no, that's deliberate. Like yes, there's been wear damage that reduces fiber length, but that's because all of the industrial flax processing machinery doesn't actually work with the full length of flax anymore, because it's been influenced by cotton processing machinery, which is much shorter staple fibers. And like, this was just so mind-opening, because I realized, okay, if I, as a textile engineer, want to work with really strong long-line flax, current flax that's being sold as long line really isn't. It's not pulling with fiber. And like I said, I could have spent months researching that, but because of the amazing community that has been built around Fantasy Fiber Mill, I can learn this really quickly again. So I think there's something very interesting about collapsing the entities. The farmer doesn't just know things about the farming. A Fantasy Fiber Mill farmer might understand what happens at the end processing. And so we can make changes, choices on the fly. Like if one season's flax crop has been really impacted by the weather or by how much rainfall, and it's not going to go into long line, you can still then all the way through supply chain, like figure out how to process it for its highest and best use. So yeah. That's it.
Thanks so much. Yeah, we'd love to hear from anybody who has questions on Discord or on email. So yeah, please get in touch if you have any questions or advice, and I'll be listening to you.
Thank you, that was great. More fibers. All right, we've got a next talk coming up from Taboo to Toolkit. And your speakers for this are going to be Suzanne Kren, a mechanical engineer, student of renewable energies, art, and narco-feminist. Is that right?
Yes.
Sigrid Kuiker,
Yes.
communication scientist, lecturer, open entrepreneurship explorer. Yana Sadevishkai, business psychology student, passionate learner, eager for communication. Min Fong Fung, junior researcher with focus on sustainable consumer behavior. And Lin Huang, strategist, storyteller, cross-cultural communicator, and business student. And finally, Jessica Helmuth, who is an artist, community organizer, facilitator of bodily expression. All right, taboos, let's break them.
Hello, everybody. My name is Visu, and let me introduce you to the open source hardware period cup project. It all began when I was hiking with a friend, and she told me about that she cannot buy her menstrual cup anymore, and this was the only one that really fitted her. So, giving my background as a mechanical engineer, I started to make some sketches and think of developing one cup myself for her, and that would be exactly as she needed it. So, as I said, I started by modeling a simple prototype. The general idea, it was to print the mold as 2 parts with a 3D printer, and then smooth it so that the layers from the printing are not noticeable anymore. For the moment, we chose for ABS because it can easily be smoothed with acetone, but in the future we want to use more sustainable materials. Then decide for medical silicon and cast it. That sounds pretty straightforward, right? Yeah, but it's like you want to climb a mountain in a straight line. It's not so easy. And as always, after starting a project, I realized that it will not be so simple as I initially thought. To define the parameters needs the knowledge of a specific body, because you know everybody is different, and the shape of the cup should reflect the the features of the body, like the vaginal canal or the pelvic floor, and also which experience one body has made. So the diameter, the length, and the wall thickness should not be the same. Of course, there were problems, and to name just one, there were irregularities from wall thickness, from the air bubbles, which build up when you mix silicon, the components of silicon. So I started to speak with people around me about the personal quest I had, and I received so much helpful advice and guidance and support, mostly from the OSH community, but also beyond. It was really great. So the project idea received so much positive feedback and quickly grew. As I told Siegfried at an OSAC meeting, what I'm working on, she came up with a plan and quickly put together a highly motivated team. And as you can see, we are now 6. And different people means diverse perspective. So now let's see from Siegfried about her motivations.
Thank you, Siegfried. Hello, so I'm Siegfried Beuger. I'm a member of OSAC for 4 years now. And before my retirement, I worked in entrepreneurship and in education. So I thought I'd go to OSAC and then I do something with entrepreneurship and open educational resources. And when I met Sisu, I thought, yes, this project is exactly what we need. It's a clear project. It's a small project. It's a small and clearly defined product. This can be a pilot for OSH entrepreneurship, because I think this is lacking still. Yeah, there is a lot of technology, but not so much that goes to market. So the menstrual cup is a doable project. We have the makerspaces in mind so that it can be manufactured in makerspaces, and that means it can be locally produced, but on a global scale. So whoever goes to Coburg and gets the plans can produce it. And we hope that with this open process, we will have an impact of many women who still need something. So we see the cup not as we are the greatest and we will now conquer the world and everybody will use this product. We see it as an alternative to existing products like tampons or pads, just to give women more choice. We want to find out what works, and we want to learn, and we already have learned a lot, and we want to continue. If we find a business model in the end, great, we go for it. But at the moment, the focus is on the product and how to spread the word. And we got a lot of support already, and so we know that we can build on the community. But it's not so easy, as Sisu already said. there are personal differences. Each person that menstruates is different. Culture plays a huge role, religious systems, belief systems. Even in Germany, we are already quite advanced, but I think it's still a taboo to talk about it. There might be ethical and legal considerations, or just things like the environment. If you don't have toilets and fresh water, you have a problem as a woman. And if you don't have a bin in the toilet, you don't know what to do with the pad, for example. Yeah, so there are a lot of things. So what we can see from that is that the menstruation is connected very much to women's health, to well-being and participation. It's not just a bodily thing, yeah, it's a societal thing. So, what we can see is that how can we bring something like that to the world, and how to spread the word, and how can we make a big process out of it. I don't know if you know the effectuation process. Effectuation is a form of entrepreneurship framework, and we can take some inspirations from it. You can start immediately with what you have. Who you are, what you know, who you know. You don't have to wait for the best opportunity. And at each step, you just think, what are you willing to invest? What are you willing to lose? And of course, you should invite people to join and to bring in their needs and their ideas. If you go, as long as you go, unexpected things will happen, and all of them contain information for you, even if they might be negative at the beginning. Because if life gives you lemons, make lemonade. So that's the proverb behind it. And most importantly, take responsibility, act, and co-create. And I think this concept fits very well to open source, and can very well fit to how we bring things to market, or how we develop things. And I think we have seen it at the air gradient example. That was, in the end, it was effectuation, what was done there. Yeah, and with that, I will give over to Jana.
Hi everyone, my name is Jana, and I would like to start my part by sharing some cool numbers with you today. Yes! Love the energy back there. The first number being that 1.8 billion people menstruate every month. More than 300 million people are menstruating on any given day. Around 500 million people lack access to menstrual products and adequate facilities. Only 39% of schools globally provide menstrual health education. A modern menstruating person may experience around 450 cycles in a lifetime. A person may use over 11,000 disposable menstrual products in a lifetime. And in support of that, disposable pads may take 500 to 800 years to break down. But the most important number that has brought this project together is that, as you see, a menstrual cup, if well made, can last for you up to 10 years. So, only from this... Guys, I should have became a rock star. What is this? Okay, so as you can see from these numbers, menstruation is really an everyday biological topic, but still to this day, in so many cultures, it's treated like a taboo that it shouldn't be known of, it shouldn't be heard about. For example, in my culture, I come from Iran, not Iran, Iran. Period pads are given to you in black plastic bags because no one, including your father, including your family, including your brothers, is not supposed to know that you're menstruating and you're in need of pads. In the same geographical location, women are not allowed to touch the same food others touch. They're not allowed to shower, and they're not allowed to pray while menstruating. And so many young girls hear the word period after the first or the second time that they already had their cycle. And how terrifying, really. Therefore, we see this project as an opportunity to define learning programs and support systems and mediate peace between women and their bodies. And we would also like to bring the proper education to women in need of it. We acknowledge that there would be obvious challenges such as cultural or personal blocks and obstacles, because I personally think that when something is repeated to you so many times, at some point you start committing to your own personal taboos. We're totally aware of that, but we're also aware of the importance of providing this education and the mental and physical consequence of not receiving it. Therefore, we see our project as maybe a small, maybe a big step in a more accessible feminine hygiene. Can I hear another one of those claps? I will now hand it over to my dear team.
Okay, thank you, Diana. That brought tears to my eyes. I'm Ling, and coming from a Southeast Asia country myself, I could deeply relate to what Diana just described about the cultural silence around women's menstruation. And even though this is something completely natural and normal, it was often treated very discreetly in many societies. So for myself, with a background in international relations and cross-cultural management, I was interested in the differences between cultures, between countries, and especially the communication around sensitive topics, difficult topics, I would say, like women's health, menstruation, and how social norms have shaped this conversation, how different it is in between cultures. And then I got introduced to this amazing project by Zikert. She was my professor in my master's degree. And working in a team with such a diverse cultural background, we could immediately see the different levels of education, of openness and discomfort regarding this topic about menstruation, and the silence surrounding it as well. And because of that, I could realize how much communication shapes the way that we experience, the way that we approach this topic, and not only on a social level, but also on a personal level for each individual. So for us, communication means creating and building an understanding in between very different groups of people. And, and every community and every individual requires a different conversation. For example, with manufacturers, we want to bring up the idea that they're not just producing or distributing another product on the market, but that they are contributing to a very meaningful and a socially impactful goal. And with users and different communities, especially the communities the areas that
menstruation is still surrounded by taboo or discomfort. The goal of our communication is to bring trust, openness, and accessibilities for them. And internally, inside of the team, between us, communication for us is translating between technological innovation and the human experiences, because we want to make sure that the project can remain connected to the real human needs, the realities, the emotions of real people that the product is fundamentally meant for. And I think that's why this project means so much to me. It's because communication becomes more important, more open and inclusive, and there's room for something much more sustainable. And now I'll give the stage to my teammate Fu and her inspiration.
Thank you very much. So yes, we only have 2 minutes, and I also want my the last colleague has some time to speak, so I will try to speed up a little bit, because we have already have Jana mentioned about all the numbers regarding the menstrual cup, right? Just give me like a rough number, how much do you think this 11,000 menstrual product is recycled properly? Like 10%, 99%? What is the number that you get? 3%? Oh, 0. Okay, there's some pessimistic going on. But okay, not a very great view, but a little bit better new, 20% though. And then the rest, when you flush it down the toilet, no. But then if you think you didn't have to do with like 40% menstrual disposable menstrual cup flushed into the toilet and end up the oceans. So that's not what we want to have. And that is why when Sigrid mentioned about reusable menstrual cup idea to me and broader open source hardware, I was so buying in. So a little bit about myself. My name is Fung, and I am a PhD student from higher university. My research focus is in reusable packaging system. So you see the relevance between myself and the project. And then, as Jana mentioned, one single reusable menstrual cup can be reused up to 10 years. So you could imagine, I mean not men, but other people menstruating per month, you could imagine how much waste you can reduce if you use such a menstrual cup. Yeah, but then we have already listened to my colleague Susanna. She mentions that we try to be very green, we try to be very sustainable, but we still have so many questions that's left open. We don't know yet if our current production is optimized. We don't know if the silicone material that we are testing in our menstrual cup can be reused, recycled after its life. So there's many other things we haven't yet been tackled or solved. And that is why when it comes to such dynamic across disciplinary expert, we were thinking the traditional business model of closed innovation would not allow us to do, because in order to fund such experts, you have to pay them, right? And it's super expensive in order to have such cross-disciplinary research and development experts into our team. And that is where we find open source hardware in the community, at least for our current project. We have, I would say, we have us developing such all the bubble from the first priority time, and they enable us to bring and to continuously learning and improving our product. And some shared experts are going to help us to move away from the traditional innovation, profit-oriented, and make our, or probably future yours innovation oriented to a better world. And I think I may talk more about talking about networking. I would kindly ask you to give us about 2 more minutes to Jessica. She's introducing the networking. I stopped talking.
I'll make it really quick. Hi everyone, I'm Jessica. I came into this project to research it for my master's thesis. I came from circus and then community organization but I started a business to try to learn how to make really important and good ideas happen and last. So I was really excited to find this team. Essentially, I did a participatory network mapping process that mapped not only the communities around this project connected to us, but also the topics in it and the sort of causes from our backgrounds, the challenges we've all experienced that made us see an opportunity in this idea and made us want to contribute to it. This map had a lot of these ideas connected to different communities connected to it, and the findings were really that while we all have really diverse causes for wanting to make this open source hardware period cup happen, they're all really mutually beneficial. They move us in the same direction. So in that way, each of us are connected to our communities with their topics and their causes that we've experienced locally. And this idea, this accessibility of an open source hardware period cup and all the communities connected to that, all the innovation potential, has made us be able to come on common ground and move in the same direction, supporting our causes and our communities, but also the causes of each other, and kind of finding new ways to explore that in quite a special way. So far, it's been really lovely to be a part of. And as you can see, OSIG is the main supporter of our network. So with that being said, we're really looking forward to seeing where this network develops, who else finds a reason to find this idea important and want to contribute to it. So if you'd like to get in contact with us, if you have any ideas, if you have any questions, we'd really love to hear from you and see where these shapes of networks and communities go next. So thank you so much.
Very well done. Okay, for our next talk, I want to take a little poll of the audience. You've got some good energy out there. How many of you sell open source hardware? Raise your hands. Oh, just a few of you, just a few of you. You guys got to get better at selling open source hardware. How many of you sell open source hardware in the European Union? Yeah, you're right, someone in the European Union, no? Okay. Well, we're going to hear a talk just right now about how to sell hardware in the European Union and what the CE mark is and all the mysteries around that. Please welcome Clemens Mayer, host of Element 4 Presents YT channel, founder of Mayer Makes and Smander.com, involved in the maker movement since 2014, certified CE product coordinator. Please welcome Clem.
For speaking now.
Hello. You basically took away my initial question, but it's a perfect question because there is a point where a lot of us think about doing the things we do, but share it with others, maybe on a commercial level. I don't want to know how many of you have already thought about CE compliance and whatever all goes into making a product fit for market, because I know that this is a topic that you wouldn't like to take much care about if you're only care for building awesome stuff, which also is the same for me. Turns out I like dealing with all these regulations and stuff, so I made it part of my job to help others with getting their stuff onto the market. I'm going to give you the ultimate answer about what you have to do for your product in one simple sentence. It's basically, it depends. It depends on a very specific of your product. One thing that we always have to be sure about is that whatever rules and regulations apply to your product, whatever you have to do to get to market compliantly, always depends on the very specifics of your particular product. There is no general answer to very general or easy sounding questions. There's always a long-winded thing that usually starts with it depends. Before we even get into the topic of CE, there's one thing that covers it all on a much higher level. That's the GPSR, the General Product Safety Regulation. And that one will apply for almost any products that you might put out there. The only things that are not covered by it are, for example, food, aviation, defense, some parts of medical equipment, mostly because there's already much more precise stringent regulations for those types of products. So everything that is not covered by already very strict subset is covered under General Product Safety Regulation. So first thing we have to do is find out what rules apply to our product, and we have to analyze it. And I really want to emphasize this, you have to be critical with your product, with yourself, and how you approach this thing, and with stuff you find on the internet. There is a ton of information out there. There are primary sources, like the EU Commission page, for example, that outlines the whole process in very long-winded pages that take ages to go through. But there's also a lot of hearsay and a lot of misinformation out there. And since regulation is constantly changing, you will find a lot of information about outdated regulations for stuff that will apply to one product but not the other, but may read as if it will apply to yours. So be critical of all these things. The good news is you can just get help whenever you need it. Now, one of these places is Sweden, but there are many others. And also, you get a lot of free educational content on the web, but as I said, be critical to make sure that it actually applies to your case in particular. That's why we do personal guidance on these things. So, we are all dealing here with open source hardware, and for those kind of products, there is a distinct advantage compared to all the proprietary stuff. The things we do at Xmander are about like 60% are proprietary things, and only 40% open source hardware. For one reason, the big clients with the big proprietary products basically pay the bills so we can subsidize open source hardware, so I do more work on that side to make this all work. But that also means that more work goes into these proprietary things because they are usually not as well documented as one might think, and there are certain guidelines on how good your product has to be documented to count as a full technical documentation. If you publish an open source product and this documentation is good enough so that somebody could download the source and produce this product and use it, then your product documentation is already a lot better than a lot of other products on the market. With open source, we have the advantage that we take our well-documented project and have pretty much, say, about 60% of the technical documentation already done by default. And this is something that takes a lot of time if you go about it in a considerable way. Git is a huge time saver on version control and making sure that your process is documented, especially in something called a risk analysis. We'll quickly go over that. The approach with versioning over Git saves you a lot of time. Okay, here are the main things on regulations that we have to talk about. We already talked about the General Product Safety Regulation. That has a very important article, Article 5, which says you are only allowed to put safe products on the market, period. So, how do you prove that your product is safe? You make a thing called a risk assessment, and there may be other rules that your product falls under, and if you comply with all of these rules, then your product is safe. One of a subset of the CE rules is on the screen right now. These are some regulations, but not all, that will apply to a product. Which one of these is relevant for your product? That has to be looked at in detail. So EMC is electromagnetic compatibility, how your product will interfere with other things around it, and as well how other things will interact with your product in the electromagnetic spectrum. So we have to make sure that we don't disturb the functionality of other things. Low voltage directive is for all products above a certain voltage level. This is mainly like mains power equipment, for example. Then RHS, restriction of hazardous substances. A lot of people fear this regulation, but it's actually quite easy to comply to because this is basically your BOM, then all the data sheets of all the parts in your BOM, and to make sure that all the things and the materials and substances that you use in your product are RHS compliant, and you document that. So this is mainly a paperwork thing. Then we have the red directive, the radio equipment directive. If your product has any sort of radio in it, Wi-Fi, Bluetooth, whatever, this will apply to you in some form or another. Here is the biggest money saver that you can have in a product. Don't use anything wireless. If you can avoid it, don't use it. If it's a nice feature, a nice thing to have, it would be so nice to have everything wireless, but it's not strictly needed for the function,
you can save a lot of money. And I mean a lot because the tests required for EMC and RED in comparison are 1 to 10. So that's 10 times the amount of money possibly with those. Also be very careful on how you implement RF stuff. This is usually a bit harder to get through the testing. Machine directive is all that is called a machine. A bicycle, by the way, is not a machine because it's human powered. And if it's human powered, horsepower or whatever doesn't have any other power source but has moving parts, it might be not even a machine. And then we have the cybersecurity regulation. This is very new. If your product does anything with the internet, can be accessed over the network and whatever, cybersecurity regulation may very well be applied to your product. This is currently in the evolvement of things. There are some requirements that are already have to be implemented now. There are some that will follow in the next years, but this is the first time we have a regulation that has rules that will retroactively also have to be applied, which means you have to have security updates. Okay, I've talked about regulations, whatever, but actually there are two kinds. There are directives and regulations. If you read something like General Machinery Directive or Electromagnetic Compatibility Directive, this is one of the older subsets that has to be first translated into national law, because all the EU member states are very fast. Meaning they were not in adopting these rules to their national laws. Now the EU puts out regulations which are in effect directly. Don't get yourself fooled by the dates that are on these regulations, like years and whatever. This is not the year it is in effect, this is just the year they signed off on it. So each regulation may have a different time on when it's actually in effect. So the new machinery regulation, for example, applies to all machines from January 20th, 2027, for example. These are the rules in these regulations, whatever, these are the rules that you have to follow. Now, how do you follow these rules? There are recipes for that, and they're called standards or norms. So standards and norms are not laws, they are just recipes on how to do things. The recipe on how to perform things in a safe manner, or how to construct things in a proven safe manner, or how to test things. So all the EMC tests and whatever, all expensive lab stuff, this is all based on standards. That's great, because there are harmonized standards, specific standards that basically have a thing called presumption of conformity, which means there are rules. The regulation actually says, hey, you have to provide evidence that this thing fulfills the requirements of that regulation. How will you do that? You apply the recipe, which is a harmonized standard. In the standard, it says, do this test. If you do the test exactly as in the recipe, you say, okay, that's good. We accept that because we have, beforehand, we have agreed, all the EU member states have agreed that this way of proving compliance is okay. And standards are minimum requirements. You can always do better. Standards are not something from the tower of unachievable things. Standards are recipes and they can be fulfilled. All of those stuff here might sound quite scary, a lot of paperwork or whatever, but once you have a grasp on how the system works, it's all achievable. It's just work that you have to put in once and you can get help at any time. By the way, the law doesn't actually say you have to do all the testing. They have to say you have to provide evidence, which means you could make up your own standards and your own testing procedures. But you would also then have to provide evidence that this is good enough. So this is actually a higher burden. But some companies actually do that. For example, if they make very specialized test equipment, these standards might not be good enough for their cases. So what do you actually have to need to do? You have to first identify the applicable directives and standards, which means analyze your product, make sure that you know what you're dealing with. A big part of my job is helping you identify these things correctly. Then we have to do something called a risk analysis or a risk assessment. This is a bit dependent on what rules apply to you. If the General Product Safety Regulation applies and no other CE relevant things that need a specific risk assessment, you do a risk analysis. This is a bit of an easier document.
I've done 1.5-hour webinar with Robert Ferranek recently on that one, so please watch that on YouTube if you're interested. We go through all the details in there. You have to, if applicable, perform required testing, create the technical documentation. Already did that with open source hardware for the most part, hooray, a lot of time saved. Then there's the issue of the declaration of conformity. This is the actual document that says, hey, I am the manufacturer of exactly this product. These are the rules that apply to it. This is how I tested that this is okay. And here I sign it to swear that this one is okay. And this is the basis for applying the CE mark. Without all the other bits, in this order basically, there can be no CE mark on your product. So even if you find a CE mark on something, on there, and there is no declaration of conformity that the manufacturer gives you, and they have to give you that, you can just ask them for it. They also have to give you a manual in the language, by the way, just ask them for it. And if they can't give you that, well, that mark is void. And by the way, if you find a number next to that mark, that is the number of the laboratory for a modified body who had tested that one. So if you want to know if a specific type of product falls under very strict regulation where you have to involve a specific accredited lab, if there's a number next to the CE mark, it is such a product. Oh yeah, and keep all your documentation up to date. This is actually a requirement. So always make sure that if you change anything like, oh, I have a new vendor for capacitors, I've done a revision, always keep your documentation up to date. Okay. Now we go into the practical part. There are, as I said, a lot of things out on the internet that may be a bit misleading. A lot of the misleading stuff is made up of mix-ups of regulations from the EU or from the United States, with a lot of exemptions that may or may not apply. Spoiler, if you try to find some exemption that will apply to your product, you will likely waste a lot of time with that. It's much better to not look for schemes or tricks to like sneak by some regulation. These are all written in a way that exactly that doesn't work. So if you try to circumvent things, and if you did not take the care to actually like correctly assess your product, this will make things even worse. It's much better and it saves time and money in comparison to just do it right from the beginning. So in case you are confused and don't know what to do, get help early on. This makes the whole process easier, but the most important thing is don't try to find any sneaky ways. If you want to know if your sneaky way works, just contact me after the call and I will likely say no. So I've heard many schemes and I've found one, like one guy told me a very specific scheme. Turns out, yes, your product will fall under a specific exemption, but this is a very, like an extreme narrow special case. This is not something that will apply to 99% of you. So be aware, your product will likely be just a normal item that has to go through the process. You have probably all heard about self-certification. What is self-certification? Where is this? I don't know. This is a self-certification process. Self-certification is not putting a stamp on something saying, yeah, it's okay. Self-certification is going through this process. All the individual regulations, so I'm kind of paraphrasing here, like they all have their specifics, but in general, it depends, but in general, you can do self-certification under most of these regulations, and that means I apply which rules apply, I find the standards, I produce my product according to the standards, I test it wherever required, I know and confirm for myself that this product is safe, and that it will work, and I document that process, and then I issue the declaration of conformity. This whole process, that is self-certification. The opposite of that is not self-certification, which is basically I have to submit my device to a notified body, and they will then assess if it's correct.
and if it can be certified, which is quite similar to how the process in America works, by the way. Also, I have a 2-hour webinar with Robert Ferreneck on that process, on the differences. So you can see there are no short answers to that. Okay, let's go back here. Really important thing, documentation is as important as testing, and with open source hardware, you have a huge advantage already on the documentation side. You know how to document things, and the question comes always up, how good does your documentation actually have to be? If you would die today and you would give your documentation to someone else, could they just keep on producing it? If the answer is yes, then absolutely your product documentation is good enough. The earlier you start with all of these things, the easier you will have. Get help before you get stuck is a general advice that will always help in these things. And if you need to get in touch, here's all my details. We, of course, also have a Discord, and I'm very active on social media and whatever. We have a newsletter and things, but I always love just talking to people. We have quick to book calls and whatever. If you want to learn more about this, just contact me directly after this talk. Thank you.
All right, so we have the final speaker at 3:40 or so. We're going to take a 10-minute break. Don't get lost. But before we go, I wanted to ask a question that gets asked.
Testing, 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 testing. Testing, 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 testing. 1, 2, 3, 4, 5, 6. Testing, 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 testing.
Mitch founded Cornfield Electronics, which gives talks and workshops worldwide promoting hackerspaces and open hardware everywhere he goes. Thank you so much.
Hey everyone, it's good to be here. It's my first Open Hardware Summit in quite a long time. I used to go to every one when it started in, was it 2010? And just celebrating open hardware and sharing and learning from everybody. And I've been promoting open hardware ever since. And I was an early adopter in 2004 with my TV Be Gone project. And for those who don't know, TV Be Gone is my invention. It's a keychain, which I always have with me, that turns off televisions in public places and monitors. And I've been making a living off of that for over 20 years now. And I love encouraging other people to consider making a living on their projects. But before I get into my talk, this is my contact info. Please feel free to contact me anytime for any reason. I love helping people any way I can. That seems kind of, that's better. So much about our world is changing in so many ways, and open hardware is definitely not immune to these changes. My talk today is intended as an attempt to bring up issues and ask questions that I think are important for the future of our open hardware community. As we all know, open hardware is way cool. And many of us play with it, many of us work with it, many of us here make a living from it. I saw a bunch of people raise their hand when that was asked a few minutes ago. I've made a living on open hardware since 2004, and wouldn't it be nice if all of us who do it could continue to, and wouldn't it be nice if even more are able to make a living on meaningful projects? And wouldn't it be nice if we could continue to do what we do for others to benefit from for a long time to come? There are some big changes recently that we need to acknowledge. My slides don't quite fit, but I think we'll be okay. For one thing, two really big players in the open hardware movement, Arduino and Prusa, have changed recently. Arduino, which brought so many people into playing with hardware and with microcontrollers with their open source ethos, was bought by Qualcomm, a huge corporation, last year. And Qualcomm doesn't really seem to understand what they bought. Prusa created a new license for their 3D printers recently, and that new license has the word open in it, but doesn't follow the original definition of open hardware that we collectively created 15 years ago. And regardless of any value judgments on any of that, these are really big shifts. Throw into the mix the sudden emergence of AI, a big wild card that may be a useful tool to help us to some degree, maybe help us to a huge degree, but it may also have some unintended consequences, probably will, that maybe aren't so good. So anyways, today I want to explore these shifts, and more importantly, to ask questions. Where goes open hardware? Oh, too soon. Where goes open hardware? Is the movement dying? Can it sustain itself? Is it being swallowed by large corporations? Do we need to change our definition of what open hardware is? Can we still continue to make a living with it? Can more people make a living with it? I have no crystal ball to answer these questions, but I want to provoke some possible directions for us to ponder. So let's start with the changes with the two big players. Start with Arduino. The open source For so many of us, and perhaps millions, Arduino was the gateway, the hello world of hardware. Arduino made it so easy for people with little to no experience to start playing with electronics and microcontrollers. The open hardware of Arduino meant that others were encouraged to use and improve their designs. The more people who copied the hardware, the more the hardware improved. The number of people using Arduino increased, and the more projects there were that used Arduino. And the more projects there were, the more people actually bought the official Arduino boards. The open source software meant that others could help improve it, and no one needed to worry about making use of their open hardware designs, even if they're selling their project as a product. In this way, so many projects and products were created using the Arduino software, which helped further spread the Arduino brand, and the more people bought official Arduino boards. It worked really well for Arduino, and it worked really well for all of us. This is the entire ecosystem created by Arduino's open hardware and software. And as I mentioned at the end of last year, after 20 years of engagement, the Arduino people sold everything to Qualcomm. And one can hardly blame them. 20 years is a long time, and they had an opportunity to cash out and move on to other projects. There's with a link at the bottom, which is a blog post from Charlie the Molecularist. He points out there that when Qualcomm bought Arduino, what they primarily and perhaps inadvertently bought was their open source ecosystem. And Qualcomm appears not to understand that. They changed the terms of service to, amongst other ambiguities, make it unclear if projects could utilize Arduino hardware or software and remain safe from Qualcomm later asserting patents against you. As a result, many people, probably myself included, are now moving away from Arduino to other platforms such as Espressif ESP and Raspberry Pi to continue to make a living on our open hardware projects. So that link, if you want to take a picture, these slides should be available afterwards also. And then Prusa. Josef Prusa is definitely a hero of mine and probably to many of us, and for good reasons. He and his company were an example and model for profitable open hardware and making a living on one's meaningful project, in Prusa's case, 3D printers. But recently, Prusa changed their license. They moved away from a purely open source model to one that no longer allows anyone to use the designs for commercial purposes. Prusa was understandably concerned about people and companies making use of their designs and then selling products without further contributing back to the community in any meaningful way, and thus diminishing Prusa's ability to make a profit. And I've got a slide here with another link at the bottom, which is their open source, or their new license with the word open in it. Their new open community license, OCL, is intended to allow individual users to do whatever they want with the design files other than to sell products that make use of them. The original definition of open hardware, however, created 15 years ago, was the result of a lot of debate among community members. One major point of debate was whether open hardware could restrict use of design files against commercial use. That debate is still going on today, and it'll probably go on for a while. But the original definition of open hardware that was agreed upon by everyone involved in the community in 2011 and still in use today excludes any restriction against selling products or designs. It explicitly encourages commerce through the open exchange of designs. And I think that works really well for people. So what does this tell us? Well, for one thing, for sure, it tells us that some businesses are no longer believing that the original definition of open hardware is a model that works for them. For longer than I've been alive, which is a long time, there's been this ongoing notion, which seems weird to me, that you cannot give your ideas away and also make money. And the air sensor person was going over some of these concepts as well. So, how do you make money? Is this true? Can you give your ideas away and make money? Many people think that you can't. I tend to differ. I think that it's really helpful to give your ideas away to make money. And let me explain with a couple of examples. Oops, wrong slide. Qwen 3.6 is an AI, and when I fed it the abstract for this talk, when I extended my proposal, the abstract, I fed Qwen 3.6 the abstract and asked it to write this talk for me, like so many of us do nowadays. It's bizarre times we live in. But anyways, it came up with a talk that was not the one I'm giving you now. It came up with some so-called common wisdom from the internet and said that I should say to you and anyone listening, open hardware is no longer a hobby, it's a business. And businesses need to survive by protecting IP, intellectual property, while keeping, it further said, while keeping the community engaged. I agree, that last part, that open hardware businesses need community engagement. But community engagement results from the goodwill of sharing the designs openly, not from protecting IP. In my opinion, probably a bunch of you agree, maybe a bunch of you don't. In my opinion, sustainability and openness are not mutually exclusive. In my opinion, openness causes sustainability for our kinds of projects. As one of many examples, I can give my project TV Be Gone. TV Be Gone was and is sustainable because it is and has been open hardware. I have sustained making a living for over 20 years with TV Be Gone because it is open hardware. I received a lot of help from incredible engineers who made my project better for free. I have low legal fees, free, because open source licenses are free, unlike patents. Incredible PR from all the people who copied my project and enthusiastically shared it with everyone they know, saying, look at this cool thing that I made, even if they sell it. And that directed so many people to me and my project. That is PR I never would have been able to afford if I would have had to have paid for it as a small company. All of this created so much goodwill, all of this is free, and most importantly, lots and lots of people were going around the world turning TVs off and monitors, which is why I do this project. All of the above generated for me a lot of community engagement and sustained my business because the project was and is open hardware. So, some people might be thinking, what about bad players? Yeah, there are bad players, and it sucks. It really sucks, but it's part of our world. We can't escape that. And regardless of your business model, it's there and it sucks. And regardless of whether the bad players violate an open hardware license or another license or whether they infringe on a patent, it's still there and it still sucks. What can you do to deal with bad players? Regardless of how you share or protect your IP, if someone violates a license or a patent, all you can do is go to court and spend lots of time and money. It's really all you can do. And unless your business model is profiting by lawsuits, how many of us have enough time and money and energy for that? Changing terms of your IP, I would argue, does not help. This is definitely not easy for anyone. But rather than protect against bad players through lawsuits, I will further argue that a better approach, as the AR sensor guy also said, is to continually evolve your project to new and better versions and stay ahead of the game. This is true whether one has an open hardware license or a patent. But with an open hardware license, with all the goodwill generated through community engagement, you are not alone, and evolving and innovating is way easier. Further, if it turns out that the market you created stops working for you, perhaps because others can make your thing better and or cheaper, as painful as it might be to let go and move on, maybe it's time to let go and move on, freeing you up to do something else. But again, this is not easy or fun. But the only really other alternative is to fight it out in court with lots of time and energy and money that you probably don't have. And then we have AI. I want to just mention a few things about AI. In comparison with software, I haven't really heard of a whole lot of hardware design with AI. Have any of you had any experience with that? A bit? Yeah, I've played around a little, and I don't know, I think it's going to get way, way better. Right now, we can certainly do firmware quicker and better with using it as a tool. We can have it do some calculations and tell us about calculations that we might not have thought of, things like that. But I think it's going to get more. But as with any tool, we need to be skilled in using the tool. You know, if you've never used a hammer before, you're going to get hurt learning to use it. A lot of people are getting hurt learning to use AI effectively. AI is really good at giving you a starting point, but not the finished thing. As an example there, this talk. It gave me a good start, but not the finished thing. TV Be Gone Kit, which I have a version of, a new version of, where I'll be giving a workshop tomorrow, by the way. Look how fun it is when people come together in solder. There's going to be a lot of that tomorrow. Anyways, I wanted to add new off codes. I hadn't done that since 2018. Oops, time goes away. And I wanted to do it before the big Chaos Congress in December, and I only had a week. And it would have taken me about 3 weeks doing it on my own. But with AI, I did it in 3 days. But the first 5 minutes, it gave me the answer. 5 minutes. I was like, wow, this is amazing. But it was totally wrong. And it took me and a friend who are really good at firmware 3 days to get results that work. And by the way, the results were only 7 new codes that I needed to, again, turn off way over 90% of all the TVs in the world. It's fun turning TVs off. So let's see, I'm running a bit out of time, so I'm going to skip some of these other things. You know, another thing is trolls. Trolls are making new versions of open projects, and it'll probably be applying to open hardware as well, and then calling it their own and even suing the original creators. We've got some serious problems to contend with in our near future. But let's see. Part of what created open hardware was a philosophy. Let me add this one in. You know, I want to see all of us, who want to make a living out of meaningful projects that we can share with others and, you know, make life better for us and the people we help. So I'm going to go to my last slide, which is more of the main thing here. It's impossible to say what things will be like in a few months from now, let alone in a few years. Instabilities, wars, all sorts of economic problems, energy problems, on and on and on. It can be quite overwhelming to think about all this. And open hardware is going to be affected by it. All of our lives in so many ways will be affected by it. Will open hardware go away because of these challenges? Maybe, but I don't think so. I think it won't be easy, but I think that we as members of a supportive community have a better chance of staying resilient in the face of the unknown than many, many other people, and we can share and help others in turn. We are a community of hobbyists and professionals. We're a community of total newbies and seasoned veterans. We're a community of people with curiosity, the need to explore, the desire to learn and share with one another. This is really powerful. We are still open, we are still transparent, and we are still helping one another. I really do want to see more of us making a living doing things that are meaningful, sharing our projects as products with others, and making a living on this rather than wasting our money on some stupid job. I would love to see that. We have community. Let's continue to support each other and make this happen. I'd love to hear your thoughts, your fears, your successes. Let's talk. Thanks.
All right, fantastic. Thank you again to Mitch Altman. That was a really wonderful talk, and thank you for all the work you've done over the years. I first learned to solder from the comic book you made, and I'm sure many other people here have learned all sorts of wonderful things from Mitch over the years. Next, I'm going to introduce mining old treasures with new electronics for DIY DNA sequencing. This talk is by Lisa, who has been involved in DIY bio since 2008 at varying levels of intensity. 10 years ago, she became interested in making DNA sequencing available to DIY practitioners, which has led to teaching workshops on it and co-creating an open DNA fluorometer. Thank you so much.
Okay. Hi, everyone. I'm Lisa. You can reach me here. I'm going to talk to you today about DNA sequencing. And just for context, I'm not a professional in this at all. But this talk is a continuation of work I've been doing over the last 10 years, spread out like the workshops that were mentioned, working with the one commercial portable sequencer, figuring out how it works and passing that on to amateurs and artists, and building that DNA fluorometer. So what I'm going to talk about today, well, DNA sequencing, obviously, and I'm going to assume that we all know that DNA is kind of a long string of the 4 bases, H and C, T, and DNA sequencing is the process of figuring out what that sequence is for a given DNA molecule, something like that. The talk is also about the question, can we have an open DNA sequencing platform, and what might that look like? As mentioned, I've been working with the Nanocore Minion, which is this commercially available, very small sequencer. I brought mine. It's very small. You can probably not see it from the back, which is the whole point. And it's good fun, but the problem is that you're completely dependent on one vendor, because this thing, as it is just a very expensive paperweight. You need consumables to make it work, and you need them continuously. And they're all available from that one vendor. It's also pretty expensive still to use it. So what do I mean by that? The device itself runs you about 3,500 euros at this point, which is not great, but even worse, the consumables run you about 500 euros per sequencing run. So anytime you want to sequence a sample, it's going to be 500 euros, which is really sad because it kind of precludes this playful, curiosity-driven approach to DNA sequencing, something like, it's at 3 a.m. on a Monday and I desperately need to know how the spiders in my bathroom are related to each other. Like, they're obviously the same species, but are they all the same family? Is there a different clan living by the window and under the bathtub? This is clearly not a serious scientific project, and I wouldn't want to spend 500 euros to find out, but what if I didn't have to? What would that look like? And for that, I'm going to start with a requirements/wish list for open DNA sequencing. One, It should be suitable for in-field use, and ideally that would mean I could chuck it into my backpack when I'm going hiking, but as we're gonna see, that's a little bit ambitious, so I would settle for, I wanna take it to a hacker camp or a conference and put it in checked luggage. For that, I'm gonna wanna keep the size and weight down, I wanna worry about the power budget and ask whether it can run off of the battery. Robustness and operating conditions are a concern, like does it have to sit on a stable surface during the run? And run times are also a concern because mostly sequencing runs take several hours. Next one, safety. This should be safe for in-home and in-community lab use, which is a pretty serious constraint already, as we're going to see. This means I'd like to avoid toxic chemicals, I'd like to avoid dangerous currents, and UV shielding is a concern, all of that. Next one, the so-called applications. I am willing to concede that we maybe don't need to be able to sequence the whole human genome with it. We might be happy with limiting ourselves to something like SNP analysis and species identification. And four, it should be open, and that means hardware, software, and wetware. And this is maybe a good time to make a bigger point. The DNA sequencing system will be an interplay of open hardware, open wetware, and open software. And unfortunately, among the three, the state of open wetware is very sad at the moment. The good folks of open wetware are trying to change it, as are the open bioeconomy lab folks, but it's still far away to go. And for our DNA sequencing system, this would mean giving preference to reagents that are well documented, widely available, instead of having to rely on expensive vials of magical mystery juice where the vendor keeps the composition a trade secret, which is sadly extremely common in wetware. Okay. First off, the fundamental problem with DNA sequencing that you have to solve is that DNA is too small and the chemical basis too similar that you can just look at it and read the sequence off directly. There's been research on it, but there hasn't been a breakthrough. So all of the sequencing technologies that we do have work indirectly by converting sequencing information into something that we can measure more easily. There is a bunch of these available by now, and with our wish list in mind, there is one that I find particularly interesting, which is Sanger sequencing, also called DNA sequencing like it's 1977, because that's when this was invented. It's still in use today. It's been used to do the Human Genome Project, so it's got some chops. And among all the sequencing technologies, the hardware and the wetware requirements are the most accessible. And I have to stress here that it's not even so much about the hardware requirements, because I suspect that about half the people in this room could build the hardware platform for some other sequencing technologies as a fun side project. But for Sanger sequencing, the reagents are the most accessible. There's also not much in the way of patenting that you have to worry about. It's very well documented. There's a ton of literature on it. And all of the components are widely available from lots of different manufacturers. Okay, I really wanted to show you how the Sanger reaction works here, because it is a really clever piece of biochemistry, but we couldn't fit it into the 20 minutes. We're gonna have to make do without, and we're gonna have to keep it a little bit abstract. I'm just gonna talk you through the general flow of the process. You start with a DNA sample, and you run the Sanger reaction on it. And you just need to know two things about the Sanger reaction. One of them, I assume we all know what PCR is at this point, thanks to a certain coronavirus, at least in the abstract. And the Sanger reaction is very similar to PCR, and it uses some of the same reagents and has pretty much the same hardware requirements, for which there are already several open hardware projects like OpenPCR and Pocket PCR. And also building a PCR thermocycler is kind of like the hello world of open labware. So I'm going to consider this a solved problem. Next up, what the Sanger reaction does is essentially it converts the problem, what is the AGCT sequence of this molecule, to the much easier problem of how long is this DNA molecule. Again, sorry about not showing you, it's really cool. I have an animation, maybe I can provide a link later. And the reason this is a much easier problem is this is a Swiss Army knife technique of molecular biology, just telling how long a DNA molecule is. It's called electrophoretic size separation, or electrophoresis for short. And there are 3 broad approaches you can take for that. I don't know which one's going to be the winner. I'm just going to run you through all 3 of them and give an overview of the challenges and advantages. First up is slab gel electrophoresis, which literally uses a slab of gel 30 by 40 centimeters. And the way it works is very simple. DNA is negatively charged, so if you put it into electric field, it's going to migrate to the positive pole, which gives us the ability to pull a DNA molecule from A to B. And if we put kind of an obstacle course in the middle of it, that a large molecule takes longer to migrate through than a small one, then that gives us the ability to separate DNA molecules by size. You can think of it maybe like you're trying to get through a crowd and you have a bunch of friends with you, you don't want to lose each other, so you hold each other's hands, form a long chain, and weave through the crowd like that. And it's going to take you much, much longer than if you're just by yourself. Same thing sort of applies for DNA molecules. The obstacle course is made of a polymer that has variable size pores, and the DNA sort of weaves through that. So, slab gel, as I said, polyacrylamide, big slab of it. The slab gel is immersed in a liquid buffer, as are the electrodes. You apply a voltage across the whole thing, and then the DNA migrates through the gel towards the positive pole. Setup looks a little bit like this. And then in the next step, you have to sort of make the DNA visible, which is not on its own. You do that using a DNA dye, which has the extremely cool property that it fluoresces only if it's bound to DNA. Otherwise, it just doesn't do anything. So you can make the DNA visible like that, and then you get this band pattern that you can reconstruct the sequence from. This is from Sanger's original paper, actually an earlier one. Same principle, that's the band pattern, you can reconstruct the DNA sequence from that. A few considerations for that. One, you use polyacrylamide gels, which has great resolution, which means you can tell a 50 base pair long DNA molecule from a 51 base pair long molecule. The problem is that the precursor for it is acrylamide. You have to use that to make the gels, and it's a very unpleasant neurotoxin that absolutely has to be handled with care and under a fume hood. And I would not be comfortable having that around a community lab or a home. It also generates hazardous waste. It's just nasty stuff. I'd really like to avoid that. There's an alternative that is often used in gel electrophoresis called agarose, which is non-toxic, but it has a lower resolution. Although there have been papers that have pushed it to single nucleotide resolution, so that might be an option. Or there might be another polymer out there that gives us both single nucleotide resolution and is non-toxic. I don't know. Next consideration is power. So we might have seen DIY gel electrophoresis that looks like that, and that works for some applications, not for Sanger sequencing, because Sanger sequencing pushes you to the limits of what electrophoresis can give you, and you're not going to get there with a Tupperware box and a stack of 9-volt blocks. Because, just to give you an idea, sequencing gels are run at 1700 volts at 70 watts for 4 to 8 hours. It's a lot, that's a lot of power, I know. You also have to run it at constant power, meaning the power supply has to dynamically adjust the voltage and the current, because the resistance of the buffer in the gel fluctuates during the run. And if you don't do that, then you're just gonna run your gel hot, it's gonna melt, it's gonna crack, it's gonna be useless. Then other consideration related to that, with great power comes great thermal management. You absolutely have to do that. In practice, when you do these runs, you have to cool both the gel and the buffer continuously. Next ones I'm going to skip over because I already have too many things here. That was it for slab gel electrophoresis, and capillary electrophoresis switches out the biggest slab for thin glass tube, like 50 to 100 micrometers across and tens of centimeters long, filled with a viscous polymer, not polymer, you use other polymers for that. Then you inject the sample at one end of the tube, you apply voltage, and then the DNA migrates through the capillary, and you detect it at the other end of it using a fluorescent detection unit. Kind of like this. Because it is essentially a long, thin column of buffer, it's a much higher resistance path than a slab gel, which means you can run it at higher voltages, but in the microamp range rather than milliamps, which is friendly currents. The heat dissipation is also much nicer in such a setup, so you can run faster slab gels without melting your gel, which makes for nicer run times. The downside is that glass capillaries are prone to breakage. The sample injection can be really finicky, and you need a very precise alignment of the detection assembly. The detection window is very small, so you have to align everything very precisely. Both of these things are not really friendly if you want to chuck into a backpack, I imagine. So. And the last option that we have is microfluidics electrophoresis, which uses a small area chip or glass slide or even paper and serpentine channels that kind of fold along the migration path into a small surface area. And remember, the distance between electrodes determines how much power you need. So if you can fold the migration path into a small distance for electrodes, then you can run the whole thing in much lower power. And there has been, it's been proven. There's papers from 2003, meaning it's really old at this point and proves out the whole thing. So in principle, this would work. The downside of microfluidics is that fabrication can be a little bit tricky, it's challenging, although it has gotten a lot more accessible over the years. And the good folks from Bacteria have been doing a lot of work on DIY microfluidics already. It's a wonderful rabbit hole, but one that I haven't gotten to go down myself much. Okay, with this, we're in the workflow at this point, so there's just one empty space, and that is there because at some point you're going to have to make your DNA visible, because on its own you can't see it. And how you do that is you use a DNA dye. I mentioned that already. You add it to your DNA sample, you shine a light of one wavelength on it, and then it fluoresces on different wavelengths, only if it's bound to a DNA. The popular setups in the last years have used blue light and one of the green DNA dyes, like gel green and cyber green. And the excitation emission spectra looks something like this. This is for gel green, but they are pretty much all the same. And you can see that the excitation and emission peaks are very close together, which makes for a very noisy fluorescent signal and much higher requirements for sensing and for filtering. There are different dyes, the red DNA dyes, which have a much larger distance, but they also need to be excited at around 275 nanometers, which means UVC. Can get away with UVB, but this used to be traditionally mean that you need a UVB bulb or a deuterium arc lamp or something like that, which have high power requirements and heat up a lot, and they're also bulky, and you need to shield the whole assembly for UV radiation. In short, it's not a lot of fun to work with in a portable device. However, over the last years, very exciting, UVC LEDs have become much more accessible. 10 years ago, they were available, but they cost 300 euros a piece or something crazy like that, and nowadays they cost a few euros. And they give us the very cheap option of cleanly separating the excitation light from the emission light of the red DNA dyes, which is very exciting, and a huge step forward for the detection side of things. Skip that. And with that, we have our whole workflow covered. And this was a lot of ground to cover, so I'm just going to try to put everything into one slide. Okay. Status quo is very dissatisfying. DNA sequencing for fun and in-field use. The closest available candidate is proprietary and too expensive for fun use. It's also dependent on one vendor, and they have been doing some not so nice things in the last years in terms of cost. DNA sequencing open system would mean open hardware, open wetware, and open software. And of these, open wetware is in the saddest state of the three, sadly. Finally, we have this whole workflow. There are already open hardware projects for part of this workflow. Another part is by now much more accessible thanks to cheaper UVC LEDs. And the remaining problems are mostly in electrophoresis, for which there are three approaches. Snapgel electrophoresis is the lowest tech one, but it's very unclear whether it can give us what we need in terms of portability, safety, and power requirements. Capillary electrophoresis is a lot better. However, it's kind of finicky to work with, and you also still need kind of a long tube that needs to be handled carefully, so maybe not so great for in-field use. And then there's microfluidic electrophoresis, which is the most promising of the three, but still kind of an open quantity for DIY use. And that was it. Now you know pretty much everything I know about open DNA sequencing. If any of this sounded at all interesting to you, I would be excited to talk to you. Thank you.
Thank you so much, Lisa. It's really nice to see additional intersections coming in. I was not familiar with the term open wetware, and I'm sorry to hear that it is not yet in a good state. So hopefully your work and other people can kind of keep pushing that forward. So next I'll be introducing open source hardware, sustainable circularity, and the collective search for the universal super part, or pardon me, super universal part. This talk is by Lars Zimmermann. Lars is a Berlin-based designer, artist, and activist. He runs the design studio My Factory, teaches at universities, and is a co-founder of the participatory circular design project IKEGO, an open and modular Lego meets IKEA design system. You should join.
Hold on a second. I don't know how to get out of this screen.
Just bring me to a browser, that'd be cool. I don't need my presentation.
Okay. We need something. Yeah, give me a, I don't know.
I don't know how to. Oh, who knows how to run this computer?
Yes.
Put your mouth to the top of the next. There.
Thank you!
Yay.
Yeah! All right, which presentation?
Oh, no, just let me take over. I want to show that side.
All right.
Thank you. Quick second. How do I unzoom this? All right. Thank you for coming. A couple years ago, there was a group in Berlin that was interested in making open source hardware work for sustainable circularity. What is circularity or circular economy? I assume all of you are aware that making products destroys the planet, because we have to mine resources, and in the end, we have to discard a lot of trash. And I don't like that, and I assume many of you also don't like it. There are many people that have ideas how to solve this, and one group It's called the circular economy. People, so to say, and they have an idea of a collection of practices that will help us to keep already extracted materials in the loop so that we can reduce the pressure on the environment to supply us with new materials and also reduce the pressure when we discard things. The problem is that these practices need to be supported by the design of our products, and currently this is not the case. Current design paradigms are there to support these practices. So, open source hardware to the rescue. Why is open source methodology a great match for these practices? First of all, if you look at the open documentation. Open documentation, of course, helps with things like repair, manufacturing, refurbish, great. Then the second thing is that you are allowed to make a commercial use of the products. This also helps, for example, when someone wants to manufacture spare parts for repair, or manufacture things and put them out maybe under a brand name, and so on. And there is a third line in the open source hardware definition that is my favorite line. That's the line where they start to talk about how to design open source hardware. And there they talk about that you use readily available materials and components and open source design tools with the idea to maximize the ability of people to make hardware. So with the idea, so you choose components and design methods that are maybe easy to understand so that many people can start to work creatively with hardware. And if you look at these circular practices, these are also invitations to work creatively with hardware. So people are invited to do more with things than just consuming them and discarding them. No, to be repairing, remanufacturing, and so on. So also on that level, open source hardware helps a lot with making circularity happen. But of course, for real circularity, you need to have a few more things to design. And I'm particularly interested in this last part, the repurposing part. Because open source hardware, yes, open documentation might help us that. But what is repurpose? It's the idea that you use a part, you reuse it, but you use it for something else than it was initially intended to. So you give it a new use case. This also needs to be supported by design. And we thought about this for some time, and basically the idea that we came up with is that we make products from open source, multi-purpose parts. So really like Lego bricks, where you can use the same brick for many, many different applications. And in the Lego community, they have this creative parts use as a term, you know, everyone loves it when you come up with a cool use for an existing part. And I think we need to design the parts that enable this. Then the circularity really becomes easy and actually quite fun. So we started this project called Ikego, and here's our line. It's a young participatory design research studio. That's what you have to understand. This is really research. We try to invent this kind of open source modular building system to make really anything. So like Lego meets IKEA. And how does it look? You see, we have here now many parts. So basically, we try to invent parts, and we try to make sure that there are multi-purpose. So we only add them to the catalog if we have a couple of ideas how to use them, but then we basically put them into the race and see how many use cases are discovered over time by the community. So for each pass, you can then click and see what use cases are there for this part already, and then you can click on these things, and we call these things analog to Lego, of course, sets. No, these are not products, these are sets of multi-purpose parts. And then you can see here a classic product-like documentation, and you can, of course, in each of these sets, click on a button called Parts List, and there you get to all the parts that are used in this. And I think it's obvious that all of these parts are open source. So you see they are well documented here, and we even have a download form where you can download them and start playing with them in cut, maybe manufacture them using a digital manufacturing method. So who creates this? Of course, this is an open invitation for many, many people to contribute to the system. If you scroll up here, you see people that already contributed to this system. And you can see what were their contributions. And if you have a dynamic like that, that's really nice because some weird things start to emerge. I will show you one of the sets, for example. here. This is a chair, and the chair is it grows, you know, you can, I think, 16 different seating sizes. Okay, I got it. And here you can see a little bit of documentation, and down here is an image that shows who made these parts. You know, you see these rods were made by Parker without ever foreseeing that this chair would happen. And Bela made this slab, and Max also for his chair made this slab, and Birte added these KT boards, and I have many of these parts in my workshop, and then one day they're over on the table, and next minute this chair was standing in front of me. Oh, that's actually cool. And then my 2-year-old daughter was sitting on it, hey, it worked, and she enjoyed it, so wow, a new set. Maybe quickly, how does this work? Why do all the parts usually connect to each other? And this is because we invite creators to base them on the same grid. You know, like maybe so many of you are familiar with Erector sets. It's basically the same idea, but for the real world, you contribute based on this grid. So things grow, and we hope in an evolutionary process to discover many use cases. And here's the interesting thing then, what happens if you have a system like that, you get to a network effect in the parts. I assume many of you know the network effects from social networks. The software itself is not very useful, but the more people that are there, the more interesting becomes the software. The same is true, for example, for Lego bricks. If you have 20 Lego bricks, you can build something out of them. But if you add 30 more, the initial 20 become more use cases, more meaning. You know? You can almost build 1 billion combinations from just 6 Lego bricks. And over time, when our parts that we design here turn out to be really super useful, to turn out to be multi-purpose, then we get to the same problem that there are many different sets that you can build. But the question is, what do you document? What do you put on the page, given that documentation takes a lot of time and effort? And right now, I'm an intern who looks into how maybe AI can help with that, so that we might in the future improve this or get this process up to speed. And check. And there's one way for all of you to test this. We have this little fun thing we recently added to the page called the randomizer. If you go to the randomizer, you can click here on the button, and it will generate a selection of 30 random parts from our catalog. And we invite you to look at these parts and try in your brain figure out how you can combine them to a working set, and then make just a 5-minute sketch and send it to us, and then we'll start a little collection, so we already can use community input to see what potential is in the few parts that we already have. And of course, this is only an invitation to then go beyond. You will probably at some point be disappointed with the parts that are there, so maybe you have an idea, I missed this and that part, and then you can start contributing and building the system and make it really strong, hopefully. So there we are. What's the trajectory of this project? Where we want to go? What's the ambition? The ambition is huge, but right now we think that the system needs to become better, or actually really good. So currently we're focusing on getting creators in. So designers, people that know how to make great sets, so that we can maybe build this system to something that's super useful and customers want. And then the next stage will be to onboard manufacturers. You know, many different manufacturers, they all can use this open standard, distribute products to their clients, and then customers come in, and then the project really can go and make impact. But right now, we need to onboard designers. And that's, of course, difficult. How to build community. And I think in this rough stage this project is in right now, it's really hard to find people that see the potential and want to dedicate some time to this. But I had this idea, these people must exist. It's just a needle in the haystack. We need to figure out how to find them. One thing that we recently did is that we published a call for interns. That's here. And luckily, because some people with a distribution network shared it got a bit viral, and I got applications from all over the world, from people that want to do an internship here. And it's really insane. We have now people from 3 continents and 5 countries. From Dubai, there's someone. And the craziest thing that the people that apply here, I can see sometimes in their emails that they really have understood what this project is about, and they're excited about it, and they really want to contribute to this now. It's really, from all the people that applied, it's really the smartest ones that actually want to contribute to this, which makes me really hopeful. And right now we have 8 interns in parallel, creating new sets, elevating the system on all levels, and this is really, really cool. I enjoy this process. And of course, this only really worked because someone was generous and shared it, you know? So we were able to find these people, the needle in the haystack. And if you want to help this project, I would also invite you to maybe donate, share, join the Ikego Attention Army, so that we can find more pioneers and build this to the next level. Okay. Since we are here in the open source hardware crowd, let's know a little bit for a moment on licenses. How is the system open? And we somehow had to create our own little license for this. Why? Because, so just a nerd minute maybe. From what I understood, you know, in software, you have you get your IP automatically, you know? It's a problem, they hang on you, you know? And then you have to use a license to get rid of this problem, you know? So, and maybe you ask for attribution. But hardware, I learned from Michael Weinberg, is born free, you know? If you don't do anything, then it belongs to everyone, you know? If you don't file for a patent or design rights, it's free. Then you don't need a license to show that people can do something with it. But here comes the problem, how do you signal to someone that you didn't file for any design rights or patents, you know? I couldn't find anything, so we, a couple of people sat together and we created this Ikego public promise, which basically says you can use these parts for whatever you want to do with it, and you have to take care of anything. You have to not to give attribution, ask for permission, send a link or whatever, you know. People can absolutely do what they want with these parts, because we believe that a system like that can only work if it's absolutely free. You cannot burden people with attribution. Because how to make attribution when you maybe build something from 15 different parts from 14 different designers? Super annoying. So that's why we had to come up with this somehow license-shaped thing. And lawyers tell me, that's okay, it's already 70% proof, which is good. Well, if you understand something about law, that's already quite good. Okay, how much time do I have left? 5 minutes, right? 6? Okay. So then I can share a few more things about this. One thing that we do right now that shapes a little bit how things look in the system is that, of course, we want to have a system that is made for local production, so that ideally these parts can be made everywhere on the globe with very simple tools in every workshop. So one thing that we run there as an experiment right now is that we have a very luxurious tolerance, which means that we don't say what materials you have to use to make these parts, only if it's a strong part or a soft part, you know, so people can really use local materials for this. And the other thing that we do is that we have a 10 millimeter, at the moment, tolerance in terms of the size of the parts, you know, so that you don't have to have super accurate machines. This means that in this logic, this is the same part, you know, it's the very same part. Doesn't always work. Sometimes we have to define parts a little bit with less tolerance, but ideally they allow for this tolerance. And here you can see this is the same chair from the same part. You can disassemble all these 4 chairs, mix the parts, and these chairs will still work. And this is the idea. And this also means that these in this catalog, what you see there are mostly rough prototypes, you know? So that's why it looks pretty unpolished to many. But the idea is then that people can take this and then really make a really beautiful version out of this. That this would be called, we call it make, polished thing. And when someone comes and says, okay, I need to figure out how to use my factory to make this product and give it the absolute final polish with a designer involved, then it becomes a product. And there's the time where designers can come in and really decide on the final materials, colors, even curves and shapes. This is how this goes. And one more question, since I have 4 more minutes, I want to ask you, why is something like this not existing? Because usually we see new stuff when new technology emerges, of course, then suddenly something becomes possible. But this is possible for 30 years now. You can maybe say you need the internet to facilitate collaboration. And I think one of the reasons why this doesn't exist is this would have to come from the business people, you know. And there are a lot of systems that are modular, but usually they only connect within itself because they are closed source and they try to create a lock-in effect. You know, it doesn't make sense to make something super open. So you really need to have some weird open source hardware enthusiast who has an interest in seeing the potential in making something super open. And the other thing, should have come maybe from designers. But what I learned is that designers don't think that way, you know? Hard lessons. Designers really focus on other stuff. They're interested in curves and this kind of collaborative dynamic they really can see or plan for. There was one point in time where this was a little bit different. Around 2007, 9, 8, there was a term called open design. It was much more popular, and at that time, a designer founded a project called Open Structures, who has the same, which is still active. I encourage you all to check it out. It has the same idea that you base designs on a shared grid and then grow the system over time. But this project, sadly, is a little bit like Open AI. It's not open. They have some weird license that doesn't allow for commercial use. And it's not open source because you can't really download design files. But one thing this project has, what we don't have so far, it looks awesome. You know, these are really designers. They really look for the final polish, and here we came more from the DIY side, you know, and these are all rough prototypes. It looks ugly, but this is something that designers really have a hard time to connect to. They look at this and say, oh, DIY, I don't want to get near this, you know. I learned this late, because I don't come from a design background to this, but now we understand this, and luckily we have now AI tools, and maybe we can figure out to use these tools to help with the looking beautiful part. And maybe to sum this up, I think this presentation was full of call to actions. This project needs you on many, many, many levels, and maybe some of you want to get involved with it. And I want to give you what's the potential here. It's rough research stage right now. But where could this go? I'm a big fan of WordPress. This is a WordPress page. You know, WordPress at some point ran 35% of the websites in the world. Why? Because it was open source. Because it was open, it was a much more useful tool. It enabled people to build the websites they wanted. And imagine if you get this to become a thing, you know? How about maybe in some years, 35% of the objects in this world are based on an open source modular system that we all can play with in our homes. I like that vision, it inspires me, and maybe it inspires some of you, and you want to help grow this system. Thank you.
All right, thank you so much, Lars. That's all very exciting. Next, I will be introducing Anna Marks. Anna is an embedded systems engineer with a degree in CS and EE, professionally a tech lead for embedded Linux. She channels her expertise into ZE Reader, an open source Zephyr-based ebook reader project. She uses it to explore how agile software methodologies can improve the design and traceability of open hardware. And this talk is titled The ZE Reader Project, Adopting Agile and Software First Methods in Open Hardware. Thank you. Thank you.
Yeah, thanks. Then let's start. I'm Anna. By day, I'm an embedded software engineer, but sometime, I think back in 2019, I decided I could also study electrical engineering, because why not? And did this as a hobby beside work. So why not? I could do. And finally, eventually, I needed a bachelor thesis project. So I started thinking about what want I do. I already have an exam in software engineering. No need to do that again. I want to do an electrical project, a hardware project, something I can tinker on. And I want to do something that is really for me, that really gives me a plus not something that is just gone if I finish the thesis, not a next easiest project. And the ideas the prof gave me was not quite good, I don't like it, but they give me the possibility to name my own ideas, and I thought about and finally remembered this thing, the open book by Joey Castillo. I think he's also here. And yeah, I like that project, but it didn't really match my needs. But why not build my own version matching my needs as a thesis? And the prof said yes, so I started. And my idea basically was also build a microcontroller-based design, because a full-blown CPU is just overkill for reading EPUBs, I think. With nowadays microcontrollers, there's so much resources available, so much RAM, so much CPU power. No need to do a full CPU. And also, I was a bit afraid of building a PCB with all the memory timings required right in a bachelor thesis would be overkill, wouldn't dare to do that. So let's see if microcontroller was feasible. Also, I wanted to have a bigger EPUB display, e-reader display, because that matches better for my needs. I want to have a LiPo battery with USB-C charging, also fits better in my needs in my daily use. And best case, one single PCB because it's easier. And I absolutely want native EPUB handling, because preparing the file on a host computer is not really accessible and not really usable in my daily life. So this was my requirement. But wait, all the things involve software again. I didn't want to do a software thesis. So I set a focus to hardware, and software should just be a side note during the thesis. And also in my daily life, in my professional life, I have seen so many bad hardware projects, hardware-software projects, because they were completely decoupled. Usually hardware is specified first without even really think about software needs. So I decided I switched approach. I want to do software first to evaluate if it's really feasible, if the idea works at all, but also to get the requirements for the hardware development and not to waste time and money in an approach that just doesn't work. So to check that all, I started, as said, with software first, with the most primitive software proof of concept I can imagine, and with the promise to write as less code as possible. Just to evaluate the concept at all, using off-shelf components, just to really make sure the concept itself is feasible. And as said, key for me was writing as less code as possible, because bachelor thesis, I just had not the time to write all drivers from scratch, and I did not want it. And also I want to have a really, really good hardware abstraction, because at this point of time, I haven't had selected the final hardware. And I was not aware if it works, if the selection would be fine, if I need to switch components. But I did not also want to write things again and again. So I decided to utilize Zephyr as a real-time operating system, even without writing any real-time code at the microcontroller. Works. And the idea of using Zephyr is it has a really, really good hardware abstraction. It uses a description language called device tree, similar to Linux device trees with a clearly defined API. And in best case, if I would switch hardware components, it's just a write in the device tree, just a change in the device tree, switching the component without touching any code. And on the other hand, it also gives me a really large driver ecosystem with ready-to-use code, so not needed to write that much on my own except for the actual application. And with using this already defined ecosystem, I can just define the hardware selection based on the drivers already in place, which speeds up the whole development a lot. So I could just focus on making sure my selection was right, my assumptions were right, and I can start with the actual prototyping. And so I did, first with a breadboard approach, just making sure I can get everything to work in the easiest possible setup. Afterwards, I switched to a more rigid approach to make sure it's a bit better transportable, better handy for a bit more development and making sure the software concept fits. And here's an example, that's a Zephyr device tree. It's really a description of the hardware attached. If I would, for example, switch GPIO pins, attach the buttons in a different order, different pins, it's just a configuration change and no change in the software at all. And with that, I verified the software first. I confirmed my project idea was viable. I learned a lot about problems, pitfalls, limitations, and about the RAM use. This was the biggest risk from a software side, if the RAM of a microcontroller is enough for EPUB handling. But it worked, so I could start with the actual hardware development. Besides this, I also gained experience in the components and the approach. And so far, I had really minimal invest because just off-the-shelf components, not that much time spent, good for rapid prototyping. And as well, with that software first, I had a base software to validate the design, the hardware design afterwards, right to fit. Maybe adjust some GPIOs, but ready to use. And then I was able to start with the actual fun part, with KiCad and my PCB development. And I wanted to build something like this, roughly spoken, but still a software engineer and not that experienced with PCB design. So when looking back, some blocks, and I think I had at least 5 blocks I was not really that confident with. Just trying around and find out would be probably too expensive and too slow during the thesis. So I decided a modular approach would be best. But also, as a software engineer, I would like to have version control, traceability, automation, testing, generating documentation, all from one thing, matching to exactly the board I built, continuous integration, maybe even continuous delivery, all that stuff that we know from software development. And I think there's no reason why we cannot have this also for hardware development. So first, I started with modularization and a modular approach. I tried to split the design in functional blocks as possible to minimize the risk and maximize reusability. Best case, I think, would be building and verifying each block, each design block, semi-independently, maybe even as an own breakout board design, so you can just switch out the components from the prototype to proof of concept and test each component at a time. But also speaking in thesis time, this would be too slow, maybe too costly for especially as a hobbyist. But in terms of modularization, this would be my absolute best case. I compromised myself with approach like that. I used a predefined microcontroller board because this is the most riskiest component, and everything else integrated with one PCB for the start. But I decoupled the components with 0 ohm resistors, so I was able to bring up each component at a time, verify, go further, so I can isolate issues, errors in the components, and also make a good modular approach with less effort as possible. And yeah, speaking in modularization, with KiCad 10, we got a thing called design blocks. And I think this is, from the tooling side, a really good fit for what I wanted. But when I started the project, KiCad version 8 was on time, and the second revision of the board was built with KiCad 9. By now, I hadn't the time really to switch over and try KiCad 10. But the best thing I had then was hierarchical schematics, which is at least the building block level on the schematic level. And it works out fine. It's somewhat reusable. But here's definitely room for improvement and also introducing the design blocks on the PCB level. Then I wanted to start really with adopting agile approaches. And the first thing, and I think from my point of view, the most important thing is version control, because I think it's the base really needed for traceability. Make sure your documentation fits exactly that PCB that you see laying around your desk. You can really make the match. It's also a good base for automation, for documentation, together with CI. So I introduced Git. Before KiCad 9, there was no native integration, but as a software engineer, doesn't bother me. I can use Git on a command line level. But what I can't do is visually diff schematic files just on the text level, which is what Git does. Git is not built for hardware. So I also utilized the KiCad revision inspector query for visual diffs, which makes it a bit easier to really track down the changes, maybe track down issues. But the tools are there, looks a bit like this. You can do a visual diff of the components, really helps a lot if you want to find an issue. And then the next thing, which is really essential, I think, is CI. For my approach, I think the most important part is to make sure I can really identify each version of a PCB lying on my desk together with matching documentation. So the first essential step in a CI workflow is to replace some kind of placeholder with the actual commit hash. So the commit hash is written on each PCB silk screen, on each documentation file, and makes it really trackable what is matching together. On the right side, you can see how it could look like with GitHub and keyboard. Keyboard is one possibility to build a KiCad CI. Nowadays, KiCad also support job sets as a native kind of automation, which can also be run in CI level. I think right now it's not that capable as keyboard, but probably it will get in there soon. And you can do funny things like this. You can generate interactive BOM for populating the device. You can render high quality pictures of your PCB for documentation and even more stuff. But adopting agile approaches in a one-person project has also some limitations. For me, it was mostly cost and time. Just as a hobbyist, with limited time, you cannot implement everything you want. And also, not all of the software workflows you can imagine in an agile world, agile software development, does apply to hardware development. For example, Git is not intended to do the schematic diffs. It's a visual format. Git is made for text format, so you need some additional tools like Kiri, but also when speaking about the working mode. In software, you always have self-contained steps. You work in self-contained iterations. Each iteration itself is valid. If you do a hardware redesign, this does not really apply. What is the best workflow? I have no clue right now. Maybe design blocks can help to make it a bit better, but no clue. There, the tools do not really match. Not right now. What I wish for? More adoption of agile techniques in hardware development, PCB development, not only in the maker scene, but also in professional teams. And generally more collaboration between hardware and software engineers. And personally, much more time for fun projects. And coming back to the ZE reader, current state is the thesis finishes 2025. Nowadays, it's 100% hobby, most limited factor time. I finished a second revision in winter with a lot of hardware improvements, but also a lot of new issues and still a lot of ideas what to do next. The software is some kind of never-ending story. There are a lot of things to do to improve. Also here, limiting factor is time. I designed a first case some weeks ago because I need to bring it here and make it really capable and accessible. But here it is here, you can try it out. And to sum it up, it's still a prototype, pet project, but you can use it. I read by now 3 books with it, so it is usable. Looks like this. The display rotation is still broken because the Zephyr driver did not support portrait mode by now, something to fix. But if you're interested, sources are online. Thanks to Isla for supporting the PCBs. And if you want to try it out, you can come by and just test it. And with that, thanks for listening.
All right, thank you so much, Anna, and thank you to all of the speakers today. This has been a really amazing day full of so many great talks, and it is my great honor now to reintroduce Lee and Sid, the organizers of today's event. Thank you.
Thank you so much, everyone. This was really amazing. It's so heartwarming for everything that feels like just looking at spreadsheets for like 9 months to turn into real humans with all kinds of really amazing ideas. So thank you guys so much for really making this event real and for being a part of this community. And yeah, it's so lovely to have you all here. So thank you. A couple of logistical things. Also thanks to our sponsors for making this happen. I know many of you have been hanging out with them in the exhibit hall and just like getting a chance to chat. Thank you again to Berlin for helping, for providing the space and for making things happen today. We're not done though, which is awesome. If you take your schedule and you open it up and you look at the back, you'll find the schedule for day 2. So many of you have already signed up for workshops, which is awesome. There is place in workshops if you have not officially signed up. The rooms are quite large, so you should be able to just hang out and kind of see what's going on. We do have one workshop cancellation. Old Tech New Game is not running, but there's going to be a free-form soldering workshop. Details incoming. So yeah, this is kind of what's going on tomorrow. There's also some discussions you'll see, and these are going to take place in different rooms. So we're going to kind of do a little bit of a rearranging tonight, and we'll direct you tomorrow morning to where the room where each of these events is happening. If you have not signed up for a workshop, you can still also participate in our unconference. So by registration, many of you already have done this, but there are 2 really large pieces of paper. If you just want to put down an idea there and then just vote for the ideas that you like, what we're going to be doing after this ends is we're going to go through and just pick the most voted ideas, and we're just going to schedule them to happen. So I will send an email to folks with our schedule that we will create now. So if you have things that you want to talk about or things that you want to discuss, maybe a discussion you want to open up, or maybe just something you feel like the community is interested in, please put it on the unconference paper. We'll have a bit of time to do that before we leave today. So with that, I'm just going to pass this off to Sid for our year-round community update.
No, Joel. So usually this is Alicia's job, but Alicia is not with us this year, although we miss her dearly. I'm going to try very hard to fill some very, very big shoes. So every year we like to kind of review what we've accomplished as a community in the last year. So this is the community check-in. Yay! So in the last year at Oshawa, we have become a registered part of the Digital Public Good Alliance that keeps track of projects that exist digitally in the world that are keeping just making things better for the universe. So our certification project is part of that database now. We're really excited about that. We ran our first student-focused fellowship. So this fellowship was intended to help students understand how open hardware works, get connected with mentors, and get their own project certified. It was a really wonderful venture. We're going to be running it again. So if you're a student who's interested in open source hardware and wants to find ways to engage with that, but isn't quite sure how, that is the thing to apply for. It'll be running it again in the fall. We developed a open healthware certification, more on that soon. We also ran our first open healthware conference. The second one is coming up this year in San Francisco. We also did a lot of work around keeping the right to repair bill strong in Colorado. And we are continuing to do that work for a lot of different places. We constantly want to find ways to keep things accessible, open, and make sure that folks are allowed to know what's going inside their little black boxes. As far as certification goes, so the certification project is our most exciting thing that we like to do in 2025. We got 259 certifications that were new to the database. We also broke 3,000. We're sitting at about 3,300 right now. You can make that number go up. Every single one of you can help. We also got our first certifications from Luxembourg, Serbia, Algeria, Peru, Colombia, Pakistan, and Vietnam. We are very excited every time we get a new certification from a new country, and we also love to see that number go up. At this point, I believe the only continent we're missing is Antarctica. Michael nods. Antarctica. If you're in Antarctica, certify something, please. If you're, yeah, there's scientists doing science there. It's so easy. I literally, when I tell you that the process of certification is you open a form, you fill in a few details. The hardest part is naming your project. People hate that part. But you can name your project, and then you fill out a couple more details, you hit submit, it goes back to Michael. Michael looks at it and says, yep, that's documentation, and then it goes right into that database. The whole process, at most, takes 2 weeks to hear back. Your part takes 5 minutes. Healthware. So we've been working on the Open Healthware project for the last 2 years, funded by the National Science Foundation. It's been going pretty well. We're pretty excited about it. So we are working hard on what a healthware certification looks like. So we're focusing on what it looks like to have the full source available, not what it looks like to safety these items. So it's a little bit trickier in the healthware sphere, but we're very excited about it. We launched our Open Healthware Community Ed Guide that is available on our website for looking and downloading and printing. We are also having a bunch of more documents come out around best practices, replication, contribution, QA, QC, all the things that matter when you're making open healthware and what it looks like to make devices that are working in the health sphere. And we will be updating the website with a lot of info around that too. Coming up in the community, OSHWA is not the only group that does cool things, surprisingly. Well, we do have our Open Healthware Conference coming up July 9th and 10th in San Francisco. OSHWA is also hosting their annual Open Source Hardware Conference. Its 3rd edition will be happening right here in Germany on September 23rd and 24th. Highly recommend putting in your applications to speak and participate. It's a wonderful event. The organizers are so cool. And Gosh is celebrating their 10-year of gatherings with a Nepal gathering on October 9th and 10th. So there's lots of ways you can still be involved with open source, whether you're doing it at our summit or at other events. We love to see it. That was my speed run of the community update.
So now we are going to maybe take a little dinner break, I guess, and hopefully we'll see you folks at Seabase tonight at 8 p.m. For Open Source Open Mic. We have several performances, and there are all kinds of really cool things. There will be dancing, there will be singing, there will be also whatever you want to do at Open Mic. So yeah, come on by, and then at 10 p.m. it's going to turn into a dance party. So yeah, and then tomorrow, I don't know, what does it say?
That's a great question. It says 9 p.m. on there, but Lucas says 8. Lucas is in charge of the venue. 8 p.m.
8 p.m. 8 p.m. And then tomorrow at 7 p.m.
No, doors open at 8.
Doors open at 8. See you there. That's it. Thank you, everyone.
Also, real quick, if you're a volunteer, please come to the front for a volunteer photo. Thank you.
Oh, and also anyone with blue hair, we're taking a blue hair photo. Thank you.